enough, you would find a certain root radius. And why is that? Good. Okay, guys, so this is okay. How does the story work? The story works in a very simple way. You'll be attending the lectures being delivered by Professor De Borst and by Professor Pippen tomorrow. But according to our tradition, we don't want to kick you straight into these high-spec, high-level topics. So because, you know, for some of you, fracture mechanics is bread and butter, but maybe some other people in this room are working on topics which are somehow related to fracture mechanics, but not exactly into fracture mechanics. So the goal here, and this is the reason why I was invited by Francesco and company, is to give you the fundamental ideas about fracture mechanics. So we are sure that every one of you can make the most of the high-level lectures that will be delivered by Professor De Borst and Professor Pippen tomorrow. So if you already know all these things, fine. I think that this is, you should end up these two lectures feeling very confident, say, yeah, I know all this stuff, which is good. And if you are familiar with this stuff, you'll be able for sure to follow the lectures over the next 2 days in a very simple and straightforward way. Okay? So don't expect today, neither from me nor from Professor Berto, don't expect anything super high spec. Tomorrow and the day after tomorrow will be kicking you a lot, but today it's Sunday, and the idea is taking you into this school in a very gentle way. Okay? So, having said that, let's start talking about fracture mechanics. So, working? You give me something. Okay, it will work. Good. Good to know. Okay, so I'll be here. So, first question: what is a crack? Have you got an idea? This is very easy, because this is a crack we see in a piece of metal. So you can see the crack front here. You can see a little bit of necking here, striations, and this is a crack, very easy. So first of all, we need to say that even if we are dealing with a very simple material like a piece of steel, the shape of the crack can be very complex, and it's not a straightforward problem. So if you already know something about Irwin's problem or Griffith's problem, you can already see from these simple examples that their models are really already far away from reality. And believe me, these are very simple cases. But a real crack actually is something much more complex, because you've got a lot of mechanisms being involved. And this is what you can find in a process. This is basically a summary of all the processes that come into play when we have the initiation and the propagation of the crack. For instance, if you start it from the bottom, you can have bridging, that is some fibers preventing the crack from propagating. So some of you are working with composites. If you have fibers, this is a very common case. But also, if you think about concrete, when you have your reinforcement inside the concrete, again, you can have the reinforcement playing that role. After that, you have a crack, which is basically a physical entity moving this way. So friction. It could be static, it could be fatigue, you could have external components. So certainly the friction you have here is very important. After that, you can have hard inclusions, you can have a plastic zone. Here I have the crack, and the size of the plastic zone can change, the shape of the plastic zone can change. Here you can have the formation of bullets, and also the crack, actually, in reality, cracks never propagate following a straight rectilinear path. What you have is always a zigzag process. And in fact, sometimes to see Griffith's crack, you really need to observe your problem from a certain distance, because if you get very close to your crack, what you would notice is a zigzag path where the path, the morphology of the path, the direction of the path is characterized by, or depends on the morphology of the material. So really, we talk about fracture mechanics, but actually sometimes we don't really know how to answer a very basic question. What is a crack? Okay? I'm sure that you guys have got a lot of examples confirming this problem, especially if you work with high-spec, very complex materials. You mentioned biological materials. Cracking bonds, even more complicated because bonds react and you have self-repairing mechanisms which are not depicted here. So you have a material repairing itself. When I was a young PhD student like you, my boss came to me saying, test these polymers. Was basically, I was supposed to test two adhesive joints. So the glue and the two plates. I ran my fatigue test, very happy, I generated my crack. I went home, leaving the samples on the table. I came back the day after and the crack was gone. It was August in Italy. It was a polymer. Self-healing. I was like, okay, good, lesson learned. So, yeah, there are a lot of aspects which are very important. So, first of all, when you tackle your problem, the very first question you need to ask yourself is, what am I dealing with? Okay, what type of crack am I supposed to see? And we enter a field which is very, very important, which is what we call failure analysis. Okay? So this is something you should think about. Observing the process. Before modeling, observe the process, because the cracking mechanisms are very, very complex. And my personal suggestion is, imagine that you have a little kid or a little brother, and your little brother is curious about the crack you are dealing with. Think about a way to explain to your little brother what you are observing. If you can do it, so if you can break down your problem into a number of simple basic problems you can explain, then you can model those problems. If not, you would end up with a mathematical model making no sense at all. Okay? So we model reality. We don't play with the maths just for the sake of modeling, of using maths. Okay? And believe me, if you have processes like this one, it can be very complicated, but hey, it's our job. Okay, so let's start saying, okay, let's assume that we want to somehow model our crack. The first thing to do is using the right tools. Of course, there are very sophisticated models, but what we do is assuming that always, at least when we talk about the fundamentals of fracture mechanics, is that we are dealing with a linear elastic body. So non-linearities. Be careful, because in fracture mechanics, when we say linear elastic, we intend that the behavior, the stress-strain response is linear. But when we talk about elastoplastic mechanics, actually we make an improper use of that definition, because we should be saying fracture mechanics to model non-linearities. Because you can also use what we call elastoplastic fracture mechanics to model non-linearities which are not directly related to plasticity. Okay, so it's a quite reductive way to describe the problem. So the starting point of the model is assuming that you have a linear elastic behavior. If you have non-linearities, you enter a new field, and this is what we try to do at a very high spec, but to be honest with you, in situation of practical interest, still non-linearities are bad nasty animals, and we don't really know how to treat them in an effective way. Okay? So let's start then talking about fracture mechanics and what is the problem. So we have here on this side, we have a geometrical feature where the characteristics is that the root radius is equal to 0. We call it crack. So at this point we should say, okay, that's it, it's game over. Let's go to have a drink. Why is that? I mean, you should know what is the fundamental glitch in the model we use. Fracture mechanics. The problem is that a sharp crack doesn't exist, not even in a piece of glass. So, again, if we go back to ask yourself simple questions and give yourself simple answers, one should say, okay, thank you Griffith, but your model is really away from reality. Because we don't have in real applications sharp cracks. Now, if you zoom in enough, you would find a certain root radius. And why is that? Because the Latins used to say natura non facit saltus. That is, everything is continuum in nature. So, and this is what we have also at the crack tip. Maybe the root radius is very small, but it's always different from 0. So first, glitch in the theory. So if we assume that we have a sharp stress concentrator. Okay, so if we assume that our body is linear elastic, and we assume that, which is already a simplification, and we assume that our crack is sharp, what we get is the local stress field diverges, so it's a singular, it goes to infinity. Okay? It's much better if we have a finite radius notch, because the corresponding stress concentration, or the corresponding stress field is characterized by a finite value for the elastic peak stress. Here it's very easy because we go back to the theory as formalized by Peterson and Neuber, so very easy, KT stress concentration factor, which is another big joke. Why is it a big joke? Well guys, we are demolishing our fundamental theories now. This is the job today, to force you to do the thinking. Because our components are not based on specimens. And it's very nice to talk to engineers who are working on problems of practical interest, and they say, oh yeah, fine, it's the net area, the gross area, force divided by area, blah blah. I said, okay, good. Now we design an engine, please, and we have a problem there. Tell me where your net area is. So again, it's a very nice theory. We are very grateful to Peterson and Neuber, but nowadays we need something more. And this is why Professor Berto, after me, will try to talk about the local approaches, because we need to get rid of Neuber and Peterson, because they are very good to understand, but very bad to be used to design real components. Okay, so this is the problem we have. This is Griffith's problem, and so we know that it goes to infinity there, and we know that in the end, real materials, in any case, even if we assume that they are linear elastic, they are not. And why can we still use fracture mechanics? Why can in any case assume that our material is linear elastic, and in any case we can still perform a decent design no matter the field? Why is that? Because if you do a little bit of calculations and you consider that your notch is sharp here, and you can easily do that using a commercial FE code, and you can get your sharp notch, you can solve a linear elastic model, you can solve an elastoplastic model, or you incorporate the non-linearities you like in the constitutive law of your component. And in the end, what you get is that very close to the notch tip or the crack tip or whatever you want to call it tip, your solution is bad in any case. But no matter if you are using an elastoplastic model or a linear elastic model, they are both bad for different reasons. But actually, if you move a little bit away from the tip of your stress concentrator, you see that in the end, overall, in general terms, using a lot of engineering pragmatism, there is no big difference between the two fields here. So one could say, okay, fine, if the elastoplastic or non-linear stress field is very similar to the linear elastic one away from the stress concentrator, why should I make my life so complicated? I can keep using a linear elastic model. Fine, but this tells you something else here which is very important. all the classic theories, and in particular, I mean, not right now for very strange reasons, I work in the Department of Civil Engineering, and sometimes it's very tough to talk to my colleagues, structural colleagues, because for them everything is nominal, and if you go local, it's at the tip of whatever you are considering. And for me it's like, I don't care what's going on there, because it's not important at all. Because actually materials and components, really the structural integrity of components and material depends on what happens within a very specific area surrounding your critical point. Because materials have, or the strength of materials is characterized by what we call a structural volume or a control volume. So the good thing, the good news is that we can simplify our life for two reasons. First of all, we can assume that with a crack is a sharp notch. So we sort out that problem, so no root radius. And the second point is that we can make everything linear, elastic, because if we move away from the stress concentrator or the critical point, that is, we consider the process zone. The difference between the non-linear solution and the linear solution is so little in general that can be neglected. And this is the reason why fracture mechanics has been so successful. Because all these simplifications are very clever. Does it make any sense? Are you with me? Okay, so this is what we are trying to do then, simplifying the problem and making our life simple and efficient. Okay, when we talk about cracks, as you know, we have three possible mode of loading. Mode 1, opening. Mode 2, shearing this way. And mode 3, which is anti-plane stress. So we'll be focusing our attention on mode 1 loading, just because it's the most common case. But actually, because if we know this case, we can deal with these other two cases, because the theory is exactly the same. Okay, the general architecture of the theory is exactly the same. Plus, there is another big advantage coming from our initial assumption that we are dealing with a linear elastic body. What is the big advantage? The big advantage is that if we can get the solution for this case, for this case, and for this case, and we have a component of subjective mixed mode loading, we can use the superposition principle. And we can use the superposition principle because we are assuming that the mechanical behavior of our material obeys a linear elastic constitutive law. Okay? So, having said that, we can go straight to Irwin's solution. Irwin's solution says that we are dealing with mode 1 loading. We are assuming that initially the gross stress, which is the force divided by the area where the crack is, but determined by disregarding the presence of the crack, is lower than 0.6 the yield stress if you are dealing with a conventional ductile material. And finally, if we are quite close to the tip of our crack. So if all these conditions are assured, what we can say is that the stress field around the tip of our bidimensional crack is described via these formulas, where we can have also the complete solution for the plane stress case and plane strain case. So these are the equations you know. I suppose that you know are quite familiar with Irwin's solution. What is the idea here? What is the clever idea here? Which is a clever idea and it's a terrible idea. The clever idea is that no matter where you are around the point, and the position of your point depends on theta and r, all the stress components are proportional to the same quantity. So even if in theory we have a problem which can be in the simplest situation, plane stress bidimensional, or in the most complex situation that is tridimensional, it's it can have either 2 or 3 stress components which are different from 0, or 3 principal stresses which are different from 0, 2 or 3. Actually, all those quantities depend on one single constant, K1. We know the name of the mother because the name of the mother is Actually, mode 1 stress intensity factor, which is K1. K1 is an animal we like, but K1 is an animal I hate. Look at the dimensions here. What the heck is that? I spent the last 22 years working on fracture mechanics, and still I cannot get my head around that quantity. Megapascal times the square root of meter. Sorry, it's a pressure times the square root of a length. It doesn't mean anything to me. And actually, the real problem is the way these equations were structured. We could have rewritten this equation in a more clever way, coming out with a better definition for our quantity, K1, or for our constant, because it's a proportionality constant, but unfortunately it's too late. We are too used to this definition. But from a physical point of view, don't even try. It doesn't exist a physical meaning for that. But at least when you plug the number in, you can understand what's going on there. It's the magnitude of the stress field around the crack tip, which is proportional to this K1. Okay? So this is the meaning, if you like, if you really need to find a meaning. Okay? So, clearly, if we have a look at these equations, there are some interesting things we can see. For instance, when theta is equal to 0, that is when we are moving along the crack bisector, you look at the terms here, and you see that sigma x becomes equal to sigma y, equal to K1 divided by the square root of 2 times pi 2 times r. Tau x y is equal to 0. So what is good is that, as we were saying, and this is one way to visualize what's going on there, as K1 increases, the magnitude of the local stress fields increases. This is as far as we can go with K1. All the other stories you see or you find around it are just inventions, because everything was based on maths, and this is what they did. Not a clever definition. And for instance, if you look around, there are some theories like gradient elasticity, for instance, where they introduced different concepts and ideas, and rather than, in the end, rather than having K1, everything is reformulated by referring to a length, so at least you have a quantity which is, how can I say, meaningful from a physical point of view. Okay, so actually, if you have any questions or any comments, please don't hesitate to interrupt me. This is okay. So now we know that the main character of our story, and sometimes our pantomime, is K1. So if we can calculate K1, we can define the entire stress field in the vicinity of the crack tip, but actually we don't need to define the entire stress field, because if we know K1, we know that everything is proportional to K1. So that's the idea, and again, if we consider the stress distribution along the notch bisector, we can define K1 this way, and this is the classic with the limit here definition we use to determine K1 from FE models, and this is, you know, a solution of the problem. But actually what we like the most when it comes to engineering applications is this definition, which is the engineering definition for the stress intensity factor, where K1 is equal to alpha, which is the shape factor, times the gross stress, times the square root of pi, times the semi-length of the crack. Okay? So, if you are dealing with a non-conventional component, this is the definition you need to use to calculate your stress intensity factor. And a similar definition applies to the Model 1 case as well as to the Model 3 case. Clearly, you need to use a different stress component, but the idea is the same. And instead, this is the classic definition we use to do very simple calculations using fracture mechanics. Okay, so what's the story here? The story here is that, you know, if you have a conventional geometry, like a plate containing a crack, or a plate in tension containing a lateral crack, or multiple cracks, or whatever, you can find a lot of graphs like these ones, which can be used to define your shape factor alpha. Okay? In the past, the books with all these diagrams, it used to be very difficult to find, and in any case very expensive. But nowadays, I think that the internet is populated with the graphs like this one, so it's very easy to find the stress intensity factors for a lot of geometries. Or in some other cases, we can find the solutions for the analytical solution for very specific cases. Okay, this is the case of a crack, a central crack in a plate. This is the solution due to Feddersen, and this is the solution due to Irwin, the classic solution, or some other polynomial functions like this one, which can be used to estimate the shape factor, for instance, in this case, when you have two little cracks, lateral cracks loaded in tension. There is no real meaning here, because these are just polynomial functions which are used to interpolate results. But question, since you are working with fracture mechanics, what is alpha? Really, why do we need a shape factor? Any idea? Okay, Irwin's theory is based on this configuration, or Griffith's cracked plate, if you like. It's based on the idea that you have a crack, a central crack, in an infinite plate loaded in tension. Okay? And this is, and fracture mechanics is based on that. But when you need to move to other configurations, for instance, when your crack becomes very, very long, so you can no longer assume that your plate is an infinite plate, for instance, you see that you need to correct your value. And the same applies to the other situations, or even more complex when you have a real component. So shape factor, the shape factor here, alpha, is a quantity you use to bring your specific problem back to the case of an infinite plate containing a central crack loaded in tension. Okay? So it's a stratagem we use because when I have a very complex component, I don't know what to do. But when I have a crack in an infinite plate, hey, that's bread and butter. I know I can do whatever I want. So via the shape factor, we bring our problem back to the configuration we know we can handle. An infinite plate with a central crack. Okay? So fracture mechanics overall is a strange theory, because I would say deriving Irwin's equation is laborious but not particularly difficult. It's all about assuming that your reference volume is in equilibrium. It's what we usually do in continuum mechanics. So it's laborious but not difficult. This is the reason why I decided not to go through that procedure. You have very complex formulas which appear complex just because we need polynomial functions to get these quantities, but overall the maths which is behind fracture mechanics is very, very basic. And this is the reason why we can also easily implement fracture mechanics in FE codes, or we can code our own very specific easy solvers. Okay? So that's the idea. So treat the fracture mechanics with respect, but don't be scared. It's just a theory based on a lot of simplifications, and overall the job is bringing back what we are doing, back to the problem of an infinite plate with a central crack, because we all know how to treat that simple case, and this is what we do. Okay? Good. And actually this is doing a little bit of reverse engineering. It also helps when you have a complex component, trying to isolate your cracking process and trying to visualize your cracking process in an environment you know. Mentally, this is really what I do also when I do failure analysis. I try to picture the problem referring to geometries I know very well, like or either the crack in the central crack in a plate or two lateral cracks in a plate. And believe me, in the end, you can really understand a lot by always referring to these simple cases. Okay? Is it clear? Am I killing fractional mechanics? Enough? Am I making it more human? Okay, good. This is the goal. Okay, so static assessment. We have the equations here. Here with this equation, we know that no matter where we are around the crack tip, all the stress components we can calculate are proportional to K1. We know that in engineering terms, we can use this clever formula to calculate K1. So what we do is then, observing that, and you can really see that, if the nominal stress increases, given the geometry and the position of the crack, you have alpha, and also given the length of the crack, clearly K1 increases. But if K1 increases, then also the magnitude of the stress components increases. So clearly the idea is that whatever happens around the crack tip, and we know that we believe in a process zone, so we are interested in understanding what is the process damaging the material in the vicinity of the crack tip. So if that stress field, if K1 increases, the magnitude of that critical stress field increases. Well, so why not then using K1 to directly perform the static assessment? In particular, if we plot our stress field as we did before along the crack bisector, and as we increase the, for instance, the nominal stress, K1 increases. But physically, at a certain point, your stress will reach a critical value. The most complicated experiment ever. That's fracture mechanics overall, isn't it? And actually, this tells us another nice story. Stress concentration phenomenon. You remember talking to your little kid and or brother and explaining to him or sister to her what fracture mechanics is and what the stress concentration phenomenon is? This is it. This is the real complexity of the theory we are dealing with. Okay? So keep it simple, because we love simplicity, and if we keep it simple, we can understand a lot of things. So in practice, the idea is that when our K1 reaches a critical value, then our piece of paper, the component material, fails. So Kc is in fracture mechanics the equivalent of the UTS in continuum mechanics. As simple as that. So if it's true, you read the pages and pages and pages of theories, ASTM suggestions, blah blah blah. They call Kc fracture toughness, but at the end of the day, the design is nothing but being sure that your K1 is lower than Kc. The rest is a lot of blah 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 around this basic idea. Okay, all our respect to boring standard codes or boring recommendations, but at the end of the day, this is the idea. Your K1 must be lower than Kc, otherwise your component will fail. Again, as simple as that. Okay, and clearly, again, you can find zillions of different definitions, but if you divide Kc by the K1 value we're applying, you get your safety factor. Okay, as simple as that. Good. So fracture toughness. So beautiful. We have a perfect theory, a very good theory, dealing with a lot of things. We can visualize it. We know that in the end we need to become familiar with one specific case, a crack at the center of an infinite plate, and if we play with the shape factor, we can do whatever we want. Plus, we can extend this approach to mode 1, mode 3, and superposition principle, we can bring everything together. So, clearly, I'm not surprised that over the last 50, 60 years, fracture mechanics has become such a big, important tool. But where's the problem? The problem is that we design components with something which is not a material property, because the fracture toughness is not a material property. Okay, it depends, we'll see it in a second, on the temperature, no surprise. All the mechanical properties of the materials we know change as the temperature changes. Okay, it can depend on the environment in many different ways. It's different for different materials, but what is really shocking is that Kc depends on the thickness. And this is something really tricky, and this is where, you know, we understand that overall our castle is made of sand. And why is that? Oh, this is my personal interpretation. I think that it's quite accepted as a view. Okay, this is if we plot Kc versus the thickness. First of all, what we see is that, you know, we have a strange behavior here, but basically the fracture toughness decreases as the thickness increases, and at a certain point the fracture toughness becomes constant, and we call that value K1C, which is the plane strain fracture toughness. And according to the pertinent ASTM recommendation, if you have your Kc value and your yield stress, and for brittle materials you can replace the yield stress with the UTS here, and you multiply the square of this ratio times 2.5, and if your thickness is larger than this value, then according to the ISTM recommendations, you are in the plane strain condition. Why is that? Have you got any idea? Okay. Good. Let's try to understand why. Okay. I live in the UK, and one of the things that we do in the UK, and actually I'm British now as well, so one of the things we do, we Brits in this Italian accent do, is basically eating crabby sandwiches. You know, it's terrible. You know, food in the UK is terrible. It really sucks compared to the weather. I mean, it's not, the weather is beautiful. But okay, so, and we eat sandwiches. And some of them are really terrible because you have a slice of bread, a slice of ham, and a slice of bread. Depressing, isn't it? Okay. So, if we start from a British sandwich and we cut two bits laterally, as we did here for the piece of paper before, but this is now the sandwich, and we pull it just a little bit, what would you expect to see? The bread deforming a lot here around the tips of the two cuts. Can you see it? This is what we normally do. Can you picture that? Can you picture that? Why is that? Can you explain that phenomenon using fracture mechanics? I do. Because we start from the surface of the component. According to Irwin's, we can define our local system of coordinates centered at the crack tip, and we are on the surface initially. These are the equations you know. By definition, we are on the surface, so our state of stress must be bidimensional. It's plane stress, it's a surface, because if we had a stress component perpendicular to the surface, our piece of material would move around. Okay, so for sure, the stress state characterizing the surface of my plate is bidimensional. Are you with me? Do you all agree with me? Good. Okay, this means that it's plane stress. This means that according to this definition, the stress along axis Z is equal to 0. Okay? But since we can assume that, as we always do, that our slice of British bread is biaxial, according to Irwin's equation, the state of strain on the surface is triaxial, isn't it? Let me see. Here we are. This is Irwin's generalized equations. If sigma x and sigma y are different from 0, and sigma z is equal to 0. Okay, epsilon z x is different from 0. Epsilon y is different from 0. But also epsilon z is different from 0, because sigma z clearly is 0, but sigma x and sigma y are different from 0. And actually, epsilon z is different from 0 and negative. Okay? So, positive epsilon x, positive epsilon y, negative epsilon z, even if sigma z is equal to 0. So if we go back to our British sandwich here, this means that the stress, the deformation here, parallel to the axis z, is negative. So this is the reason why when you pull the bread, we see that a little valley in the vicinity of the cut. Okay? So it's a triaxial state of stress. You're laughing, right? Because you thought that fracture mechanics is something more elegant and difficult than the crappy sandwich, British sandwich with the crap. This is what we are talking about. Yeah. Okay?
No, basically I will see the British sandwich as more fascinating now, so.
Ah, okay, ooh, good luck. Good luck. You will die for starvation. Anyway, so this is, we can see that now the epsilon z is negative here. This means that the thickness in the vicinity of the crack tip here tends to get smaller and smaller. Okay? So let's move. So here we have a biaxial state of stress. Let's move to the midsection. The equations we know apply in any case. What we need to do is moving to the mid plate here, redefining our local system of coordinates. The red one, it's exactly the one you know, but now we are no longer on the surface, we are considering the mid plane, okay? But the tools we have are these ones, okay? And, but at the same time, put it this way, we have the material pushing this way from the top and pushing that way from the bottom. So you want your crappy British sandwich to be in equilibrium. So this means that the slice of ham at the center of your sandwich does not deform, isn't it? Because the thickness of the bread is the same on the two sides, you are pulling it, the bread is deforming a little bit, and the slice of ham, for sure, because it's in equilibrium, must be straight again. From a physical point of view, being straight means that the deformation is biaxial, so we don't have a vertical movement. But according to Irwin's plane strain, epsilon x equal to, epsilon z equal to 0, means sigma z different from 0. So the state of stress at the midsection is triaxial. So the story is that on the surface, the state of stress is biaxial, and the state of stress instead at the midsection is triaxial. No matter what criterion you use, you can use Tresca, Mises, the first principal strain. We know that, given the magnitude of the stress components, a triaxial state of stress is always more damaging than a biaxial state of stress. Okay, so look at these equations. This is what we can calculate, and these are the stress components we can calculate using K1. But we need to form a further hypothesis in order to tell our model if we are either on the surface or at the midsection. But the model doesn't know anything. It's something we impose on the model externally, onto the model externally. So this is the reason why, in the end, Kc is not really a material property, because here we have plane strain because our plate is so thick that, you know, at the midsection we have a fully developed triaxial state of stress, which is much more damaging than the biaxial state of stress we have on the surface. So overall we need less energy to fracture our plate. Instead, when we go back here, where the thickness is very, very small, in the end, what we have is that the thickness is so small, so the effect of the two surfaces prevail over the effect of the mid section. So we need more energy to fracture our plate because the state of stress really governing the phenomenon is biaxial. And clearly, moving from plane stress down to plane strain, we have a kind of transition region which is very difficult to consider. There are a few papers around, and you can see explaining this approach, where they did very accurate FE stress analysis. And basically what you see is that you need to have a certain amount of material to be able to create a proper triaxial state of stress at the mid section of your plate. Okay? Also, so it's all goes back to the problem of the stress analysis. And actually, it's not Irwin's fault, it's not Griffith's fault, it's in a way our fault, because we forced to, we use the theory outside of its region of validity. But hey, we know it, we can handle it, and if we can determine the proper value for the fracture toughness according to the thickness we are designing, fine. If not, we refer to the plane strain fracture toughness simply because it's the lowest value we can determine from the fracture toughness. We can walk around the obstacle, but the problem is still there. We have a beautiful theory, which is very elegant, where one of the key mechanical properties to design component, the strength, is not a mechanical property. But at the same time, put it this way, we are somehow used to this problem, because when it comes to the conventional UTS, ultimate tensile strength, we know that the size effect and the scale effect is a big issue. It's an unsolved problem. We know that the strength of the components changes as the size of the components themselves vary. So, probably it's something we need to deal with in any case, but it's a very, very extreme in when it comes to fracture mechanics. Okay, so having said that, clearly, as we said, the fracture toughness is different for different materials, no surprise, and also as we were saying, mechanical properties, fracture toughness depends on the temperature. Okay, I will show you a couple of other slides, and after that we can have a short break, and before moving to the fatigue issue very quickly. Okay, it's a theory we love, it's a theory we like, but can we always use fracture mechanics? Because I saw these mistakes being made many, many times. So this is the definition we know for K1, and according to fracture mechanics, failure takes place as soon as K1 becomes equal to Kc. So, if we go back to the definition, we can say that there exists a value for the nominal gross stress, and we call it sigma f, given that crack and that shape factor, that makes K1, starting from this definition, equal to Kc. So basically, you can read this formula given a type of loading and the length of the crack and the geometrical configuration, like I derive this formula by finding that value sigma f for the gross stress that makes K1 equal to Kc. Okay, this is another way to apply or to see the fracture mechanics problem. Okay, good. So if it's true, and if we accept this formula, clearly we can simply rearrange that equation, and we could say, according to fracture mechanics, my plate fails as soon as the nominal stress becomes equal to sigma f, where sigma f is Kc divided by alpha, the square root of pi times a. Okay? So it's simply fracture mechanics revisited from a nominal stress perspective. Okay, I'm saying exactly the same things here. When K1 is equal to Kc, my plate breaks. If I use this formula for K1, this means that K1 must be equal to Kc. This means that K1 can be equal to Kc given my geometry and configuration only when sigma is equal to a certain Fidor value. By rearranging this equation, I can derive directly this quantity. So it's fracture mechanics told from the nominal stress angle or perspective. Okay, so okay, what is the point here of the exercise in that I got rid of it? The problem here is that clearly, if now you use this formula, and for instance you assume, let's make it very easy, we have an infinite plate, so alpha is invariably equal to 1, we go back to the case we know, and now you make your crack smaller and smaller and smaller and smaller. So if A becomes smaller and smaller, the failure stress becomes larger and larger. And when the crack is very small, like a defect, according to this formula, your sigma f could become larger than the UTS. Or, according to fracture mechanics, when your defect is equal to 0, the strength is equal to infinity, isn't it? Does it make any sense? No. So you must be careful, because when you need to understand where you are, because real materials contain defects, small cracks, and it's very easy to fall into the trap and start thinking, yeah, I want to use fracture mechanics because I see these defects, which is not true. You might be in the regime where actually, even if you are the defects there, fracture mechanics would give you a non-conservative estimate. Okay? So be careful, because also this length can be very large. Cast iron, classic material. Big spheres, very poor cast iron. You must have cracks which are larger than 8 millimeters sometimes to be able to have a crack which can be managed by using fracture mechanics. Okay? So the message is, don't fall in love with this theory too much, because there are a lot of limitations. And always check if your theory can be used, because very often you see a defect and actually the defect is so small that you can keep addressing your problem using continuum mechanics. Okay? Does it make any sense? Good. The last interesting aspect is this one. So, assume that you have two plates, and we have two infinite plates, so for both alpha, the shape factor is invariably equal to 1. For the first plate, the crack length is 2 times little a. We have a second plate where the crack length is 2 times capital A, which is 4 times 2 little a. So it's 4 times bigger than the previous crack. Okay? Good. So if we believe in the local approach, we would say that, both plates fail as soon as our local K1 becomes equal to Kc. Of course, the basic assumption is that these two plates are made of the same material and they have the same thickness. So this is what fracture mechanics say. Good. Okay, so if it's true, we can say that sigma F1 then is the nominal gross stress resulting in static break of our plate, 1 having length of the crack equal to 2 times little a. And sigma F2 instead is the length of is the stress resulting in the breakage of plate 2. We do our calculations. This is Kc for plate 1. So Kc, clearly, when this condition is assured, is sigma F1 times pi times A. It's the semi-length here. But since the two plates fail under the same value of Kc, Kc must be also equal to sigma F2 times the square root of pi times 4A, simply because this is 4 times A. So I keep playing with my equations, and I would end up having that, in theory, I would say that The small plate is much, much stronger than the bigger plate in terms of nominal stresses. Why is that? It's simply because of the way the theory works. And this tells us something which is beautiful in a way. Because, and this tells you a lot about the mechanical behavior of materials. This is, it's in theory, the nominal stress here is not, it's in practice, the nominal stress is larger in case one, the failure nominal stress is larger for case 1 than for case 2. It's because this is what you need to be able to reach locally the same failure condition. This tells you that failures are something very, very local. Very, very local, no matter the size of the component. You can have something which is very big, and if you do all your calculations, you could end up, in terms of nominal quantities, with something which is a little bit strange, like this one. It takes a little bit to get your head around, but it's simply based on the maths, so nothing difficult. But what this calculation says is that actually be careful, because no matter the size of your component, structural integrity depends on something which is very, very local. And in fact, in terms of local stresses, we can see something which is on local quantities. We can see something we believe in. Let's say, as soon as the material around your critical region reaches a critical configuration, my component fails. We believe in that. But it's much more difficult to say, actually, the small component is stronger than the bigger component. Why is that? I'm using the same material. Actually, it's not true. It's simply because we are tackling the problem from the wrong angle. Because locally, the two components are equally strong, as we would expect. Okay, so again, be careful when you're playing with fracture mechanics, because you can find this kind of strange glitches in the theory. But it is simply due to the way we play with the math. Reality is this one. Fracture mechanics is not the perfect theory to explain that, but fracture mechanics is based on the most powerful design concept we have. Local quantities, local strength, okay? And this is what really governs the overall strength of our components and structures. Okay, so having said that, we can take a short break before we start talking about fatigue. Okay? Fatigue. Okay, so I'm going to talk about fatigue, giving to you just 45 minutes, so it's not too short to talk about complex materials, but we'll be talking about homogeneous and isotropic materials subjected to fatigue, just to give you the general idea. In the end, you know, with adjusting a little bit the theory, clearly you can use this idea also to deal with other materials, in particular with composites. Right now, for instance, personally, I'm using fracture mechanics and fatigue to deal with 3D printed polymers. 3D printed materials are clearly very popular right now, and it's an area where, you know, we can really reuse fracture mechanics. If I'm not a big fan of 3D printed materials, but hey, here we are. So, what is fatigue? We have a plate loaded in cyclic tension, and at a certain point, even if we see no real evident plasticity, we have a crack initiating and then propagating. Okay? So let's try to avoid the very first big misunderstanding. When we talk about fracture mechanics and fatigue, we don't talk about this phase when you see no cracks and at a certain point the crack initiates. In order to be able to use fracture mechanics to model the cracking behavior of metals, or in general terms of engineering materials under fatigue loading, you must have what we call a long crack. Okay? What is a long crack from a physical point of view? Okay, look at the shape of the crack here. clearly is a zigzag crack. It's really away from being a straight line. As we were saying before, actually, we can start talking about a straight crack if we really observe our problem from a proper distance. And the proper distance is having the effect of the local microstructure disappearing. For instance, in steel, you can forget about grains, you can forget about grain boundaries, you can forget about the local dishomogeneities you have. And you are really dealing with a material which is homogeneous and isotropic. Okay? So you need, and to reach properly that condition, you need a crack which is quite long. Okay? It depends on the application, it depends on where you are, but it must be a quite long crack. You know, if you have a very high strength steel, clearly we can talk about a crack which is equal to 0.5 millimeters, but if you are dealing with a cast iron, it could be also a couple of millimeters, 3, 4, 5 millimeters. Okay, so we need to have long cracks. So this is fatigue, but actually fatigue and propagation is a quite complex problem, because if we see the same problem from another angle, you'll see here at the midsection of the plate, you'll see a little white spot appearing initially, cycle by cycle. Here we have this white spot appearing, and after a little while you see that that is the crack initiation point propagating toward the two surfaces. You can see here the part of the crack being already appearing. Now the crack is moving toward the surface, and now the crack is eventually on the surface. And in general, what we see or we model is this propagation, but as you can see, this final propagation, now you can clearly see the crack here. This final propagation is the result of a very complex and initiation process. But now you should also be able to give yourself an answer. Why does this crack initiate here and not on the surface? Okay, it's a notch, it's not a crack. But now you can do the local stress analysis, and what would you expect to have here at the center of this plate? A kind of triaxial state of stress, or at least more triaxial than the stress you have on the surface. So physically, what the material feels is locally this state of stress which is more triaxial than the one you have on the surface. So you end up having your crack initiation happening at the midsection here of the plate. Okay? So hopefully I'm trying to deliver the big message. And please keep it in mind over the next 2 days. We model reality. We don't invent the maths hoping that the maths we like describes something. Okay? And in general, to have a rough idea about what's going on, there are very rough idea. We don't need a very complicated models. Okay? So don't fall in love with the maths, because we are interested in the phenomena. We are not interested in the modeling, or we are clearly interested in the modeling, but our modeling must be somehow linked to the reality we are interested in. Okay, I'm sure that you all know Umberto Eco. And when he talks about models and reality, he says that we must be very careful, because we might end up going to the restaurant and eating the menu. Because the menu is the model describing the dinner. But we are interested in the dinner, and we are not interested in the menu. So we need to use the menu properly to choose our dinner, and not using our menu as the dinner itself. Okay? And this is a very clever way to say, be careful, we love models because they are very useful. The menu can help you out to choose what you want to eat, but you are interested in the food, not in the menu as such. Okay? And this is what we are trying to do from now onward. Okay? Using fraction mechanics to model the fatigue behavior. Okay? So, basic definitions in fatigue. Clearly, and when we deal with the most simple case, we have 45 minutes, so we are just talking about the constant amplitude case and not the variable amplitude case, which is a completely different story. I would need a week to explore that problem. But when we deal with the constant amplitude problems, clearly the stresses we use to analyze our problems, still the nominal stresses, can be characterized by a maximum value in the cycle and a minimum value in the cycle. Accordingly, if the max and min values are known, we can calculate the amplitude, max minus mean divided by 2, the range, which is max minus mean, and is equal to 2 times the amplitude, the mean value, and finally the load ratio, which is the minimum stress divided by the maximum stress. If you look at this definition, for instance, an R value equal to -1 means fully reversed. This means that the mean stress is invariably equal to 0. Okay? So, and this is a quantity we use in classic fatigue, but we also use this load ratio to describe the mean stress effect in the presence of longer cracks. Okay? So, if we go back to Irwin's plate, clearly now we can rewrite the equations we know in a different way. And actually what we usually do is expressing the problem in terms of ranges. So what we do is expressing K1 as the range of the stress intensity factor, and accordingly the stress components we can calculate via delta K1 are ranges. Okay? This is what we usually do. But de facto, this is what we already know. Okay? We simply give a time variable meaning to these quantities, but nothing really changes. Okay? Again, we can talk about plane stress, and again, we can talk about plane strain. Exactly the same problem as the one we have under static loading. And delta K is called mod 1 stress intensity factor range. Again, these weird units, unfortunately. Okay, so clearly, when we use the engineering definition we know for the stress intensity factor, if we use the maximum nominal stress in the cycle, we can accordingly define K1 max. In a similar way, if we use the minimum value in the cycle, we can define K1 min. And the range of the threshold value of the stress intensity factor, the one we use to calculate the stresses from Irwin's equation, becomes equal to K1 max minus K1 min, which is clearly alpha times delta sigma g, which is the range of the nominal gross stress, times the square root of pi times A. So we do our calculations again in terms of ranges. And the load ratio is defined as K1 min divided by K1 max, and if you play with these two definitions, it's easy to see that it's nothing but the minimum value of the nominal stress divided by the maximum value of the nominal stress. So we go back to the usual definitions we like when it comes to conventional continuum mechanics fatigue. Okay, now let's assume that we have our plate with a crack, and as we saw from the two short videos, we know that cycle by cycle, under the applied cyclic loading, our crack becomes longer and longer, so the crack propagates. Why is that? Oh, that's a very fascinating question. It depends on your material and depends on your application. And my suggestion is have a look at the microscopic processes happening at the crack tip to better understand what's going on with your material. But put it this way, we take it for granted. In a way, yeah, I have a crack, I apply the cyclic loading, and the crack propagates. But it's not so easy to answer the most basic question, why? Why does a crack propagate? And also the other side of the coin is that why do cracks sometimes arrest themselves? Why do they stop propagating? So it's another interesting and clever question you should always ask yourself when modeling this phenomenon. Okay, anyway, if our crack propagates under the applied cyclic loading, we can easily build up a graph where we plot the crack length against the number of cycles here. Please note that it's the number of cycles, not the number of cycles to failure. Okay? So we are not talking about failure yet. We are talking about a crack propagating. I apply 10 cycles and the crack increases its length by 2 millimeters. Okay? it could not be failure yet. And now we consider two cases. The first case, the initial length is the same. The threshold, the range of the nominal stress for case A is larger than the range of the nominal stress for case B. And this is the way the crack propagates. And the crack keeps going, and at a certain point the two cracks will be so long that our plate fails statically under the maximum applied force. Okay, so first of all, we see something very interesting. You know, the larger the force, the faster the propagation. And this is common for all the materials. The larger the force, the lower the length at which your component fails. Why is that? Any idea? Okay, if you want, fatigue doesn't exist. Fatigue is a propagation problem, but we don't have a real fatigue failure. Why is that? Because even if you have a cylinder and you initiate a crack, the crack propagates under your cyclic loading, a shaft, and at a certain point, the maximum force in the cycle is large enough to break your component statically under the maximum force. So, technically speaking, a fatigue failure doesn't exist as such. It exists a propagation under fatigue loading. Okay? And clearly, if the delta sigma A is larger than delta sigma B, this means that the maximum force characterizing this cycle is larger than the force characterizing this cycle. And if you think about the definition for K1, which is proportional to the nominal stress, this means that the maximum K1 in this case is much larger than the maximum K1 in this case. This means that we need a shorter crack, or in this case we need a longer crack to be able to reach the critical condition locally. Okay? It's all there, all in the maths. The most important thing here is that at any point of our curve we can define the tangent line, and the slope of the tangent line is dA, which is the length of the crack, divided by dN, and this is what we call the crack growth rate. Okay? Flat means no propagation, vertical means fast fracture, in between fatigue. Okay? That's it. This is where we are. If this is clear, we can then plot our results in a crack growth rate versus stress intensity range graph. And if we did that for our material, we would get results like this one, where the curves we know have got this kind of common standard profile, an inclined straight line here, and a kind of vertical asymptotic line here. Here again, you should know all the definitions, because the stress intensity range delta K is defined this way. This is the usual formula we use for fracture mechanics, and this is the crack growth rate, dA over dN, which is the slope of the crack growth curve. So this diagram means that as the stress intensity factor increases, since the trend is this way, the crack growth rate increases, which at least makes very sense from a physical point of view. Okay, let's try to understand better the meaning of this diagram. So this is what we call Paris diagram. It was developed by Paris. The story I've heard from him is that basically he died a couple of years ago actually, and the story I heard from him is that he was dealing with this problem. He was approaching the end of his PhD. He was running out of money, which is very normal. So he had this bunch of data, and he tried to plot this data in a certain way. And by plotting the data, actually it was the other way around, but with this idea in mind, things started coming together. So there were two elements, according to the story I heard: being in the field and investigating that problem on one side, and on the other side, being at the end of the scholarship and being about to run out of money, which is story, which is very, very common, especially in the Anglo-Saxon world. Okay, so this is the schematic way of plotting the diagram. We have three regions. Region 1, which is delimited more or less by this vertical asymptotic line. We have a central region, region 2, where we have an inclined line, and since this is a log representation, a straight line in a log diagram is a power law. So our power law can be expressed as dN over dA is equal to C, which is a constant, a material fatigue constant, times delta K1, which is the stress intensity factor range, to the power of M. M is the slope of this line. Okay? And when it comes to metals, if you want to get a reference value for M, I would say 3. And we have a third region, which is more or less delimited by this vertical line, where we have basically the fast fracture of our component. So how can we use then this diagram in situations of practical interest? Actually, it's quite useful, not very useful, but quite useful. So we can say that, first of all, we don't have to forget that given a material, the shape and characteristics of this graph and the position of the different lines depend on environment, the characteristics of the material, and what I'm saying that microstructural features here is that, you know, if you get a piece of steel and for instance you heat treat your material in order to change the grain size, so technically speaking the designation of your material is still the same, but the microstructural features are different because, for instance, you get bigger grains, and the fact that you have bigger grains can affect the position of the different lines in your graph. So be careful, because sometimes what we do is picking up these graphs from the literature just because we see a similar material to the one we are interested in. But actually it's always very tricky, because even having a grain size which is slightly different from the grain size characterizing your material can result in a quite slightly different Pyrus curve. Again, we have the problem of the thickness, still dealing with fracture mechanics, but if we are in region 1 we can forget about the thickness, and the importance of the thickness increases as we move from region 1 to region 3. Again, another important aspect is the load ratio. Be careful, because the mean stress effect in fatigue is always a big issue. But anyway, assuming that we know all these things, how can we use this graph in situations of practical interest? Easy peasy. So let's focus our attention on region 1. Okay, we have this kind of line, and it's represented here, where here it's called, it's an old graph taken from a nice paper written by Keith Miller, and he used to call it a crack speed, because this is just an idea about the way cracks propagate. So what does this diagram say? This diagram says that in theory, if your delta K, the delta K you apply is lower than delta KTH, which is the threshold value of the stress intensity factor range, if you look at the crack growth rate, here it's very low. Be careful, this is a log diagram, so here it cannot be 0. This means that the crack propagation is different from 0, but so small that from an engineering point of view it can be neglected. And we have, in theory, no engineering propagation. But actually, if you look at the crack in this region, you would see that the crack growth, or the crack speed, follows a kind of zigzag path as the crack length increases. And why is that? Because still we are in a region where the crack is so small that the material morphology affects the crack propagation rate. So here you see, for instance, in metals, this zigzag path. It's because the crack has to run through the grain boundaries. And as we know, the grain boundaries are stronger than the grains. So you have a crack propagating very quickly when running through the grain and stopping at the grain boundary. So the the crack growth rate decreases. And again, if we keep putting energy into the system, at a certain point our crack will be able to break through the grain boundary, running again very quickly through the grain and stopping again. But you see this zigzag path, and so we have a crack propagation. So again, it's consistent with the fact that dA over dN here in this diagram cannot be zero. But it's so affected by the crack, by the material morphology, that fracture mechanics, as we know it, is not a good theory to model it. Because don't forget that our fundamental assumption is that we have a linear elastic material, homogeneous and isotropic, at least to use this formula. Here, the morphology plays a very important role. But in any case, the crack growth rate is so small that when we are in this region, we can say that the propagation is there, very small, but it cannot be measured using these tools. And this brings us back to another problem, which is inspections. You know? What engineers do when it comes to real components is every now and then inspecting real structures, and they see a crack, and the calculation they do is to check if they are still in this region. If they are still in this region, they say, okay, I know that the crack is there, we'll keep monitoring. We know that the crack is propagating very, very slowly, but still with this diagram we cannot predict the crack growth rate. What they do is keeping monitoring the crack until delta K for that crack becomes equal to more or less delta KTH, because they know that from that moment onwards they would enter region 2. So if you see a crack in a component and the associated delta K1 value is in this region, you can say that for the time being, of course, you want to keep monitoring the crack, but from an engineering point of view, that propagation is so slow that can be neglected. We know that sooner or later it's going to happen something, but still we are feeling good. Okay? So in terms of design, if we say that our delta K1 is lower than delta KTH, we are here, according to Paris schematization, we can say that our crack is not really propagating. Okay? We know that is not true, but this is the consistent answer. Okay, still we inspect our component, we know the shape factor for our crack, and one day we discover that our crack results in a delta K1 which is larger than delta KTH, so we are well within region 2. So in that case we want to know the crack growth rate, or how many cycles we need to make the crack propagate up to a certain length, for instance. Cycles can be days. I don't know, if I have a chemical process and I need 1,000 cycles a day, and my crack needs 10,000 cycles to propagate, I would say, ooh, I can work for another 10 days and that's it. So it depends on what are your units, but in the end it's the lifetime you want to measure, and it depends on your specific application. This part of the diagram, region 2, is very much affected by environment, microstructural feature, thickness and load ratio. In this equation, as we were saying, C and M are material fatigue properties. Okay? We are dealing with the metals, but for instance, you can find similar graphs also for composites materials. It's very difficult because in that case you really need to give a lot of details about the way you were running your experiments, the orientation of the fibers, and blah blah blah. But overall, they tend to summarize the story very often using this simple power law. So nothing nothing else to say. If we can calculate delta K1 and C and M are known, we can estimate the crack growth rate. This is an information we can play with in order to make, for instance, further assumptions. Finally, now the question is, how do we use this information? Because we have this formula, but as it is of little interest unless we play an interesting game. So if we define little n as the number of cycles to failure and nf the number of cycles to failure, which can be, you know, the number of cycles you need to reach a critical configuration. It couldn't be like just, you know, the complete failure of your component. You could say up to this point my component is safe. After that I don't want to risk, or it's too risky for me. So it's a failure in general terms, okay? So when your component is no longer usable, it doesn't mean that your component must be completely broken. And if we have a crack, initial crack having length AI, and we assume that AF is the final crack length, that is, for instance, in this case, is the length of the crack resulting in static breakage under K1 max, what we can do is stating the obvious. It's the only model I know in my life, or I know in engineering, where you get something useful by stating the obvious. The obvious is simply saying that if I want to calculate the number of cycles to failure here, I consider all the cycles that take me from 0 to the number of cycles to failure. It's trivial and it's absolutely stupid, but if you start stating the obvious, you can say, okay, now I multiply this quantity by dA, which is the crack increment, and I divide this quantity by dA. So you can do it because it's 1, the ratio is 1. But this allows you to rearrange your quantities here by changing variables. So you can say, since if my number of cycles, when my number of cycles ranges from 0 to NF, clearly the length of the crack must change from AI to AF. Now I can rewrite my quantity this way, and my new independent variable is dA and no longer dN, so I change the variable. I can do it because the boundary conditions are consistent here. Here I'm tackling the problem in terms of number of cycles, and here I'm tackling the problem in terms of crack length. But AF corresponds to NF and AI corresponds to 0 in this schematization. So there is a perfect consistency between these two terms. But if we focus now our attention on this term, we can use Paris equations here to express dA over dN, which is C times delta K1 to the power of M. So now we have this final equation where delta K1 is the usual formula we use, is the engineering definition for delta K1. It's alpha times delta sigma G times the square root of pi times A. Okay, let's have a look at this formula, which is not easy to integrate, by hand. It's very easy to be integrated by using MATLAB or MATCAD nowadays, but when this formula came out many years ago, it's around the 60s, it wasn't so easy to manage. And now let's play with this formula a little bit. So let's make an initial assumption. Let's say that alpha is constant. We know that is not true because the shape factor given a component changes as the length of the crack varies. So it's a very, very restrictive hypothesis, but let's play with the mass for the time being, and let's form this simple hypothesis, and we can see how can we sort out this problem at the very end of the process. So if we assume that alpha is constant, and we know that C and M are material fatigue constants, these are the constants we find in the Paris equation. We know that delta sigma G is constant because it's the range of the nominal stress, and we are dealing with a constant amplitude problem. We say we are not treating variable amplitude fatigue here. So C, M, delta G are constant. According to this assumption, also alpha is constant, so pi is by definition a constant. So we can get rid of all the constant quantities, knowing that alpha there is something very, very, cheeky to do, because we know that alpha changes a lot. But if we do so, we end up with this very simple term to integrate. So it can be integrated by hand, and this is the final formula we get, which is valid if alpha is constant. you might have certain cases where the component is so big that the variation of alpha is so small that you can assume that alpha is constant. But actually, it's not, or it's in general, it's not the case. So one trick we can use to sort out the problem is simply assuming that if this is the way the shape factor changes as the crack length increases, we can subdivide our propagation range into a number of sub-intervals for which alpha can be assumed almost constant. So what we do is calculating the number, we use this formula and we calculate the number of cycles we need to move from the beginning of an interval to the end of the next interval. After that, we change the shape factor, and we calculate the number of cycles we need to move from the beginning of the second interval to the end of the second interval, and so on. Clearly, we are introducing an approximation, but we are considering a number of sub-cases for which alpha can be somehow assumed to be constant. If we know the number of cycles to move from the beginning to the end of any intervals, in the end we can calculate the number of cycles to failure by putting together the contributions coming from all the intervals we use to define, to schematize our problem. Job done. It's very useful. You can do your calculations by hand. But actually, nowadays, really, this is no longer an issue because we can easily integrate this equation numerically by taking into account the fact that alpha changes. Okay? But this is just a very good way, if you are not already familiar with this equation, to play a little bit and to get familiar and to understand how things change in terms of shape factor, crack length, the mutual interactions amongst the different variables. So it's an educational tool, and it's also to show you what the people used to do in the past. Nowadays, clearly, a conventional computer and a simple code are enough to solve this problem. And finally, we can move to the third region, where basically what we have is that this region clearly doesn't exist. Why is that? Because as the crack increases, clearly the crack growth rate increases and delta K increases. So if we start from here and we keep propagating the crack in the Paris region, we move along this line vertically. At a certain point, K1 max, the maximum stress intensity factor value in the cycle, becomes equal to Kc. So basically what you have is a fast fraction under the maximum applied loading. This is the reason why here you have this vertical line. So basically this is the static assessment. But if we want to put everything together in a consistent way in this diagram, what we need to do is a very simple calculation. We know that by definition delta K1 is K1 max minus K1 min. We know that the lower ratio is also K1 min divided by K1 max. This means that K1 min is equal to R times K1 max. According to this definition, then K delta K1 can be also expressed as K1 max times 1 minus R. So we can say that K1 max become, or if we can say that when K1 max is equal to Kc, delta K1 is equal to Kc. This means that we can calculate delta Kc, which is this value here, which is the range of the stress intensity factor, resulting in a maximum value for K1 equal to Kc. Static breakage is the end of the story, and we go back to the first part of this chat about fracture mechanics, because here this is the static region. Here you have delta K1c. Okay? Here we are. Any questions, comments? I'd like to talk about fracture mechanics. Exhausted. Okay, any questions, comments? sharing your experience with fracture mechanics, particular problems. Was everything clear enough? Hopefully taking you gently into what we are going to do over the next couple of days. This is it. Enjoy your coffee then. I think that I talked to Francesco, and basically as you said at the beginning, you can go to the bar directly with the small tickets and you can enjoy your coffee. Okay, so I'll see you around, and if you have any questions later or whenever during the conference, just please ask. Thank you guys.
I will start the second section of today about this summer school of IGF regarding fracture mechanics, or introduction to fracture mechanics. I want first to introduce a bit the background. So I belong to the IGF group from 2003 and 4. So I started to attend this kind of conference very far away. And I think that, as I said before, it's very difficult to learn something in only 3 days or to understand all fracture mechanics in 3 days. But I think the most important aim of this summer school is to meet each other, and actually you are meeting people that are making PhD or postdoc in the same period. And actually when I start I made the same, and now I have colleagues and friends that are friends for many years, because I met them 50 years ago in the same environment where you are now. And I think this is the most useful part of this summer school. I want also to say that we have divided the summer school in 2 main parts. The first day is more an introduction to fracture mechanics, because actually we have people coming from different backgrounds and different parts of the world with different schools. And tomorrow and the day after, you will have a very good and advanced presentation by top researcher in Europe. One is Rainer Pippan, that is almost a top researcher in material science, one of the best in the world, probably for me is the best in the world in the topic that he's developing. And René de Borst, that is also a top researcher in numerical methods, and one of the best in the world, people that have written the most important books on the topics, and that have achieved almost the most important awards in their subjects. So this is the background. So I'm Filippo Berto. I'm Italian, but I'm working in Norway since 2016. So I'm here like a foreigner, but actually I'm Italian, and I belonging to this Gruppo Italiano Frattura since a long time. So the reason of the aim of my lecture will be introduction to fracture mechanics and notch mechanics. So we will add a step to what you have seen before. We will also recall a bit what you have seen before in the previous lecture by Luca, that made the introduction to the stress intensity factor in this kind of approaches. I want to start from there. I think to repeat a bit is useful, and after that I will move forward with the notch mechanics. I will also touch some quite a new topic, that is three-dimensional effects in notch and fracture mechanics. And I will also show some local criteria for fatigue and fracture assessment at the end of the presentation. So I will show you later these kind of things. And I want also to say that I prepare a very huge quantity of material. I provide to you almost 500 slides. Of course, I will not make all the slides today, but I think what I learned attending the summer school like you is that the most important thing at the end of the summer school is the material that you are taking back to your own institution. Because actually, if you have a good material, it's impossible to catch everything from the presentation of one day. But if you take home very good material that is prepared for you, you can learn a lot, because you have references that are updated, you have documentation that you can use, and so I think this is the most important thing. I want also to add that I add some, when you present something and you work for many years on a topic, you feel part of this topic, and you also tell a story that belongs to you. So I also have I have put in this presentation also my view that can be also wrong in some parts. So you have to accept my view, and if you don't agree, or you have to disagree with me in any case. So, but of course, it's a personal presentation and always have some drawbacks or advantages according to the person that is presenting. That is not neutral, or I put a lot of effort in this work for many years. I work mainly in academia since 2003, almost days and nights. So actually my view of this is quite personal, and of course it cannot be the same that you have. So as I said, I come from NTNU, where I have a position as international chair of fatigue and fracture mechanics. I work in different topics, fatigue and fracture of traditional advanced material. Nowadays I'm mainly focused on additive materials, but also I still maintain my previous topic on weldments, ball connection, and structural integrity of complex structure, including multi-axial fatigue loading. I come from the University of Padua. I like to mention this because it's always important to remember our own history. I think I'm strongly in debt with my previous university, and I strongly believe that Italian academia is very strong, and this is the reason because I'm here. Of course, the financial support is not the same that I have in Norway, but I think it's nice to remember one of the oldest universities of the world. Padua actually is the second oldest university of the world after Bologna, which is still in Italy, and before Oxford and Cambridge that came later. Okay? So and actually it's very famous because Galileo was teaching there for many years, was professor in Padua, and still we have the desk of Galileo in Padua. So I'm proud to belong to this institution, and I'm proud to work also to be professor there for 50 years actually. This is the desk of Galileo in the main building in Padua. Actually, University of Padua is quite famous because also we got the first lady that was able to graduate at the master level. So she was a girl, and she was the first girl that was able to take a master degree in medicine. And it is quite famous for the anatomic theater that was one of the first in the world, and for the botanic garden that after that was copied actually by Oxford and Cambridge, that repeat the same garden there, and now is more famous than Padua. I'm now living in Trondheim, and the change is quite different. It's not due only to the weather, because the winter is quite tough. People are quite cold, and the cost of life is very high. The food is very bad. So it's not only for that. It's a big change of life because you completely move outside your comfort zone. So in Italy we have a lot of habits, so we try to be very repetitive in our habits. We take the coffee at the same time, in the same place, with the same people every day. So you change completely your life, you move, and you try to start a new adventure or a new career in a different place, which is a big challenge that you don't know how it will be. Actually, NTNU is the most important university, or at least the most important technical university in Norway. We have 40,000 students, and we have 3,000 professors there in Glossager. It was established in 1932 with the name NTH, and after that the name was changed in 1996 in NTNU. It was at the beginning only an engineering faculty, but now we have different faculties, also medicine and other faculties. Actually, NTNU is placed in different cities in Norway. We are in Trondheim, we have the main headquarters of NTNU, but actually we have a very strong additive manufacturing center in Gjevik, and we have other economic school in Ålesund, so in other cities. The city is quite nice and quite small. NTNU is quite famous because we got a series of Nobel Prize that is quite unusual for Scandinavian university, because usually they give the Nobel Prize to people coming from MIT, Caltech, or Harvard. So NTNU is quite strong in this regard, And actually the last Nobel Prize was in 2014. We got the Nobel Prize in medicine. And actually the two winners are reporting the slide. They are two husband and wife, so they work together in the Medicine Center for Brain, and they won the Nobel Prize for a study on Parkinson's disease. And we also guessed the last festival where Stephen Hawking was still alive, so he participated in Trondheim in 2017, and we give the first Stephen Hawking medal that is reported here. So NTNU is quite international. We have a lot of connections with the different universities. It's mainly due to the English language, because all Norwegians speak very fluently English. We have courses at the master level all in English, so I think this is the main reason. Actually, we have a very strong infrastructure, especially in engineering. We have the biggest marine lab in the world, which is 380 meters long and can generate waves of different length to study offshore structure in full scale and also naval structure in full scale. And after that, we have a strong group working in full scale testing, especially in impact loading. This is the biggest machine in the world making impact loading. So the most important industry, BMW, Mercedes, and other important industries are coming in NTNU for making tests. And after that, of course, we have a quite new fatigue lab that was established when I arrived in Trondheim, and for which I'm putting all my efforts now for developing this topic in Norway. So actually, what we are trying to do is to create a way for monitoring the fatigue propagation of cracks with different techniques, infrared camera, acoustic emission, and high-speed imaging. I will speak more about this technique later. So the idea is to be able to model or to be able to capture what is happening to the crack when it's growing at different scale. So actually today we will discuss about linear fracture mechanics, but what it is very important to know is that also if the crack seems macroscopically behave linearly elastic, at the microscopic level you always have some small plasticity occurring. So it depends in which scale you are looking to your material. And this will be very clear tomorrow when Rainer Pippa will present to you which are the challenges of applying fracture mechanics or traditional fracture mechanics to micro components. This is a very important point. I think nowadays, and I will discuss this later, the scale effect in time and also in shape and in dimension is very important to take into consideration. We cannot neglect these effects if we want really to design something, especially with new materials. So in NTNU we have a very important nano lab, which is probably the second biggest in the world after Stanford. And we have a very, very nice TM center where we can actually go to the atomic scale to see what is happening, for example, to a bonding line in a welding joint. So this is, for example, a bonding line between aluminum and steel with a scale of 5 nanometer. So this is quite impressive what you can look and what you can see now. And I think Rainer Pippa will show to you tomorrow a lot of these results because I have just seen his presentation. And my research group, I think half of the PhD are here in this summer school. But actually I have almost 10 PhD under my direct supervision, other PhD that are co-supervised, and we have a turnover of 30-40 master students per year coming as Erasmus or internal master students. So actually the size of the group is around 40-50 people every year, which is quite good. So today I will try to make a bit of history of fracture mechanics, introduce a bit linear elastic fracture mechanics, after that move to notch mechanics. That is probably a topic where I can give you the most important contribution because I work mainly on that topic, and it is a very special topic where few people are working still now. And after that I want to discuss some advanced topics that are close to what we are doing now in research that can be useful for your PhD if you are working similar topics. So this is a bit the plan. Actually, I want to start from a picture, so I'm very happy to have this picture, which is almost the original picture. Fracture mechanics was born in 1960 in Lehigh University, which is a university in US, which was quite famous because contemporary many people worked there, and they were the top researcher in fracture mechanics. People that after few years of research changed completely the perspective in designing components in presence of cracks. So this is the group of people that was present there. And actually, I put these lights. It's difficult to see, but in this picture are present Jim Rice, that was the person that actually introduced first in 1968 J integral. George Irwin, that was the founder of this group, that was the person that developed the stress field equation that you have seen in the previous presentation. You have Hutchinson, that was the person that studied the elastic plastic mechanic field in fracture mechanics. And after that, many others that contribute a lot to the topic. And finally, you have Paul Paris, that was considered actually the most important researcher dealing with the fatigue crack growth propagation due to the Paris law. And when he discovered the Paris law in 1962, from that moment he didn't pay any more a ticket for flying, because actually US provided him a life contract for taking flights forever, because actually this was the award for discovering the Paris law. And actually Paris was here in the last conference that he attended in 2016 in Catania, where he also got an award, and after that he died in 2018 at the age of 91. If we want to discuss the really starting point of fracture mechanics, I think that group of people in Lehigh was actually pushed a lot by different problems that happened during those years due to failure, and so they developed some criteria for fracture prediction. But if you go back in the history, I think the first real contribution in fracture mechanics is due to Arnold Griffith. That was a very famous professor that developed an energy criterion that became after that very famous, and that was applied by the researcher in Lehigh for building up the basis of fracture mechanics. And of course, I have just mentioned before, the most important contributor of this fracture mechanics development was Irving, and actually Irving worked as chief in fracture mechanics in Lehigh, and of course he has as teaching assistant Rice, George C, that was very famous on the mixed mode, Hutchinson, that was very famous in plasticity, and Paul Paris, all together. They resist there only 3 or 4 years, because after that they start to fight for the fraternity of the thing that they discovered. So after that, one moved to another university, the other moved to another university, and so they actually spread around the US. That was also good, because they spread around the knowledge that they create in Lehigh. But of course, they start a very strong competition between different groups, as always happens when people are very, very skilled. So I also take the occasion to find out the first house of I made a kind of historical research. This is the first house of Irving in Lehigh, and actually this is also the occasion for remembering this book, that is the history of fracture mechanics, that you can probably find in your library. It costs a lot if you want to buy in Amazon. It costs more than 300 euro. But actually it's reporting all the real history about fracture mechanics and all the steps that have almost have been almost taken for developing fracture mechanics during the years. Of course, as I mentioned before, if you consider the part related to fatigue, I think Paul Paris was the person that we have to refer, and he worked together with another great researcher in Lehigh, that is Fazil Erdogan. That also was a person that became very famous, because he was the first with George C to make some mixed mode failure test, as we will see later in this presentation. And this is George C. He is one of the most famous Chinese professors. He worked in Lehigh for many years, but he also had different roles in academia in China, and he became very famous for two contributions. This one dated in 1974, that is the strain energy density factor applied to mixed mode crack problem, and after that the famous book that is reporting all his findings related to the mixed mode propagation. So I think this is the contribution of George C. But we will discuss later in detail what he discovered. Actually, this is a picture where George C. and Fazil Erdogan were together in the lab making the first test under mixed mode. So they invented this inclined crack, and they start to study mixed mode on rubbers for the first time. And after that, I think as for his pioneering contribution, it's important to mention James Robert Rice, that is still professor in Harvard, and actually he was the person that applied for the first time J integral, and after that he is now applying the same concept to geological materials and to other things of materials. So he's still active and working in Harvard University. And after that, I think is also nice to mention John Hutchinson, that is also a kind of key person dealing with elastic plastic solution for fractal mechanics. Actually today it's too short time for looking very well inside the elastic plastic solution, but I think it's nice to mention this person. And as I said before, this is the book that I'm mentioning. If you consider instead notch mechanics, it means that you consider a different kind of component, or a kind of geometrical discontinuity, where actually you don't have a crack, but so the flank of the discontinuity are not parallel, but you have a different shape with the notch opening angle that is different from zero, and actually the crack can be considered a kind of special case of a notch, because if you consider a sharp notch radius of 0, so if you consider a notch opening angle of 0, you have the crack as a special case of a notch. And the first contributor to this was actually Bratz, that was an engineer that studied the stress field of this kind of geometry when he first designed the dam in Pasadena. And actually it's interesting to see how it's always a need for something, to design something that is leading to new discovery in some fields, also some advanced discovery from a mathematical perspective. So actually he was the first to dedicate some study to notch components. After that, I think what it is important to mention is the contribution of Williams, and today we will see the Williams solution for notch components, for sharp notch components. But actually, there is also a kind of not very well-known work dated 1941, only in German, from this researcher that was the first to make the same analytical solution. So probably this is the first case of plagiarism, or not, we don't know. And I think if we consider a kind of generalized perspective on notches, I think Heinz Neuber, that worked for a long time in Munich University, is the reference person. He wrote the three fundamental books, the first one in 1937, the second one in 1958, and the last one in 1985. The only one in English is the one from 1958, translated by NASA. The first one from 1937 is only in German, and also is only in German the last one dated in 1985. But I think these books are really a kind of pioneering work about notch components, and still many of the equations that he has developed are not well understood. So it's still an area. Of course, we don't need to understand it much more, because we substitute the analytical solution with the numerical solution. So actually we don't need anymore to be able to develop something analytically. But what he was able to do analytically many years ago is really impressive. And actually, as I will show you later, to be able to understand an analytical solution is always very nice, because you can understand how to place correctly a boundary condition or a constraint condition in your finite element model. So I think it's very important to at least try one time to solve an analytical problem. Of course, you don't have to make many times. And I think if we want to go inside the applications, I think another eminent expert in the area, according to my experience, is Dieter Radai. He was president of the International Institute of Welding. Of course, if you consider a notch shape, and if you consider a weldment, the geometry of a notch and the geometry of a weldment are very similar. So if you want to predict fracture and fatigue behavior of weldments, you can use actually notch mechanics, and it is what Dieter Radai did from 1968, trying to provide engineering tools for designing notch components and actually apply to weldments. And after that, I want to remember, I think one of the people that contribute more in the last years with the theoretical solution on notch mechanics. It was my previous chief in Padua. He died in 2014, and this is also the reason because now I'm in Norway. Actually, I worked with him for more than 40 years. We worked together for many years, and I think some of the contributions that he developed are really outstanding and give a kind of very good overview, and actually are the best solution that we have up to now regarding notch mechanics. Coming back to fracture mechanics, you have previously seen with the Luca that we have mainly three modes of fracture. If you consider plane solution or actually out of plane solution, which is mode 3, but we will see later that if you consider not plane strain or plane stress solution, we will define them better later. You have also other additional modes of failure that are due to three-dimensional effects in your components. So if you consider a plane solution, plane stress or plane strain, so you consider, for example, that in plane stress the sigma in the z direction is equal to 0, or if you consider plane strain conditions, so that the epsilon in the normal direction to your plane is equal to 0, you are in a simplified condition. If you consider a real thickness of your components, in addition to these three modes of failure, we have other two modes of failure that are not predicted by traditional linear elastic mechanics, and we will see later the results of this. Of course, the necessity to study brittle fracture mechanics starts from these kind of events that were not possible to be explained with traditional design methods that they got in 1950. And they have a different case in the North Sea where this kind of failure happened suddenly without any possibility to stop this event or to prevent this event. And of course, we have many applications of fracture mechanics in weldments. In Norway, the first big accident that happens in fracture mechanics, that it is also linked to the development of the marine tech structure that we have now, is due to this offshore structure that collapsed in 1968, provoking actually that 68 people died in the North Sea, and after that the Ministry of Research in Norway has invested a lot for solving this kind of issue, and they established infrastructure and labs providing a lot of support for studying these kind of topics. And after that, of course, fracture mechanics is very strongly related to aircraft and this kind of aerospace application nowadays. But of course, this is not the only field. Also, geological materials, as you will see with the presentation of René de Borst in the next few years, are subject to fracture mechanics and to cracks. So I think it's a very wide topic of research. It's not only limited to steel, but is very important for different materials, for civil engineering and other applications. This is the last case of failure where we have a failure in Genoa 1 year ago with the 37 people that died. And of course, there are different components that are subject to crack. And actually, linear elastic fracture mechanics is not only applied to a crack, but can also be extended to contact mechanics due to the fact that a punctual contact or a point contact is very similar to what we, in terms of stress field, is very similar to what we have in cracks. So these are examples. I want also to add that a very important case where fracture mechanics play an important role is when the temperature is very low, and it is due to the fact that there is a kind of transition in the material. In fact, the properties of the material are very sensitive to the temperature, and what is happening is that actually the sensitivity to the defect or to the crack become much higher at very low temperature, and this means very dangerous to design with the same load that you are using, for example, at room temperature. So I think this is one important point to always remember. And Norway actually is a very good gym for this exercise due to the low temperature with minus 40, minus 50 in the North Sea. And actually what is now making Jim rise is to study fracture at very large scale in ice or in rocks. That is also a relevant topic for earthquake and how we can solve the problem of earthquake. So what it is an important point dealing with fatigue and fracture is that sometimes we have to design very huge components, but what is happening is that, and that makes fracture mechanics and fatigue due to crack propagation very dangerous, is that fatigue and fracture are very localized. So sometimes you are designing a component that is 5 meters as a diameter, and the process zone where the crack is initiating is few millimeters or less. So the local design is very important. So you cannot neglect details in your design. Of course, a global design is always welcome, but if you have increase of stress field due to geometrical discontinuity, it's very important to take care of this geometrical discontinuity and to proper design the components to be able to smooth the stress field close to them, because otherwise you have failures. And of course, actually this picture is very nice because you have a failure in a ship, but after that, of course, if you look to the initiation point in few millimeters, if you go to the grain size, it happens that it's a defect occurring in the material. If you go to the boundary, you understand that it is a boundary of a grain that is a problem, and you can go until the atomic scale. So fracture mechanics, it's important at many different scale levels, and actually traditional fracture mechanics is working quite well until we are at the scale of millimeters, as Rainer people will discuss tomorrow. But if you go down and you start to have cracks that have the dimension similar to the grain size or similar to the atomic level, you cannot use continuous mechanics to solve this problem. It's more complex, and you need to use additional or more sophisticated tools. This is an example that is also shown in the introduction in the first slide of this presentation. This is a component subject to hydrogen enrichment. This is my colleague that is studying this problem in Trondheim. Actually, if you look macroscopically to the crack, it seems a normal crack. The shape is a bit strange. It's a S-shaped crack that is due to some local mixed mode effect. But if you go down in scale until the notch tip, you see that also a crack that seems quite linear elastic from a macroscopic point of view, have micro voids and some plasticity close to the crack tip. Of course, this is a work that is still in press in engineering fracture mechanics. So it means that this topic is not closed. I want to show you that still there are researchers dedicating time on this topic. So now I will start the worst part that contains some equations. So I put this image where I give you a kind of kick in the ass about the presentation. So I don't want to make this part very long, but what it is important of this part is to understand that behind the fracture mechanics theory, there are some equations that we have to know, and there are some way for solving these equations that have been used for many years and are now very well established technique. In particular, I will discuss with you the iron stress function and Uskeli's-Willy-Kolosov approach, that are useful for solving the problem of the stress field close to a crack, but that are also possible to extend to notch components. So if you consider a stress field, you know that you have a stress tensor. Lucas Ulme has just shown before the stress field too close to a crack tip. I put this slide only for remembering what the stress is, but I think you are engineers, so you know. And actually that you have a stress matrix that is made like this. Actually, in a three-dimensional case, you have all these components present automatically on the component. So if you consider a finite thickness on your components, you have all these components present. What we usually do is to use some simplified model, or some simplified hypothesis that consider plane stress state. So in this case, we consider only one plane, and in this plane, the stress that are actually present are only the stress sigma x, sigma y in two directions, and the shear stress on the face of this small element. And actually, we are completely neglecting the thickness effect. Okay? And in this case, we are considering very thin components because the sigma in the normal direction, sigma z, is not present because it's equal to 0. And this happens when you have a very thin plate because due to the boundary conditions, so to the equilibrium on both the free surface of the components, on the free surface, of course, you have a condition where sigma z has to be equal to 0. On the other surface, the sigma z has to be equal to 0. So in a thin plate, the stress cannot move much from 0, and so it is 0. On the opposite side, you have plane strain condition where you consider very large thickness of your component. In that case, you consider not sigma z equal to 0, but epsilon z equal to 0, because actually the deformation, due to the thickness that is very huge, is equal to 0 in the normal direction. But this means that the sigma z is not equal to 0 because you have the Lamé equation that are connecting the different components. So you have epsilon z equal to 0, but the sigma is not equal to 0. What it is very important also for making analytical solution, but also has to be understood for making numerical models, is that actually what has to be respected generally is that we have a static equilibrium equation on a body. So when we are discussing about fracture mechanics and all this kind of problem, we have to respect the static equilibrium equation. It means that we are respecting that the translation in x and in y direction are equal to 0, and this is the equation. So we have to respect this equation, considering a plane case in a plane. And after that, we have the strain compatibility equation. It means that if we deform a body, actually we have to deform the body in the way that the body remain completely kind of uniform and is not fragmenting like this. So it means that the movement of the nodes have to be quite proper, and so that we have to respect this compatibility equation for strain in the way that we have this condition and not this condition. So as you know, actually in linear elastic fracture mechanics, or actually in continuum mechanics, the most important law are Hooke's law, and this is the starting point of any solution that we have also in fracture mechanics. And we can express this stress field also in polar coordinates or in Cartesian coordinates. It depends on which coordinates is fitting better our problem. So as I said before, we have two methods for solving, two approaches for solving a complex problem in fracture mechanics and also in notch mechanics. Actually, they were developed almost in parallel by two different researchers, Muskelishvili, that work together with Kolosov, and this is the Russian school. And after that, we have the IRI stress function approach that is also covered in this course. I put here the picture of the... Actually, I always like to put the picture of the people that almost have dedicated their life to develop a very focused topic, because of course it's a very specialized topic and no one is remembering them. It's more famous a pilot of Formula 1. But actually, what we are designing now is based on the contribution of these people and not from the people of Formula 1. So what it's important about the iris stress function is that it's possible to express the stress field close to a notch discontinuity or to a crack in this case, in the case of fracture mechanics, but is also used for other problems where we have a kind of stress gradient, also in contact mechanics. Actually, the key of this method is that we are able to express the stress field on the basis of the function that is phi, that is called iris stress function. So if we are able to find an appropriate function that is able to describe well our physical model, we can link the stress field to this iris stress function according to this equation that is reporting Cartesian coordinates. And of course, we can also express the compatible equation in terms of this stress function, and this has to be satisfied to maintaining the compatibility equation. So we have two kinds of equations that have to be respected. The problem is how to select. Of course, we have the same in polar coordinate system, so we can express always in polar. I don't want to go much in details of this, but we can always express the same equation in another stress field. I think it's important to know that if you change a coordinate system, the stress are changing. So you have only few invariants if you change coordinate system. So if you are looking, for example, in the finite elements, in ANSYS or in Abacus or in other software, if you are looking to a stress field, you have to be very careful if you are looking to the Cartesian coordinate system or if you are looking the stress to the polar coordinate system. The single stress is changing according to also if you are considering the same point, the same stress field, the stress field is changing if you are considering actually different local coordinate system for looking to this stress field. So this is very important. So actually, I want to concentrate on iris stress function because it's also useful for the Notch-Williams solution. But what it is very important is that the step one, so I put here the step for solving the problem, pick a harmonic function which is appropriate or that can describe quite well the problem, calculate the stress components in terms of the assumed solution, using Hooke's law to calculate the corresponding strain components, integrate the strain component to obtain the displacement component, and after that check if traction displacement boundary conditions are satisfied, so if we are respecting actually the compatibility equation of the problem. So actually we don't have much solutions that are available up to date analytically, but I think it's in this case we are focusing on fracture mechanics. Is very nice to mention two analytical solutions that are really the most important solution for a person that is starting to study fracture mechanics. And this is also the starting point of my master thesis when I started with Professor Lazzarin many years ago in 2001 to make my master thesis there. The first solution is a kind of very simple case where you have a plate without any notch discontinuity or any crack, subject to tensile loading. And actually the solution is very simple, and we actually the first to study this problem was Timoshenko, that was professor first in Russia and after that also in Stanford, that is now celebrating the fact that he was professor there with the Timoshenko Fellowship in Stanford. But this was the first time that they studied the problem. And of course, I report here the people that more contribute. I think the first, actually they work in parallel to the same problem, and the problem was to study what is happening to a plate with a circular hole. Actually, we have the most two important solutions that we have are a plate with a circular, weakened by a circular hole, and a plate weakened by an elliptical hole. Especially the elliptical hole is very interesting because if we think to an elongated ellipse, we almost tend to the crack shape if you consider a radius that is tending to zero. So actually the solution for the elliptical hole is very interesting because it's a kind of precursor solution for fracture mechanics. So the first solution is due to a German guy that first made the solution in 1898, but actually it became not very famous because the solution was in German. And after that, Goudier and Timoshenko, in page 58 of the book Theory of Elasticity, published in 1958, they reported the full solution also in English, in a book that is almost well known and is one of the best in the theory of elasticity. So the main idea is to understand what is happening close to the notch tip of the hole when you apply a uniform stress. So which is the increment of the maximum stress close to the notch tip with respect to the nominal stress. In a linear elastic solution, we call this factor stress concentration factor. So stress concentration factor is the increase of stress that we have locally close to the notch tip when we consider a nominal stress that is sigma. So one of the most important points to solve an analytical problem is to define the boundary conditions of the problem. And so the boundary conditions of this problem were placed by Timoshenko and other researchers around the edge of the notch, so when R is equal to A, and also very far from, so R equal to B, so we consider a very far point from the notch, which is almost not disturbed in terms of stress field from the notch distribution. And what it was made by this researcher was to find out a kind of iris stress function divided in two parts, phi1 and phi2, to solve the problem. Actually, this is the final solution that was obtained for studying this problem, applying the, of course, proper boundary conditions. I think if you try yourself only this case, which is the circular hole as a kind of homework, you understand really a lot and you start to also like more the analytical approaches that are behind many of the tools that are nowadays, that we are nowadays working or using. What it is interesting is that, of course, nowadays we can obtain very similar results with the finite elements, and what it is very interesting is that the increase of the stress field close to the notch tip, if you consider this kind of configuration, if you consider that the size of the hole is small in comparison to the dimension or to the width of the plate, you have a stress concentration equal to 3. So it means that the notch stress amplification or the notch stress concentration factor at this point is an increase of 3 with respect to the nominal applied stress, which is remotely applied to your component. Of course, also here we are considering plane stress or plane strain condition. We are not considering the thickness effect. But if I will show you later that if you consider or if you add the three-dimensional dimension, you have a different solution. It's not differing too much from 3, but of course you have a distribution of stress along the notch thickness that is changing a lot. And that is affecting the, so actually the value of 3 is valid only for plane strain or plane stress solution. So actually here is report the solution. The stress concentration factor is equal to 3. So we have one part of the notch that is under traction or tensile loading locally, and one part of the notch that is under compression, which is quite impressive because actually we start with the problem where we have only tensile loading, and on one side of the notch we have a compressive part. So this is a very simple example, but at the same point, if you are not familiar with the analytical solution with local approach, it makes the problem quite interesting. At least I found it quite interesting when I start my master thesis. And of course, what it is important is that if you plot along this line, so the notch bisector line, actually the stress field, you obtain a value that is starting from 3, and after that you have a very strong gradient of stress until you reach the value of 1, that is the nominal solution. This means actually that the critical part of your component is very close to the notch tip, and very far from the notch tip you have a condition where you are not affected by the notch. this explains also something. If you want to measure a kind of a problem like this from an experimental perspective, you have to be careful where you place the strain gauges, because if you place the strain gauges in the zone where you have only the nominal stress, so if you are too far from the notch tip, you are simply measuring the remote applied stress. So actually this also gives you some inputs that you have to use in the experimental activity to measure correctly these kind of effects. And this is only a simple solution. So as a precursor of, I think, fracture mechanics, it's important to mention English solution, because English was the first to study a more complex problem. This is really complex also if you want to make the calculation by hands, because the stress field of an elliptical hole requires more effort than a circular hole. And of course the coordinate system that is useful for solving the problem is called elliptical coordinate system, that is quite heavy to manage analytically. But also this is a good example. Actually, we don't have many analytical solutions for notches, but the two more fundamental are these two. And actually what English made was to study the ellipse, also an inclined ellipse, and was able to describe mainly what was happening at the notch tip. So it was not able to give the full stress field distribution, but it was more focused only on the stress concentration factor. So what it is interesting about this case is that English was able to formulate an equation for SCF, so the stress concentration factor. So how much the stress concentration factor increase when you are at the notch tip. It's interesting to see that if B is equal to A, you have A divided B equal to 1, so it means that the stress concentration factor is 1 plus 2, that makes again 3, which is the circular hole solution. But if B is becoming much larger of actually A, you have a solution where you are tending to 1 because this term is disappearing. But if you consider A very small, B very small with respect to A, it means that this term is tending to infinite. So actually, this means that the stress concentration factor, if B is tending to 0, is almost tending to infinite. And actually is without any meaning from any point of view, because if a stress is tending to infinite, we cannot do anything to design anything. So actually we understand from this equation that if we have a notch, a blunt notch with the defined notch radius, what we can use is a point method. So we can focus our attention to what is happening at the notch tip, because that is significant for the design, because that stress is a finite value and we can estimate how much this value is bigger than the nominal stress. But if we have a kind of infinite value of the stress concentration factor, this means that we have a stress field of a crack. This means that the point method is not working. What is happening to the crack tip is not giving to us any information of the cracked tip stress intensity. So we don't know anything about the intensity of the stress close to the crack tip if we consider only the stress tip. And in fact, when we discuss about fracture mechanics, we always speak of a field approach. So an approach that is based on not only on a point, but what is happening in the front of the crack at a certain distance from the crack tip. This is a very important point. So actually, if we consider traditional notch mechanics, we can always use a notch approach, so a point approach that is based on what is happening at the notch tip. But if we consider a linear elastic fracture mechanics problem, we have to use a field approach. So what it is important is not what is happening at the notch tip, but what is important is what happening close to the notch tip, in the front of the notch tip. And we need a field parameter able to describe the stress intensity in the front of the crack tip. And in the previous lecture, you have seen that this parameter is called stress intensity factor. Okay. So I will escape this part. This is a solution. I mentioned before that Griffith energy balance approach is very important in fracture mechanics, and I want to discuss with you why it's so important. Actually, Griffith energy balance approach was the first approach that actually allows us to understand which is the meaning of a stress field approach, and which is actually the physical definition of the stress intensity factor or of the fracture toughness of a material. So actually, linear elastic fracture mechanics was mainly born due to Griffith, and the reason is that if you consider what is happening for breaking atomic bonds in a material, you obtain a stress that is 10,000 megapascal for a steel. That is almost something that we cannot believe that it is possible. This means that if you consider actually atomic bonding, we are not able to actually describe the real ultimate strength of a real material, but the stress is mainly 100 lower, and we want to understand why. And Griffith tried to explain why, if we have a kind of bonding solution or atomic solution, we are predicting a stress that is completely wrong with respect to what we have in reality. And this is the problem that is studied with the energy-based approach. Actually, Griffith suggests that the low fracture strength observed in experiments is strongly dependent on the size of the component, and is due to, in fact, to some microscopic flows that after that were called by Irving cracks, that were not predicted by the atomistic or by the kind of atomic bonding prediction. So this is the main achievement of Griffith. Actually, if you consider theoretical strength of a solid, and if you consider that the solid is a kind of assembly of atoms, you can study the fracture for dividing two atoms according to these laws. And I don't want to enter in the details. I have reported here only for a question of to be completely, to report to you everything. But actually, the idea behind this is to study the attraction between atoms and to show that the fracture is when two atoms are separate each other due to a strength or a force. And what you find out is that the theoretical strength that you can predict with this model is the Young modulus divided 10. So for example, for a steel, you have 2000 megapascal divided 10, it means that you have 20,000 megapascal ultimate strength, which is of course not real, because we know that the maximum capacity of the steel is 2000 megapascal for the ultra fine grain steel, which are almost not used in any application. And so if you consider this table, if you consider Young modulus, the theoretical strength is very high with respect to the reality, but the practical strength that we find in the experiments is much lower. And the ratio between practical and theoretical strength is reported in the table. So actually, if you are not considering defects and size in the final prediction, we are missing something. And what Griffith did was to try to explain why we have so big difference in the theoretical strength and in the practical strength, and why the ratio between them is so high. So actually Griffith says that the main reason of discrepancies between these practical strength and theoretical strength is due to the existence of stress concentrators, flows such as cracks or notches, the existence of places of weakness such as grain boundaries in polycrystalline materials, so actually the scale effect, and after that the fracture process such as shear, slip or rupture, which occur by plastic deformation, are not considered if you consider a kind of atomic level approach. And actually, I like to remember Griffith because he was the first also to apply an energy-based approach. I think you will have the occasion in these 3 days of summer course to appreciate a lot what is the meaning of using an energy-based approach in a solution of a problem. Why it's so important to be able to connect the strain and stress to the strain energy approach. Actually, from a numerical perspective, it's very important, because if you are using a stress-based approach or a strain-based approach, you are considering actually a kind of differentiate problem where you have actually the derivatives of the stress field or of the displacements to obtain the stress distribution. And it means that if you want to solve numerically the problem, when you make numerical derivatives, you are actually accumulating errors inside the solution of your problem because of the derivative itself that is very complicated to solve numerically. But if you consider the energy approach, the energy is directly proportional to the displacement of your model. So actually, the model based on energy are completely mesh insensitive. So actually, all the models that are based on energy are not sensitive to the mesh size when you are applying numerical models. And this is very important from application, especially if you are looking to three-dimensional problems and real problems where you have huge structure to design, and the computational time can almost explode to infinite if you are not able to be efficient in solving the model. Actually, Griffith, of course, it was in 1932 without any computer and any other support. So he considered plane strength and plane stress solution, and he was able to derive the energy for actually bonding a component as a function of the length of the crack and the nominal stress of the component under plane stress and plane strain. And actually used English solution for actually approximating the stress field close to the flow. Yeah, I don't want to go much in the details, but actually what he was able to do was to express the total energy, and he added two terms, the internal work and the external work for making the crack propagate. And actually he solved this equation, providing the final strength of the material that were quite accurate with regarding to the practical solution for strength of the material. So actually this method is containing a crack dimension that is A. After that, there were more people that tried to solve the problem in different approach, and there was a correction to this approach, to Griffith approach, by Orwan. Orwan became very famous for the study of dislocations, but after that he was also able to study the problems of elastic energy, and he added there that is the plastic work that locally was very important in the crack propagation. And he modified actually the Griffith theory, adding this term. But of course the original idea was the one of Griffith 20 years before. So actually if you look, Griffith was in 1932, and for adding the plastic term it takes 22 years, so it's not a direct improvement. These are the details of the Griffith solution. I report here only for also this, in this case, for completing the explanation and to show how he used the Griffith, the English solution inside the energy solution for solving the issue. So the most important results of Griffith is that he made also some experiments, and he was able to interpret these results in a way that no one has made before. So sometimes we have a lot of experimental results in front of us, and we are not looking to these results in a very good way. So this is another thing that happened also to me many times. So we have a lot of results available. So we have a lot now, but sometimes we are looking these results in a very, very bad way, or on the surface, and we are not understanding which is the real behavior behind this, and we are not able to interpret them properly. I think that what is the real contribution of Griffith was that he was able to make some experiments where he make a crack component like this, he was very smart and he changed the dimension of the size of the component, and he measured the strength for making a static failure of the component. And after that, it was quite, I think, clever to make a kind of multiplication of the critical sigma c, multiply the square root of A. And he was able to find out that this product is almost a constant. Actually, if you consider the stress intensity factor for an infinite plate, this is almost the equation, of course neglecting the shape factors. But actually, it was the first to practically show that the stress intensity factor exists, is able to take into account a different size of crack, and of course is independent of the material, because it's only a material property. And so actually what it was able to find out here is not a stress intensity factor, but it is a material property that after many years it was called fracture toughness. Actually, the stress intensity factor is generally a stress, a nominal stress applied for a square root of the crack length. But here we are applying not a kind of nominal stress. This is the stress that is breaking our component with that length. And so it is the critical stress. And so what we are finding out here is the critical stress intensity factor that nowadays is called fracture toughness. And of course is taking into account the crack length. What it is very important here is that we understood from this equation that automatically linear elastic fracture mechanics is considering scale effect, and is automatically including this information in the equation of linear elastic fracture mechanics. If you consider the notch components with the weakened by a hole, and if you take a plate of one dimension and after that you scale all the components of 10 times, so you increase the components of 10 times including the hole, and you measure the stress concentration factor, actually you obtain again 3. So the point method in traditional notches is not scale dependent. So if you consider a notch component and you multiply by 10 the notch size of the component, including the notch diameter, what you are obtaining is the same stress concentration factor. So the point method on traditional notch mechanics is not scale dependent. And in fact, if we are considering the stress concentration factor for designing under fatigue, for example, a component, we have also to consider a dimensional factor that is considered as another factor, an additional factor that is taking into consideration the size of the component and that is decreasing the fatigue life. Linear elastic fracture mechanics is more powerful because the linear elastic stress field locally is just automatically able to consider automatically the scale effect into consideration. So as I said before, of course, we are working at the scale of engineering application until the size of millimeters, but if you go down in scale until the micro scale or atomic scale, actually there are a lot of drawbacks also to this theory and to this application, and you will see this tomorrow in a very interesting presentation by Reinhard Tito. So I want also to say that the Griffith model was a very strong inspiration for a different series of approaches based on strain energy density. The most famous approach is due to Jim Rice, and is the definition of J integral, that is an energy-based approach. Okay, and that actually is working very well for crack prediction. If you consider all the algorithms inside ANSYS or Abacus for determining the stress intensity factor automatically, they are based on J integral. Actually, J integral is this kind of equation, and is combining the strain energy density in one point, multiply this very strange factor that is actually the tensor along the path where you are studying the problem. So T is actually at the traction vector in the point where you are studying the problem, and the derivative of the displacement with respect to the x. The drawback of the approach is that you are making these derivatives, so it's sensitive sometimes to the mesh size, it's not insensitive to the mesh size. The positive thing of J integral is that it is path independent. It means that if you are considering a different path around the crack tip, J integral is independent from the path position, but is mesh sensitive. So actually is a partial energy-based approach, because in the second part of the approach there is actually a stress tensor multiply the derivative of the displacement. Actually, there are different ways for representing J integral and for connecting to the strain energy density, and this is mainly due to the work of Hutchison that was making later. And I think it is also interesting to mention that after that J integral, almost very recently in 2013, it was extending with a very complex formulation to a three-dimensional component. So actually, nowadays we have also the closed form solution for three-dimensional components. Actually, numerical solution in finite elements are taking account of this solution for giving to you the three-dimensional stress intensity factor along the thickness of the three-dimensional component. So, I think another important point for the stress solution is the solution by Westergaard that was made in 1939. What he made is to use the Iris stress function defined in this way, actually using a complex equation. So an imaginary plane where you have zeta that is a complex function expressed like this. And he was able to determine sigma x, sigma y, and the shear stress, actually making the derivatives of this equation and solving the problem in closed form, actually finding out the same solution of Irving. And the first to visualize, there were different researchers that were able to visualize with optical method the stress field close to the crack tip. So the first time they use interferometry and other optical methods to be able to reconstruct actually the contour lines of the stress field close to the crack tip under mode 1 solution. I think you have seen in the previous lecture that there are some limitations to this elastic stress field, so the nominal stress has to be lower than 0.6, 0.5, the yielding strength of the material. After that, the stress field or the Irving stress field is valid only in the close vicinity of the crack. So if the crack has a length of A, the stress field is valid only at the distance that is A divided 10, and only in that region. And after that, the Irving solution is only valid for mode 1, so it's not considering mixed mode loading. Actually, this is the stress solution that you have seen before. If you consider plane stress or plane strain, nothing is happening to the stress field on the plane. So actually, if you are considering an hypothesis of plane stress or plane strain, if you want to measure the stress intensity factor K, the stress intensity factor K is the same both for plane stress and plane strain. So you don't have to expect different results in plane stress or plane strain hypothesis from a finite element model. And the definition of the stress intensity factor is sigma y multiply the square root of 2 times pi r. So if you consider the notch bisector line, for example in this equation, theta is equal to 0. So theta is equal to 0, so it means that the sine part is disappearing, the cosine part is equal to 1, and so you have k divided the square root of 2 pi r and equal to sigma y. If you multiply this vector for sigma y, you obtain k. And actually this is valid for any point at a distance, at any distance from the crack tip. So for any different value of r, you can actually determine k. Of course, in the area or in the region where r is less than A divided 10, so in the range of validity of the Irving equation. Okay? So actually, if you make a finite element model nowadays, you can easily obtain the crack stress field. And what it is very important is that if you consider sigma y with respect to r in a double logarithmic scale in the front of the crack tip, you have, according to the law that you are applying to the component, in a double logarithmic scale, you have a linear elastic trend. Okay? And the slope of this stress field in a double logarithmic scale is equal to minus 0.5. That is called stress singularity of the stress field for the crack component. What it is very interesting is that if you consider K1 according to the definition that we have seen before, if you are considering different r at different distance, what you obtain is that the square root of 2 pi multiply r multiply sigma y is giving a constant value. Okay? So actually the graph is plotted from 10 minus 3 until 1, and is completely neglecting what is happening to the stress tip of the crack. Completely neglecting. So what we are looking here is what is happening at the close vicinity of the crack tip, in the front of the crack tip, but not on the crack tip, because the crack tip is completely without any sense in terms of stress. Actually, the stress is infinite, and we cannot say anything about the stress intensity of the stress field if you look to the stress tip. It's a singularity. Okay? Singularity, sometimes my students say that singularity is something strange because it's singular. It's something strange. In Italy we say singular when something happens that is strange. But singularity means that the stress is going to infinite in one single point, so we have a vertical asymptote of the stress field, and not that the stress field is strange. Okay. And after that, of course, after Irving, of course, they developed the Cartesian and the polar coordinate system, and as an extension of Irving's solution, they were able to find out the solution for poor mode 2. So actually, if the plate is subject to push here, we can define actually a stress intensity factor of mode 2 with the same identical way that we have defined the stress intensity factor under mode 1. And the same happens under mode 3. That actually is the most easy case, because we have only actually 2 stress components that are present in mode 3. If you want to have a quick estimation of the stress intensity factor for an infinite plate, there is a simplified equation that is this one, that is only valid for a kind of infinite plate. So it means that the dimension of the crack is smaller with respect to the width of the plate. And actually, what we are using for making this calculation is the length of the crack, multiply not the local stress, but the global stress far from the notch tip. So this is very different with respect to the previous expression that we have used locally. The previous expression was based on the local stress field close to the crack tip. This is very important. This stress is, of course, a global stress field far from, which is the remote applied stress to the component. Of course, this cannot be applied for any kind of component because it's a very special case, and this case is when you have an infinite plate under poor mode 1. But what it is very important is to understand the difference between a local approach, that was the previous one, and the global approach where we are considering a definition of the stress intensity factor based on the remote stress applied to the component. We can make the same under shear stress, so the mode 2 stress intensity factor is a function of the shear stress, and we can make the same under mode 3. But all these stresses are referred to the remote area of your component. Actually, if you want to consider also a kind of dependency on the geometry, here I take the equation from another book. Sigma is the S is the infinite, the stress applied remotely to the component. But what it is added here is the factor F, which is a kind of adimensional factor that is called shape factor, and that is able to also consider a finite dimension of the width of the plate with respect to the crack length. Okay? Actually, in the handbooks, this is taken from Norman and Dowling book. That is one of the most famous books dealing with the fracture mechanics and fatigue. You have different graphs that are plotting, for example, for different configuration, the factor F according to the ratio A divided B, where B is the actually semi-width or width of the plate according to the shape that you are considering. And of course, if you have an infinite component, the starting point is 1. If you have a finite component, so if A divided B is changing, the factor F is increasing. So actually the stress intensity factor becomes sensitive to the shape of the crack with respect to the width of the component, and you change completely the dimension, the value of the stress intensity factor. Why we are trying to make this? Because what we want is sometimes to avoid to make finite elements model every time. So we want some handbooks that make our life simple, and we are able to estimate the stress intensity factor without going any time inside the finite element software for a numerical analysis. About this, you can find 4 handbooks published by Professor Yukitaka Murakami in Japan that are reporting almost all the possible cases dealing with the fracture mechanics and with the stress intensity factor evaluation. I report here many examples. I don't want to make much more details. What it is very interesting is that we have discussed now about the stress intensity factor, but the stress intensity factor is actually only a geometrical based parameter, so it's based on the remote applied stress, as we are seeing now, and on the semi-amplitude of the crack, so on the square root of the semi-amplitude of the crack. But this is not a material parameter, because actually we can apply any kind of stress and we can obtain different value of the stress intensity factor. If we want the limit of our material, so how much the material can survive in terms of static stress, we have to define the fracture toughness that you have seen probably also in the lecture of Lucas Sussman. So K1C is our material parameter, is independent on the crack size, and is giving to you the maximum limit of the material, so the material can reach only that limit in terms of critical value of the stress intensity factor if you are applying an external load. And at that value of K1C, the fracture happens instantaneously. Okay? So comment on fracture toughness. Actually, it's interesting to see that if you have a shape factor included, you have to consider this also in the evaluation of the fracture toughness. So actually, in the range of the specimen size, we are not much sensitive to the fracture toughness, to the shape of the component. But as Professor Reinhard Pippan will show tomorrow, the shape factor can play a very important role if you go down in scale. This is very important. And after that, another important consideration is that AC is a critical length, which is actually quite important, because if we have inside the material a defect that is smaller than AC, the material is not sensitive to that defect, so the material is behaving is like a material without any defect. If in our material we have a defect or an initial defect of the material that is higher than the critical value of AC, actually the material became sensitive to the defect, and so we have to go for fracture mechanics. So actually we have a transition between designing without defects and designing with defects, considering this AC, which gives us a kind of material property that is also called sometimes critical length property of the material, that is quite interesting. If we consider broad trends in K1C, we can see that steel has this kind of values, aluminum alloys and ceramics have different kind of value, our plastic have this. So actually there is a very strong variability of the fracture toughness with respect to materials. And this is another table reporting some interesting steel used in application. Actually, we have a different way for studying or for evaluating the fracture toughness. What the standard enforce give us is a standard dimension of the samples and some rules that we have to follow to determine in a standard way this fracture toughness parameter for uniformly having a kind of value that can be trusted in the design that we have to do later using this parameter. So we have different kind of components, and this is interesting because of course they are also very interesting to the scale effect. So this is the biggest samples and this is the smaller sample. And the standard enforced mainly, the main standard enforced is from ASTM, American Society for Testing Materials. It gives you some different samples and it gives you the shape factor that you have to use for evaluating at the end the fracture toughness of your component and some rules for evaluating it. You can evaluate also with 3-point bending. So actually the first one is with axial loading on this pin and this pin. So you actually put traction on these two pins. In this case you have a pin here and two support here, and it is 3-point bending test. And after that a different configuration. What it is very important is that, and this is also a limit that is given by ISTN, is that fracture toughness is dependent on the specimen thickness. This means that for designing purpose, what we need actually for designing properly a component is to have the lower value of the K1C, because if we design with this value, we are not in the safe direction, because we are considering a limit that is higher than the real one if we consider larger components. So usually the information that we need to design under static loading is this parameter that is called fracture toughness, and it is specimen thickness dependent. And actually the standard reports a rule that say that if you have a T that is greater than 2.5 KQ divided the yield strength of the material power 2, you are in the condition that you can consider the fracture that what you are finding out that KQ actually is K1C. So actually what you do when you are testing material for finding out the fracture toughness is considering different thicknesses. You can start probably from a smaller value of thickness. You for example, find this value, you use this equation, you try if T is greater or lower than this value, that is KQ, and after that you start another thickness that is greater until you will find that this relationship is satisfied and is reporting the standard. When you first find out that T is greater to 2.5 this product, you are in the condition of fracture toughness. Another important point is that the fracture toughness is strongly dependent on the yield strength of your material. So actually, if you increase the toughness, you actually are losing in terms of strength. If you increase the strength, you are decreasing the fracture toughness. So actually, there is a kind of contradiction between these two parameters. If you increase the strength, you are decreasing the capability of the material to absorb energy. But if you are actually decreasing the toughness, you are able to reach a much higher strength for your material. And so you have to be careful which is your application. You want the high strength because you don't have problem with cracks and defects, or you have problem to absorb energy due to cracks and defects. So you have to tune this. So it's always a selection. You cannot have both satisfied. Actually, there are some materials that are satisfying both these conditions, and I will show you later. And another important relationship is that plane strain, fracture toughness, and yield strength have not a kind of relationship. So if you consider a yield strength of 200 and you look to the variability of the the plane strain fracture toughness, you have a range that is very huge, from 40 to 240. This means that it's not only important the material yield strength, but also which is the heat treatment that you are applying to the material. So actually, there is not a direct correlation between the yield strength and the fracture toughness. For one value of fracture toughness, of yielding stress, you can have many different values of fracture toughness. So actually, there is not a linear relationship between these two values. There are very interesting maps reporting fracture toughness with respect, for example, to Young modulus in the Ashby maps. It's a very famous book, and also it is very interesting because it is used also to represent trends on new materials. And so actually it is evident from the Ashby maps that there is a contradiction between fracture and strength. From fracture toughness and strength. If you want to increase the fracture toughness, it's like a kind of drawback. If you want to increase the toughness, you always lose in strength. So if you consider fracture toughness and strength, you can see the different range of material in this nice graph. What it is very interesting, and what I want to mention this paper, is that there is a very nice paper in Natural Material by Robert Ritchie. Robert Ritchie is working in Berkeley, is the most cited researcher in fracture mechanics and fatigue. He is emeritus professor now in Berkeley University. And actually he was describing the conflicts between strength and toughness, always trying to explain why we have these conflicts and contradiction between these kind of approaches. And what it was very interesting in this paper is that he was studying different kind of natural materials, showing that this kind of material sometimes tends to solve the problem of conflicts between fracture and toughness due to the microstructure of the material that is designed from nature in the way that the material is very strong, but at the same time is very able to absorb energy and also to repair itself when it is damaged. So the natural materials are very interesting because you are always able to find material that are able to maintain a high strength and also a high fracture toughness and are also able to repair themselves. Actually, they published a recent paper in 2019 on material science of nature arms race, where they describe a lot of natural materials, and they show up that, for example, actually with biological material science you can reach properties that are very high with respect to natural material because of the local geometrical design that the natural material can have, and that are very different from man-made material in this regard. Actually, we have to learn a lot from natural materials because we can actually increase the property of new materials, look into the local properties of these natural materials. Actually, they studied very interesting examples. So they actually mentioned this, natura magistra intelligentiae is a Latin motto. It means that to follow what nature is doing is always very nice because we can learn a lot. And actually, if we consider a very simple and funny example of a teeth of a shark, we can actually understand that the shark teeth is very strong because he has a kind of structure. This is the TM image of the teeth. That is a kind of composite at the almost a nano scale. That is impossible to see from the macro scale, but actually the structure is made in the way that the material is not only very strong but also very ductile, because this fiber increase a lot the ductility in different direction of your material, for example. But they made very nice example also of different natural materials. And actually there are very interesting results also from other researchers. In particular, there is an Austrian professor that is Peter Franz that is studying a lot of this natural material in parallel to Ritchie, and I want to mention he has published some recent papers, probably older than Ritchie paper, but is in 2005. And of course, this can be used as a lecture or a lesson from nanostructural perlitic steel wires for building up, as Rainer Piepan made, some ultra strong materials. And I think he will show you tomorrow how it's possible to make this and how it's possible to actually win the conflict between strength and fracture toughness, which is actually one of the main challenges of this century. Because if we are able to solve this, actually we have ultra strong material that we can use. The second challenge will be to have this material at a cheap level, so in a way that everyone can use them. And actually there are very good examples in some different papers. One good example of this ultra strength material is high entropy alloys that allows to have a very high strength and a very high ductility in parallel. But of course, I want only to mention this and to give you a reference, so you are able, if you want to investigate more these topics, you have some starting points. Another interesting point is that what we can learn from nature if we want to design against fatigue. If you, for example, consider a very simple example of a branch and a trunk in a kind of tree, what David Taylor made is to study the geometrical optimization of the notch. And what it is very interesting is that the notch is not uniform here, so it's not like this circle, but is changing gradually, actually to diminishing or to smoothing the stress concentration factor. So the green curve here is the concentration factor of the natural structure, and the orange one is the stress field of the circular notch. So nature tried to actually optimize the notch radius in the way that is reducing naturally the stress concentration factor. So it is just a kind of optimized design in a way of topology optimization that is also able to take into account local fatigue design. This is very interesting, I think, because it's solving a lot of issues that we have in fatigue design. Actually, all the tools that we have now with the new possibility that we have with additive manufacturing are giving us the possibility to design very complex components, and there are a lot of software like Abacus or ANSYS that are trying to topology optimize, so removing material to make the structure light and to increase the stiffness. But actually, to increase the stiffness is not the key, because if you increase the stiffness without taking into account the local approaches or what is happening close to the notch tip, you can decrease the weight of the material. You can make a component light, but it's better if your component is working under static loading and not under fatigue, because if you subject to fatigue the component, if you don't take into account the real stress concentration factor of the notch tip, you are missing a very important information. So actually what is missing nowadays in the topology optimization in this part. And actually nature is very interesting, because if you have connection between parts, what it's trying to do is to create a kind of mechanical interlocking. So you don't have a straight edge between parts, but you have a kind of zigzag pattern that is increasing the contact of surface, and this is increasing a lot the strength, because you have more surface in contact, and so you can increase a lot the strength. And this happens in many applications. So actually what we did with some study recently was to study a bonded joint that was designed like this, and a bonded joint with the sinusoidal bonded line. And of course, if you consider the comparison, you can increase the static strength of 2 times only with this mechanical interlocking, which is quite interesting. So I want to put out this slide, because I think that what I have shown to you in the last part is that what we have as a challenge for you guys in this future is not only to be expert of fractal mechanics of a very specific field, but to be able to have a more multidisciplinary. And I think the first example of multidisciplinary was given by Leonardo. We are today, or this year, in the 500 year from the death of Leonardo, and we are celebrating this death. And so I think that to have a multidisciplinary approach is very important. So if you consider mechanical engineering only as a kind of very closed topic, you will not solve any problem. Mechanical engineering is working with the continuum mechanics, is working with the understanding of material, is working with the process due to additive manufacturing, is working with many other subjects together. If you don't have this overview, I think you are missing a lot of information nowadays, and you cannot have what you want for the design purpose. So I think what it is very important is to be completely open. And of course, we need to be also focused, but we need to have the right parameters from different topics or for close subjects to design our real component. Actually, natural material are an example, because we are studying something that is biological and transfer this information to the design of a complex structure that can be made in steel. Okay. What it is another important information, and after that I will stop the first part because I'm very boring, is the effect of the temperature and toughness. So actually I have shown before to you that there was very big failure in the Northern Sea due to the fracture mechanics. And what is happening is that the temperature is affecting a lot the value of the fracture toughness. So if you actually decrease the temperature, so if you reach, for example, for this steel minus 25 degrees, you have a very strong decrease of the fracture toughness, also before this value. So, and at the same time is also decreasing or is increasing the yield strength of the material, decreasing the temperature. So if you decrease the temperature, actually your ultimate strength or yield strength is increasing. At the same time, the fracture toughness is decreasing. This means that at lower temperature, we have a brittle materials, and more brittle materials. The fracture toughness is decreasing a lot, and the ultimate strength is increasing. It's like going the direction to have a glass component, also if you are starting from a steel. So the steel is not the same if you are considering a steel at 20 degrees or the steel at minus 40 degrees. We need to be very careful for which is the service temperature of our components. This is very important. If we are not taking into account this, we still have a lot of problems. The variation is 2 times, 3 times. So you can, if you don't predict this properly, you can have failures that are completely unexpected. And another important point is that if you consider the graph before, so that the temperature is changing, if you consider 2 different temperatures, T2 and T1, so T2 is the room temperature, and actually the critical size of the defect for the room temperature is this one, but if you decrease the temperature to minus 60 degrees, for example, you decrease the fracture toughness, so you translate the curve of the fracture mechanics down because you are decreasing the fracture toughness, and you increase the fracture strength. This means that you are changing this parameter that is that's becoming smaller, so A is becoming smaller. A star is the kind of intrinsic crack length of the material. It means that the material at low temperature is more sensitive to defects because also smaller defects become important and relevant for the fracture behavior of the components. So the temperature is very important. At room temperature, this value is large, so also if you have large defects, the material is not very sensitive to the defects. If you have a lower temperature, also smaller defects become very sensitive. This means that the material is completely another material in terms of design. Okay? Yeah, I have a lot of solution for surface and internal cracks, but I think now we can make a stop. I don't want to start more. I think we can make 15 minutes of stop. Okay? I hope that I think at least I provided some information. The second part of the lecture, I want to go on mixed mode, and after that I start to introduce a bit notches and three-dimensional effects, as I mentioned before. But actually, I think one of the most critical problems that we have when we have a fracture mechanics problem is that usually it's very difficult to have a component subject only to mode 1. And so usually you have a configuration where you have a kind of mixed mode loading combinations. So you have cracks that are inclined with respect to the direction of the load. And so actually the local mode 1, the local stress field is not mode 1, but is a combination between usually mode 1 and mode 2. And if you have also out of plane loading, it's a combination also with mode 3. So actually the problem of how to treat these modes in terms of final fracture prediction was studied many years ago. And the first two to study the work were George C. and Fazil Erdogan in the group of Lehigh University that I have shown to you before. And they start to make some experimental tests with the inclined cracks to understand how they behave and how it is possible to predict the behavior of these cracks when they are failing. Actually, the first paper that was produced from this study was dated 1963. It's a very famous paper that has nowadays more than 2,000 citations, and it's always referred as the most important contribution for mixed mode loading. Actually, it was establishing a criterion that is called maximum tangential stress criterion. It is based on the idea, so the maximum tensile stress criterion, or MTS criterion, is based on the idea that if you have a crack subject to mixed mode loading, the direction of the crack propagation is the direction where locally you have a mode 2 that is equal to 0. So locally the crack tends to propagate in the direction normal to the local stress field. So in a condition where you have a kind of equivalent mode 1 condition. And so actually what George C. and Erdogan find out is that you have this kind of relationship that the crack tends to propagate when this equation is solved. So actually when the contribution of the stress due to mode 2 in this direction is equal to 0, and when actually locally you have a kind of point or a kind of cube of material that is only subject to tensile loading locally. So locally there is not mode 2, and so the criterion is also closed. It is also called the local mode 1 criterion. Actually, it's very simple because it's a kind of imposition that locally you only maintain mode 1. After that, George C. also improved the method, introducing a strain energy density approach that has two advantages. It's also sensitive to the Poisson's ratio variation, and is also sensitive to the mesh. Is also insensitive to the mesh size. So this is a big advantage. But actually, in terms of angles of prediction of crack propagation, is very similar to the maximum stress criterion. So there is not a big difference in terms of angle prediction with respect to the maximum stress criterion and the strain energy density criterion. Actually, they give almost the same value of angle in terms of crack propagation. This table is reported in a book that is nowadays used for teaching, that is Sung Ing book, that is called Fracture Mechanics and published in 2012 from Taylor and Francis. What it is very important when we deal with fracture mechanics is that we are assuming a linear elastic behavior for our material. So what it is very important is that we always can use a superposition principle for solving a complex problem. So this is very important. Actually, if we have a combined case like this, so where we have a remote stress field and a point force applied here, we can always say that the complex model can be divided into sub-models. The first one is the one with the remote stress, and the second one is one with the punctual stress or punctual force applied here. And if you have the closed form solution for this and the closed form solution for the two sub-model, After that, the combination of the stress intensity is the sum of the first term plus the second term. So the advantage of having a linear elastic model is the possibility to always use superposition principle. You don't have to repeat the model. Also, if you change the stress level of 2 times, the stress intensity factor increases of 2 times. So you don't have to remake any kind of model. So the superposition and the scalability with respect to the load is a very important effect of using a linear elastic hypothesis in your modeling. But actually, locally, as I have shown before, plasticity occurs, and so what happens is that sometimes plastic field is not negligible, and we need to take into account of it. And so there are also elastic plastic fracture mechanics solution. But of course, when you introduce plasticity, you lose the possibility of overposition principle. So any time that you apply a load to your component and you obtain a solution, that solution is only valid for the applied load that you have applied to the elastic plastic solution. Actually, the integral is very flexible, can be applied also for elastic plastic solution, and actually the stress field for a crack in elastic plastic condition is based on a J-integral definition and is mainly based on the work of John Hutchinson. As always happened in that period, there were different people working on the same topic. Rice and Rosengren obtained a solution, and Hutchinson obtained a solution in the same year, and after that they start to fight for which was the owner of the solution. But actually what it is very interesting is that you can express the stress field of the material according, generally in terms of J integral, and according to a kind of elastic plastic rules for your material that is not more linear but is following these rules, so is following a kind of potential rule where n is the hardening exponent of the potential expression of your material. You can also use a Rambert-Osgood equation for your material, but what you are obtaining is a stress field that is a function of J integral, a function of an angular function of theta that is still depending on n, and this is also the reason because the stress field is not scalable in terms of loading and in terms, so the overposition principle is not valid because the angular function are also depending on the strain hardening material property. Okay, and after that you have this contribution in the exponent of n that is a material property parameter. So actually, if you consider a kind of estimation of the plastic radius, it's always very convenient to be able to estimate in some way which is the plastic radius of your material. So if you have a crack, you have always the possibility to understand which is the size close to the crack, that is where inside which the material is over the yielding strength of the material properties, and so you can measure the radius and you can define this radius as plastic radius of the material. If the plastic radius is very small, you can apply without any problem linear elastic fracture mechanics. If the size increase, probably you need to go through a more complex model considering elastic plastic mechanics solution. Of course, the shape of the plastic zone is depending on the mode that you are applying. If you have the plastic zone shape for mode 1, you have like this butterfly shape, but if you have mode 2, you have like a 8 shape, and if you have mode 3, it's perfectly a circular shape. Okay. So what Hutchinson made was to describe the elastic plastic stress field in small scale yielding, so the plastic zone is small with respect to the K field. So you can almost consider the first cluster of the stress field elastoplastic, but if you are interested to a zone that is larger, so if the process zone that you want to use for the design is larger, you can use linear elastic fracture mechanics. But if you are in the condition where you have a large plastic yielding, it means that the plastic stress field is larger, and so actually you have to design in this field, and you have a linear elastic fracture mechanics only outside that region, but is not interesting for the design process. So what it is important to know is in some way the size of the plastic radius for your material, and if you estimate that value according to the load that you have in place in the service condition of your components, you can decide if you are in small scale yielding, in large scale yielding, or if you are actually in fully linear elastic condition. This is very important for selecting the way in which you are presenting the material. Actually, if you consider this configuration, this is the stress field, n equal to 1 means a linear elastic trend of the material, and you have a slope that is 1 divided 2 of the stress field. If you increase n, so if you are going if you are selecting a material that have a hardening exponent equal to 3, the slope is decreasing, actually. And if you consider a kind of elastic plastic material, you have a fully plastic behavior. It means that n is equal to infinite, and actually you don't have any stress singularity, and the stress field is almost constant. So you are almost in the static case without any crack. I think it's interesting to mention that this approach was also extended to notches by this team from Padua, where Lazzarin was leading. Livieri, Zambardi and Zappalorto were also very active on this field, and they were able to actually define a stress intensity factor that is also a kind of plastic notch stress intensity factor that is a useful parameter to describe the stress field under elastic plastic condition in presence also of V notch and also of cracks. Okay? And of course, the scale effect is also present for this kind of behavior. It's only the exponent of the stress field that is changing, so the scale effect is changing proportionally to the stress field slope. I promised to you before to arrive at least to the Williams-Asymptotic solution for under linear elastic conditions, and now we are here. Actually, considering closed form solution, this is the most important contribution dealing with V notches. And actually, as I said before, if you consider a notch, it's like an extension of the crack case. The only difference is that you don't have a parallel flank of your defect, but you are opening the face of the geometrical discontinuity, maintaining the notch radius equal to 0. So the crack is a special case of this V-notch shape. Okay? And the first to solve the issue, we just mentioned that the first one was a German 10 years before, but the most famous contribution is due to Williams, that published Williams was a mathematician, mainly not interested in engineering problems at all, but he was interested to solve this issue, and he tried to understand which was the stress field close to the notch tip in presence of a radius equal to 0. And actually he used an iris stress function in a very simple shape that was a kind of contribution depending only on R, and a contribution only depending on theta. And what he did, it was to express f theta as a function with some constant, as an angular function of theta, and introducing A, B, C, and D that are constants that have to be determined under imposing some boundary conditions. Actually, actually the aim of William was to solve both the mode 1 solution and the mode 2 solution. So he plays the blue terms that corresponds to the symmetric part, so the mode 1 solution, and the red part that are corresponding to the antisymmetric or shear stress solution corresponding to mode 2. Okay? And what he did, it was to apply the angular expression of the iris stress function, and by imposing the boundary condition on the edge of the notch that have to be traction free, so without so if you want that the component, the boundary condition respect the radial stress has to be 0, and the tangential stress has to be 0, and the shear stress has to be 0 along the traction-free edge of the notch. He imposed these 4 boundary conditions on both edge of the notch. So you have 4 conditions, and you are able to determine the 4 constants, and you are able to obtain the stress field close to the notch tip. Actually, the Williams asymptotic solution considers that the strain energy is small disk of radius rho around the corner. And actually, it is important to understand that this value, this consideration on energy is valid only if lambda is greater than 0, because if lambda is lower than 0, we have an infinite energy close to the notch tip, which is an impossible solution from a physical perspective. Actually, what he did, it was to impose that sigma theta and tau r theta are equal to 0 along the flanks of the notch, and imposing these boundary conditions that are quite simple from a mathematical point of view, he was able to find out these simple solutions, and actually he was able to show that there are 2 equations, one for mode 1, which is the symmetric part of the solution, and one for mode 2, that is antisymmetric part of the solution. Lambda, which is the unknown parameter in these equations, is called the eigenvalue of the solution, and is actually the degree of singularity of your stress field close to the crack tip. So if you consider lambda minus 1, and if you consider the crack tip, you have a slope that is minus 0.5. If you consider a notch, so if you are moving back in this graph, because you are considering a notch, 2 times alpha is the supplementary angle to the notch angle. So in this direction, you can open the angle, and the eigenvalue is decreasing according to this slope until you reach the condition where you have completely not a notch but a plane specimens without any geometrical discontinuity, that is this point. What it is interesting to understand is for symmetric case of mode 1, the stress field is singular from the crack case until a notch opening angle of 180 degrees. For the mode 2 condition, the stress field is singular, so tends to infinity at the notch tip from 0 until this angle. So actually there is a limitation, so there is a point where at a certain point of opening the angle, the mode 2 becomes not singular, and only mode 1 remains singular, which is very important consideration. Actually, as we made for the crack tip, it's possible to define the same definition of the stress intensity factor that is in this case as an extension is called notch stress intensity factor. That is again a function of the stress field close to the notch tip, multiply the square root of 2 pi, multiply r with power 1 minus lambda 1 and 1 minus lambda 2 if you are considering mode 1 and mode 2. Of course, the slope of the stress field is given by 1 minus lambda 1. If we have the crack case, so a notch opening angle of 0, we have 1 minus lambda 1 that is equal to 0.5 according to linear elastic fracture mechanics. So actually, the crack case can be seen as a kind of simplified or special case solution of the Williams solution. And again, also in the case of a notch opening angle, what it is interesting is that we have a field parameter that is a constant value close to the notch tip. So we have K1 that is constant according as a function of R. What it is also interesting is that if you change the notch opening angle, K1 and K2 are changing their unit of measure. So if you have a different notch opening angle, you have different value of the unit of measure for K1 and K2. This means that if you have a different notch opening angle, you cannot directly compare the value of K1 for a notch opening angle, for example, of 120 and for a notch opening angle of 150, because it's changing the unit of measure. Okay, so this is also very important, and this is also a limitation of the approach, of course, because you have not a direct comparison between different notch opening angles. This is a very strong limitation. Of course, as I said before, the Williams solution is a special case of the Irwin solution is a special case of the Williams solution, and actually what it is interesting to show, and it was also discussed from Williams, is that it was also discussed from Irving before, is that what we are considering in linear fractal mechanics is usually the first term of a kind of series development. So when we are considering the stress intensity factor, also in Irving equation, we are only considering a part of the solution and not all the solution, because the solution has also higher order terms that are more complex and are changing the exponent here. And so the leading term is a function of the stress intensity factor, and for those terms, the slope of the stress field is minus 0.5 for the crack field. But if you want also to consider more high order terms, and this is sometimes important for thin specimens, you have to develop the series considering also higher order terms. So it's also important to remember this. Actually, 95% of our applications are based on the main leading term, and we are automatically neglecting the higher order terms. But it's important to know that for thin components, sometimes the contribution of the higher order terms, and the first order terms is the T-stress, that is sometimes very important, has to be taken into account. After that, Lazzarini and Tovo in 1996, restarting from historical works by Krieger and Paris and other works, were able to find out a fantastic, in my opinion, solution for generalized notch. So considering not only a notch opening angle, but also a notch tip radius different from zero. So they extend actually the Williams solution to a notch radius that has an opening angle of 2 times alpha, and the notch radius that is different from zero, giving a very, very interesting solution. They use the complex potential method, and they apply Muschelis-Willy-Kolosov that we didn't have the time to see today, but actually is not so far from Airy stress function method. What they did, it was to, of course, they put in the notch radius. This created more complexity in the solution, so they got more constants to find with respect to Williams, but taking into account also the notch radius. But they were able to impose very, very smart boundary solutions in the PhD thesis of Roberto Tovo, and they were able to find out this final solution that has 2 parts. The first part actually is the Williams solution, and the second part is taking into account the notch radius contribution. So they are very useful, because actually with this solution you can treat in a generalized way not only the Williams solution and the crack solution, but any kind of joint with any shape and any notch radius. So of course, as a special case of this solution, you can see that we have a Williams solution, but Lazzarini and Tovo were able also to give, as a function of the notch opening angles, all the parameters necessary to apply very easily the equation in a closed form. So actually, also for a non-expert person in engineering fractal mechanics or notch mechanics, the applications are very easy to use and implement, because there are these tables that are reporting the coefficient as a function of the notch opening angles, and they make the use very, very useful. And that, of course, they define the stress intensity factor in the case of a sharp notch, but they were also able to extend this definition to a kind of generalized notch stress intensity factor that is not only taking into account the sharp case, but is also considering a round notch. So they define the kind of stress intensity factor also in the presence of a notch radius different from 0, extending Gross and Mendelssohn definition of 1972. One of the most interesting applications of these results is the study of welded joints, because actually welded joints usually fails from the weld toe or the weld root in the case of lack of penetration. So usually the two critical points for a weld joints are the weld toe and the lack of penetration, which can be considered like a crack. Okay? So what Lazzarini and Tovo did was to apply their analytical frame to this case and to express the stress field for mode 1 and mode 2 as a function of the stress intensity factor. Of course, this equation, if rho is equal to 0, is also a kind of Williams equation in this case. And they verify the validity of the equation considering finite elements and different kind of notch radius and notch depth and notch opening angle. And actually the solutions are very accurate for different kind of configuration notch opening angles. I will go back later to the design of welded joints. The problem of the approach of notch stress intensity factor when you are designing a welded joints is that if you have a weld toe and the weld root, here you have a crack and here you have a notch which can be considered with an opening angle of 135 degrees, but as we have discussed before, the notch opening angle with 135 degrees has a different stress intensity factor or notch stress intensity factor, which has a unit of measure that is different from the unit of measure of the crack tip. And so if you don't know where the failure happens, here or here, you cannot directly compare the stress intensity factor because they have different unit of measure. So this is the limitation of a stress intensity factor approach or not stress intensity factor approach for welded joints. Usually, if the weldment is well designed, the failure is always happening at the weld toe. And so, actually, you can neglect the contribution of the weld root. And in that case, the notch stress intensity factor is a very powerful parameter. But still, it has the limitation that is linked to a stress field distribution, so is mesh sensitive. You need a very accurate mesh close to the notch tip to evaluate accurately the stress field. And if you need a verified mesh, this makes the application, the computational application, very complex if you have a complex geometry. Okay. So the first to try to solve the problem of a notch using a kind of very old approach based on iris stress function was Neuber in the book of 1937 when he was only 32 years old. So he wrote this book when he was only 32 years old. And actually he tried with this complex iris stress function equation. He was able to find out this stress field exponent as a function of Q. And after that, he was able to express only, because it was very complex, only the sigma theta along the notch bisector line using the definition in Cartesian coordinate of the iris stress function. He find out this solution. Actually, this value of t is not so different from the value of lambda that is present in the Williams solution. So this solution is not so far from the solution of Williams in terms of eigenvalue. What we did later in 2009 was to modify the solution by Neuber, improving the solution, and actually we were able to obtain a very accurate exponent for the stress field, and also a stress field that was able to predict the stress field also at a far distance from the notch tip and using complex mode loading conditions. Actually, considering a comparison between finite element analysis and Neuber solution, you see that the Neuber solution is deviating from the finite elements, but what we did in 2009 with the contribution of myself and Radai was to improve the solution, making almost perfectly solution, changing as a function, for example, of the notch radius, you still maintain a very accurate solution. Of course, here it seems a very small difference, but it is 30–40% that can be very important for the final design of a component. It's not so small. So we exchanged a lot of fax because Radai was the old professor, so all the communication was made by fax. I want to also to remind a very funny episode that happens to me. He actually got a very old Mercedes with the fax inside the car and connect to the battery of the car. So we start to fight for a kind of coefficient during a trip that he made. And so actually I completely destroy his battery of the car. And after that he was completely upset with me because I sent many pages of analytical discussion and the points to him. And actually he was not able to reach the hotel during the trip. So it was quite fun. But we fight a lot for this paper, and because of course he's very German. Actually it was a very good collaboration, but it was very complicated because the topic was new, and we start to modify very well recognized equation by Neubert that was German and very famous there. So to change those equations, it was very difficult to publish the equation and to make the paper accept engineering fractal mechanics takes 2 years of work, because also the reviewer were very upset about the solution and the improvement of the solution. So actually we made a lot of round of revision with a lot of improvements, and it was quite tough. What it is also interesting is that, and it is also a very important diagram in my opinion, is that if you consider the stress concentration factor Kt, as we have seen before, this stress concentration factor, if you want to use this for design purpose, actually the fatigue life or the strength of your component, also under static loading, is decreased by Kt following this line until you reach a certain value that is Kt star. If you make an experiment over this value of Kt, actually you don't follow this line, but you don't have any sensitivity to the Kt increase. This means that in this region Kt is not working for the design because it's too conservative. So actually Kt star is giving us the threshold between the actually traditional design based on a point method and this plateau value that is making us understand that Kt is not working. We need to leave Kt and the point approach and we need to go for a fractal mechanics approach, because actually the value of Kt is increasing too much. If we use this decrease of fatigue life or fractal life following Kt decrease, following Kt increasing, we are decreasing too much the fatigue properties of the material that is not following their rules. Okay, and actually this was also interpreted in another way by Smith, Watson, and Topper in 1979 that they gave us another important information both under static and under fatigue loading. This is the interpretation under fatigue loading. I think you have seen before the delta K threshold in the Paris curve that I have omitted in this presentation. But actually, as I said before, there is a value that is a kind of material parameter depending on the threshold value of the stress intensity factor and the fatigue limit of the uncracked material, that is called A0. If you are over A0, actually you are, so if in your material you have defects that are bigger than A0, you are decreasing the material, the component life according to this law. So you are following exactly linear elastic fractal mechanics. If in your material of your component you have defects that are lower than A0, the material is not sensitive to this defect. So almost you find out that the material behaves like a kind of uncracked material, because the material is not sensitive to defects that are lower than A0. So A0 is called intrinsic crack length. So it's a kind of indication of which is the critical size of a defect for our material as a function of delta K threshold and the fatigue limit of the uncracked components. If we are below the threshold, we are in the case of actually uncracked material. Of course, nature is not making sharp transition, so the decrease is a kind of smooth transition like this. But the original diagram of Kitagawa was like this. Was a sharp connection. So A0 is giving us a threshold value. Here we are not sensitive to defect if we have defects lower than this, but here we are very sensitive to defect. And A0 of course is a function of the temperature. So if we have a lower temperature, A0 is decreasing a lot, and so actually defects that were not so important at room temperature become very, very dangerous at lower temperature. And this makes the design very complicated. And Lazzarin and Azzori in 2001 for the first time, and after that in 2005 with also Professor Meneghetti, they extend the Kitagawa diagram to make a kind of generalized diagram that in the first part is the diagram that we have seen before with linear elastic mechanics, but they add a second part that is the kind of contribution due to notch, and actually the diagram behave like this. In this second part, this part is the unnotched uncracked component, this part is the linear elastic fracture mechanics component, and this part is the notch component. So in one single diagram they were able to represent all the material, and after that they were able to use the scale factor for also taking care of the real component of the real size of your component. Actually, they apply the criterion to different materials, and they were able to summarize in a very, of course, different structural material in the same diagram, proving also the existence from an experimental point of view of the smooth transition of the diagram in this part. So after that, we also extend. This is a recent contribution. This was my paper published in 2007. We are able to extend J integral that was initially taught for the crack case also to a sharp notch, and after that to a blunt component. Of course, what is only changing is the complexity of the analytical frame, but the definition of J integral remains the same, and what we are losing, opening the notch opening angle, is the path independency, because if you open the notch, you are losing the property of path independency that is only valid for the crack case. We plot this analytically in a work published in 2007. It was more a mathematical work, but actually after that we give also some useful tool for design. And so if one wants to be fixed or want to use a J integral for design, you can find all the closed form expression also for blunt notches based on Lazzarin-Tovo solution in this paper. And actually we also were able to predict the failure in blunt notches under 3-point bending under mode 1, considering different notch depth, considering different notch radius, and we are able to predict quite well the fracture behavior under static loading with this generalized J integral approach. What it is very interesting and not well known until now, this is still an open field of research, and actually me and Professor Lazzarin, Professor Cook and Professor Kotosov have worked together on this topic, is to study three-dimensional linear elastic fracture problems, and actually some recent results that are very interesting. As I said before, usually we consider plane stress and plane strain as a main hypothesis for using, for defining the stress intensity factor and mode of failure. So we have mode 1, mode 2, and mode 3. But if you consider a finite thickness, this is changing completely what is happening locally in your component, especially if you have a sharp component. Actually, what we did in the past was to start with a very, very simple component. We start like for making a kind of trial. We start with a very simple, also because we started during my master thesis, so it was 16 years ago, and the power, I started using ANSYS 3.0, now the version is probably 19 or something like this. So we almost use a very, very preliminary version of ANSYS with very few nodes. And so we start from a very simple solution. And actually we studied the effect of the finite thickness on the stress distribution. And what we find out is that if you consider the thickness effect along the thickness of the plate, if you consider a kind of hole, usually you expect a stress concentration factor equal to 3, but in the mid plane, yeah, you have almost 3, but you can have also 3.2, depending on the ratio between A, which is the radius of the notch, and H, which is the thickness of the plate. And also it's sensitive to the Poisson's ratio. In this graph is not reporting sensitivity with respect to the Poisson's ratio. So in the free surface you can have actually a lower value, and also on the mid plane you can have a higher value of the stress concentration factor. So actually also the well-established key solution is wrong or approximate if you are considering a finite thickness for your component. Of course, you are not making a big mistake, but still, if you have an A divided H ratio that is equal to 4, you have an increase of 20% of the stress concentration factor at the notch tip, which is not negligible. What it is very interesting is what is happening if you have a three-dimensional solution in cracked components. So an extension of linear elastic fracture mechanics to three-dimensional components. We have discussed all the day about two-dimensional solution for elasticity. We have introduced K1, which is the fracture parameter, K1C or KC, that is the fracture toughness. We have discussed plate stress and plate strain conditions. But what is happening if you consider a crack where you have a finite thickness of your component? So this is the open question that we try to answer. Is changing or not changing the stress field close to the crack tip? How is changing? Which is the most important contribution, mode 1, mode 2, or mode 3? There are other modes that are coupled with the primary modes. So we try to answer to this. And actually, the overall problem is very complicated because it requires, of course, a lot of computational effort for solving the problem numerically. And because when we started this, we didn't have many computational support of tools. What we tried to do was to study a very simple problem of a disk, where we simply consider a finite thickness H, and after that we apply some boundary condition in terms of displacement around the disk, representing mode 1, mode 2, and mode 3 solution to find out what was happening locally to the crack tip when we apply poor mode 1, nominal poor mode 1, and nominal poor mode 2, and nominal poor mode 3. So what we find out is that under poor mode 1, it's like what happens with the circular hole under poor mode 1. You have a trend that is a stress field that is strongly changing along the thickness of the plate. So you have the maximum stress field in the mid plane of your component, and you have a decrease of the stress field when you are on the free surface. So of course this is half of the plate, and of course this is changing a lot if you are considering a small value of Poisson's ratio. So if you have a Poisson's ratio 0.1, so for example 0.1 is for some ceramic materials, if you the sensitivity is very small, you have almost a straight line. If you have 0.3, you have a difference between the mode 1 solution, the two-dimensional mode solution, that is 7%. If you have a 0.5, that is very difficult to have. But if you are in a condition of a polymer, that is, for example, 0.4, you have an increase of 15% or more in the terms of the stress intensity factor. So also here, it's not negligible, and you have to consider this effect. But what it is very interesting is what is happening if you consider mode 2 stress field, which is the most interesting part. So actually, what we did, it was to apply a kind of nominal shear stress to our component. And due to the three-dimensional effect of the finite thickness, what you can find locally is that you can see also an out-of-plane displacement in this direction. Actually, you are applying mode 2, but what is happening is not only mode 2, which is this configuration, but due to the thickness or Poisson's effect, you are pushing in one direction, and you are putting tensile under other direction. So what is happening is that you have also a kind of Poisson's effect close to the free surface of the plate. So locally, what you are generating is a kind of coupled mode that is called mode O, and it is called the out-of-plane mode of fracture that is not predicted by two-dimensional fracture mechanics solution. Okay? And actually, this KO, that is we call this stress intensity factor linked to the out-of-plane mode KO, is not negligible because actually applying a remote stress intensity factor of mode 2 that was equal to this, close to the free surface of the knot of the crack, quindi close to the free surface of the plate, sorry, we have a value which is very close to the maximum value that we are applying nominally. So this effect is not negligible. Actually, this explains many failures that we have from the free surface of the components in a three-dimensional components that are not easy to explain if you consider b-dimensional models. So this was a very good scientific achievement. And what we did later was to make the same. So we apply in this case a nominal pool mode 3. And what we obtain is that the pool mode 3 is also transferring to the component a local mode 2. So actually mode 2 and mode 3 are always coupled together and are generating some additional mode 2 and mode 3 locals that are locally present close to the free surface of the component. And also in this case, the value of the K3 local, the value of the K2 local was the couplet mode was not negligible. So it was a very high intensity with respect to the generating mode. So actually, we made a lot of finite element results, but what it is interesting is that we were also able to prove the existence of this couplet mode by means of some experiments that we make at the University of Adelaide in 2011. And with the digital image correlation, we were able to find out the displacement. So we apply mixed mode. First we tried with mode 1, and after that we apply also different kind of combination of modes. But actually we were fine to detect the existence of an out-of-plane mode coupled with the nominal remote load applied to the component only locally on the free surface of the components. Actually we were quite lucky because the most important effects of three-dimensional effects are close to the surface, so it's possible to detect them with optical imaging techniques. These are the results that are the most original under mode 2, and actually we find out that applying pool mode 2 to a component, we were able also to clearly distinguish a kind of displacement in the Z direction that is not predicted by any of the Irwin solution or Williams solution for the in-plane solution. And what we did also, it was to extend the consideration to notch components. So actually we simply go ahead with the same approach. We add the thickness to a sharp notch components, and actually what we find out was that also Williams solution have some limitation because they don't consider, of course, the thickness effect. And if you consider the thickness effect always and again, you have the mode 2 and mode 3 are always coupled together, and you have to consider them for the design, at least if you have a material that is very sensitive to what is happening on the free surface of the component. So we studied the same case with the sharp notch, this was the finite element model. So what happens is that again we find out that there is a strong influence of the Poisson's ratio. So if you increase the Poisson's ratio, you find an increase of the intensity of the coupled mode. And again, that the coupled mode is very localized and close to the free surface of the components. Here is the mid-plane. In the mid-plane, actually, you don't have this effect. So you have a close effect of this component, of this induced mode that is very important, close to the free surface. We also try to give an analytical solution for this couplet mode, but in this course it's only important to know that actually the traditional fractal mechanics is based on plane models. If you extend to three-dimensional models, you have also to consider this kind of effects that are now very well studied in the literature. These papers are very recent. We publish a lot of this paper from 2007 to 2015. And actually what it is very interesting is also that, of course, following the rules of linear elastic fractal mechanics, is possible to use a scale effect because we are in linear elastic hypothesis. So if you actually scale this plate in geometrical proportion, increasing or decreasing all the dimension of the plate, you can also obtain a scale dimension of the stress field, which is following the rules of linear elastic fractal mechanics for the generating mode, that was mode 2, and for the induced mode, that is a kind of out of plane mode. And so we made this kind of study for understanding if the scale effect was respect also for three-dimensional couplet modes, and in fact it was. This is the stress field along the bisector line. So actually the scale effect of mode O, if you increase the size of the component, is also increasing the stress field. If you increase the size of the components, you are decreasing the effect of the mode 2. So it's a bit difficult, but you can understand if you make a finite element model very easily. I want only to show that actually the advantage to have a linear elastic approach is that you can use overposition principle and that the scale effect is always verified. This is the most important consideration that I want to underline. Of course, summarizing, in classical theories of bidimensional fractal mechanics, we have three primary fractal modes, mode 1, mode 2, and mode 3. And of course, plane thickness is almost totally disregarded in this approach. See if the stress intensity factor is considered constant across the thickness. There is no effect in problem with stress type of boundary condition. And actually, if you consider a three-dimensional theory, you have 5 modes, 3 primary modes and 2 couplet modes. So actually the modes of fractal are not 3 but 5, because there are also 2 modes that are coupled with mode 2 and mode 3. The extension of couplet modes is strongly affected by the plate thickness. And actually there are marginal effects on primary and strong influence on couplet modes due to these effects. And also it's interesting that it's possible to predict a strong scale effect of deterministic nature considering these couplet modes. So actually, if you want to make a very accurate design, when we studied first, this approach was for a project with the aviation in Australia. And now they are implementing, because actually when you want to make light design, you are always trying to save material and you want to have an accurate design. So we developed a software based on these solutions that after that was implemented by the Australian aviation that is still using the software for design purpose, considering these three-dimensional effects. And we made this with Koltusov and Wang in 2005. This was, I think, the first work that I published after my master thesis. And actually, I mentioned before that Neuber and Radai were very important in notch mechanics. Actually, Radai was a student in Munich of Neuber, and they started also themselves to fight by fax on analytical solution when they were very young. So This fax is dated 1977. Is the original fax of Neuber to Radai. Is answering to some of the practical questions that they solve. And in this part of the lecture, I want to introduce some approaches that are useful for design purpose when you are considering notch components. I don't make much, but I want to give you some introduction to this approach. Actually, what Radai, first Neuber and after Radai made, was to try to solve the problem of a very sharp notch, so a notch with a small notch radius, averaging the stress close to the notch tip, considering a microstructural support length, which is a material property that is called rho star. But actually, so they consider that, for example, the point is not the point value of the stress concentration factor is not very important for the fatigue or fracture purpose, because as we have seen in the diagram of Frost, if you consider the stress concentration factor, you are too conservative in the design because the notch is sharp, rho is very small. And so what they try to do is to average the quantity of the stress over a material property length that is rho star. So they make the integral of the stress over this length, and the integral is called rho with a bar. But of course, if you have every time to make the integral, it takes a lot of time. So they propose a kind of equivalent fictitious notch radius to solve easily the problem. So what they consider was the real notch configuration and the fictitious configuration, which is based on a fictitious radius rho f that is defined as a function of the actual real radius of the geometry, plus a contribution that is linked to the multiaxiality of the problem, S, and rho star, which is the critical length of the material. So what they did here, you have to, in this side you have to make the integral of the stress field if you want over rho star, if you want to understand which is a critical parameter for fatigue strength purpose. On this other side, in the equivalent model, you need only to make a finite element model where you substitute the initial rho with rho f, but in this case you have a direct value which is the maximum value directly from the finite element analysis, and actually the solution is based on the hypothesis that this sigma max on the fictitious radius is exactly equal to the integral over rho star on the initial model. So it's a kind of way of bypassing the integral problem and to solve with the point method the problem of a quasi-sharp notch. Actually, the microstructural support length was discussed by Radai for different material. Actually, for steel and austenitic steel, we are in the range of 0.3, 0.4 as a critical support length of the material. And the Neuber procedure of fictitious notch rounding, of course, can be applied if you have also a sharp case, because if you have a sharp case, what you can do is simply to avoid this term that is in the initial model equal to 0, and in the fictitious notch radius approach, you have S multiply rho star. This is a method that wants actually to avoid the singular behavior, or it wants to avoid that you have to treat the singular problem of stresses that are tending to infinite close to the crack or notch tip. And actually, Radai proposed this in the standard for weldments and for welded joints. And for welded joints, the equation is rho f is equal to rho, that is the worst case condition, so rho is equal to 0. S is equal to 2, and rho star is equal to 0.4. So actually, for welded joints, for design purpose, what they are doing is to giving a fictitious notch radius that it is 1 millimeter. So if you want to design a weldment, you have to substitute the value of the real value at the weld toe with this notch radius, and you can directly read the stress field or the stress concentration factor at the point of the notch with the radius equal to 1 millimeter. And this is also reported, this is the only local approach that is accepted nowadays in the standard in force for welded joints. Actually, if you have a welded joints, what you can do is to substitute the critical points with the critical radius equal to 1 millimeter, and after that to understand which is the place where you have the maximum value of the stress concentration factor on that position, and you can actually design a weldment completely bypassing the effect. After that, we work a lot in this regard with radii from 2009 and later, and we apply the same concept to mode 2 loading. I have a report here for a kind of for giving you a complete overview of these references. But actually, after a lot of exchange of faxes and a lot of fights, we develop a method that is quite general, that is able to give you actually a kind of very good approximation of the method if you try to apply it to different kind of configuration of notches, different kind of modes, and actually the papers are reporting all the solution with all the steps. The solution, the analytical solution are very complex, but what we did is at the end summarize the results in very simple graphs that are very easy to use from a numerical point of view, and very easy tables that are reporting how you have to consider the parameter S as a function of the notch opening angle. So also a person that is not very skilled with analytical tools can always use the method for designing purpose, because we are engineers at the end, for fatigue or fracture prediction. But this method actually is completely neglecting, wants actually to completely avoid the problem of stress field with many different graphs that I don't want to mention. And we also treat different kind of notches. And after that, Radai in his book is reporting directly also the stress concentration factor for the more used welded joints, in the way that you don't need also even to make the finite element models, because you have directly the stress concentration factor just made in the book, just reported in the book. So actually you can make design of everything for design purpose. And after that, Petersen, using our findings, was able to actually make some standards that, and also reporting a lot of data of welded joints, considering a lot of data and giving some design curves that are very interesting under fatigue loading, because actually they are very simple to use and based on a very simple approach. But of course, the drawback of the approach is the big scatter that you have. This means that the approach is not very accurate, so it's still something to do. So what we did, and what some people made before us, was to actually treat the singularity in some way, and so actually treat the singularity with some approach. And the first, following Neuber, the first to make this approach were Professor David Taylor from Trinity College and Professor Lucas Usman from Sheffield University. Actually, they developed the so-called theory of critical distance, and actually they were able to consider different methods, point method, line method, and area method. So actually what they did was actually to integrate the stress field along the notch bisector line and give you a kind of, in the line method you integrate along a line which is a length of 2L. In the point method you only look to the stress at a certain distance from the notch tip if it is sharp. In the case of area, you average the stress over this volume and you evaluate the stress over that volume, the average stress over that volume. I think it's also worth to mention that before Lucas Usman and Professor David Taylor, there was an eminent researcher that made the same. The first one was Peterson in 1959 that tried this approach. After that, I think this is the most relevant contribution due to Professor Tanaka, that is quite famous in Japan and is considered the king of notch in Japan. And after that, there is also a Poland professor that is Severin, that made, a Polish professor that made the same. This is an extract of a paper from 1984 of Tanaka. And actually the idea of averaging was not first proposed by Susmel, but taking advantage of the, or Taylor, but taking advantage of the work by Neuber. Professor Shepard in 1991 proposed the idea of averaging, but she proposed to average in a very strange shape, a triangular shape that is not very significant for designing purpose, and it's also very difficult to manage from a computational point of view. She is now working in Stanford for many years, and the paper that where she has reported this is date 1991. This is the original book of Neuber, where he proposed the raw star application. This was Neuber, and this is the book in German from 1985, which is the last book that he wrote before he died in 1987. And this is the contribution by Severin. Actually, the point method, the line method, and the area method are well studied by Lucas Susmel and Taylor, that have actually made a very good work of synthesis. And I think one of the most relevant papers, if you are interested in this topic, is this one published in 2008, where they were able to apply this kind of theory of critical distance to brittle failures of polymethyl methacrylate, and considering mode 1 and mode 3, and also mixed mode 1 and 3 in combination, that was quite new at that time in 2008, and they obtained very good results in terms of predictions, with some peak in the errors, but not a big mistake. I say before that weldments are always a kind of extension of sharp notch. So we have, if you consider a weldment, if you consider that usually in a weldment we have a notch opening angle of 135 degrees, and at the root we have a notch opening angle equal to 0, so we have a crack, or we have a notch opening angle that is 135. We can apply the notch stress intensity factor for design purpose, considering the stress singularity. The problem is that, as we have discussed before, we have different units of measure here and here. So usually the notch stress intensity factor is very powerful if you have failure only from the notch, from the weld toe. Usually, if the weldment is well designed, we don't want internal failure. So actually, we want always to detect the initiation of cracks from the outside. We don't want that the crack is starting from the inside. So usually, if we are making a good design of the weldments, the majority of the failures are happening from this point and not from this point. So actually, what Professor Lazzarin and Tovo made in 1998 was to try to study different welded joints with different main plane thickness ranging from 6 mm to 100 mm, and the transverse plate thickness ranging from 3 to 200 mm, so a very wide range of size. If you try to summarize these results in terms of the nominal stress, you have a very huge scatter in terms of nominal stress. All the failures of these components were happening from the weld toe. If you try to summarize the results considering the notch stress intensity factor at the weld toe, you have a very, very narrow scatter band. This means that the notch stress intensity factor is a very powerful tool for designing a welded component if the failure is occurring at the weld toe. And also they extended this to aluminum components later. So actually it's not only for steel but also for aluminum welded joints. But what we tried to do later was to generalize the approach also to different kind of failures. So actually sometimes we have some components that are failing from the cracks, also welded joints that are failing from the lack of penetration. So we try to get a more general approach. And so we develop a strain energy density approach, taking in mind that the first very interesting approach was due to Griffith, but actually the first to try to make a based on energy approach was Beltrami, an Italian professor that works in 1985, and he published a work only in Italian, in Istituto Lombardo of Scienze. And it's very interesting because he published 4 books on these topics that are not very well known because they were only in Italian, but that was the first trial to apply based on energy approach. After that, of course, there are many other people that have tried this. This is the picture of Beltrabi and a bit of history of him. But actually the advantage of the local strain energy dense approach is that it automatically, now I will explain a bit this approach, but the aim of this approach is mainly based on 2 considerations. The first consideration is that if you have the notch stress concentration factor, you cannot compare notch opening angle with different size. So if you have a notch opening angle of 90 degrees and a notch opening angle of 135 degrees, you cannot directly compare the values because of shifts, because they have different unit of measure. And the second point is that the notch stress intensity factor is based on the stress field close to the notch tip. This means that is a stress-based approach and not an energy-based approach. So this makes the computational efforts much more higher because you cannot use coarse mesh. You have always to use a very fine mesh close to the notch tip. And actually, what Lazzarini and Zabadi did first in 2001, and after that we extended many other applications later, was to develop a kind of parameter that is called R0. It's a reminding of the rho star value of Neuber, so it's a kind of microstructural support length that is called rho star, and here is called rho 0. But the idea is not to use a stress average in this volume, but a strain energy density instead of the stress for designing purpose. Actually, we are merging together a kind of theory of critical distance plus the consideration of a microstructural support length of Neuber. I don't want to give much more explanation, but actually the strain energy density inside the control volume is a function of the stress intensity factor of mode 1 for the notch and the stress intensity factor of mode 2 of the notch, multiply the radius r where you are averaging this quantity. So it's a very close, a very simple equation, and is connecting the strain energy density average in the control volume to the stress intensity factor that you can measure. So actually it's a more powerful tool, and the advantage is that the strain energy density has always the same unit of measure independent on the notch opening angle. So you can compare directly actually a notch with a notch opening angle of 135 degrees and the crack case, for example, without any problem. So you can consider this kind of notch and this crack, and you can always very easily compare the results. R0 is the control volume radius of the material. I will give you the definition later. And actually delta K1 is because we are thinking this equation for fatigue application, so we always use the range of the delta K. But E1 and E2 are only a function of the notch opening angle, so it's very easy to evaluate them if you have these simple expressions. So they are only a function of 2 times alpha. And this expression actually can be used using a simple calculator. And after that we extend also the same consideration to a blunt notch, not only a sharp notch. And if you consider a finite element, you can see also that the shape of the contour lines are very, very similar to the shape of the contour volume of the control volume that we have selected, actually parallel to that. So this means that the model has also some physical reasons to be very good. So we apply the same concept to mixed mode loading. So we consider the maximum tangential stress approach, so a kind of local mode 1 approach. We consider that along this bisector line we have mainly mode 1 loading. So what we did was simply rotate the volume under poor mode 1 to a volume like this, maintaining the length R0 for both the volumes, is simply rotation of the volume. So the method can be applied also to mixed mode conditions. And we define the control value of the radius R0 as a function. So for defining the control radius under static loading, you need two fundamental parameters. You need the energy of the material for the unnotched material, and you need the energy of the material for the crack material. So you need the test from the unnotched specimen and the test for the crack specimen. If we consider as a critical parameter the energy for the material, what we actually have is that we have to consider that the energy for failing the unnotched material is the same energy that we use for failing a crack material. If you equate these two equations, it's possible to obtain R0, which is a function of the Poisson's ratio, is a function of the fracture toughness, is a function of the ultimate strength of the material. So actually, it's a very simple closed form expression that is giving you R0, that is a material properties, as a function of some simple test that you can easily make on standard material and also complex materials. We try to apply the approach to different configuration of notches, and as a function of the notch radius. Was made in collaboration with Professor Elises and Professor Gomez in Madrid. At the end, we were able to make a synthesis of more than 1,000 results made from us and taken from the literature, about 900 results, where actually the critical radius was ranging from 0.4 micrometer to 500 micrometer. Actually the ultimate strength of the material was ranging from 2.5 to 1,200 megapascal, so from a kind of very soft polymer to almost a ultra strong steel, with a fracture toughness ranging from 0.15 to 55 megapascal multiplied square root of meters. So a large variation. Mode 1 and mixed mode load were included in this cutter. So the results were quite good. And also we applied this to graphite under mode 1 and mode 3 loading. Actually, this was the first time that we applied the strain energy density criterion also to mode 3 loading. And of course, we also applied the same consideration. First, to the data that Lazarin and Tovo obtained in 1998. We defined for the weldments with the same consideration that we made before for static loading. We actually consider a welded material without any geometrical discontinuity, and this is the critical radius. So the energy of this component has to be equal to the energy close to the notch tip for this component. So the energy of the unnotched component has to be equal to the energy of the notch component for determining the value of the critical radius. So you need always two information. In this case, we were thinking to fatigue, so we were referring to the critical value of the notch stress intensity factor at 5 million cycles, for example, and delta sigma A is the value of the unnotched material at the same level of number of cycles. In the literature, you can find that these two numbers are this one. This is the value of the critical value for the unnotched material, unnotched weld material, and this is the value of the critical stress intensity factor, critical notch stress intensity factor for welded joints. Actually, considering failure from occurring from the weld toe and weld root, we were able to summarize more than 900 fatigue data for weldments in a single scatter curve that can be now used for design purpose, at least for steel, if you consider a critical radius of 0.28 millimeter. So, which is the advantage of the approach is that you can use very coarse mesh. So you don't need a very refined mesh for making any calculation. But actually, if you consider this is only a plane case, so a bidimensional case, but if you consider 35 elements in the entire model and 5 elements in the volume close to the notch tip, you can actually evaluate the strain energy density very accurately. If you consider the notch stress intensity factor, if you want an accurate value of the notch stress intensity factor, you need a very fine mesh like this close to the notch tip, which is very, very heavy if you consider three-dimensional models. So we actually give some guidelines in a paper published in 2007 and also in a paper published in 2010 in how it has to be made, the mesh close to the crack tip to make efficient the method. And after that we apply to different configuration. What it was found out is that considering a fine mesh, you have this value of the notch stress intensity factor. And considering a coarse mesh, a posteriori you can derive the notch stress intensity factor, deriving the stress intensity factor from the strain energy density. And the mistake that you have, or the difference that you have, is very small, so it's almost 3-4% in terms of notch stress intensity factor if you use a very coarse mesh with respect to a fine mesh. So this is very efficient. Of course, this method is very powerful if you use it for a three-dimensional component. You can use a very fine mesh like this close to the notch tip, and you can evaluate the three-dimensional the energy density in a three-dimensional model very easily with a very light model. So we compare, for example, mesh 1, mesh 2, mesh 3, mesh 4, mesh 5 with different increase of the size of the volume of the elements. We reach the extreme case of 4 elements in the critical radius are 0. And if you compare the results, if you put more than 1,000 elements inside the volume and 4 elements, you have a difference that is 2%. So it's a very efficient method. Actually, we use the method for designing the Panama Gate. So in 2015, we start this project in collaboration with Simolai, that is a big industry in Italy making large civil construction. And also the transportation was made by sea. What we did was to actually we were able to actually the Panama Gate was composed by 8 of these gates, and every gate has 50,000 weldments plus 1.3 million of notches. So, and these gates are subject to fatigue because also the transportation was made from Europe to the Panama Gate using this ship with waves in the sea of 10 meters that were cyclic loading to consider in the design. Okay. And we developed a very interesting tool that is based on artificial intelligence and neural network that is able, and machine learning, that is able actually to design in an efficient way. Is also able to remember previous details that were just considered in the design without repeating any finite element, not useful simulation if the details of the weldment was considered before in the computation. It was the first time that we applied this. If actually when we started the project, there were almost 30 engineers that were dedicated to the design of the gates. And what they did was to design every single nodes, critical nodes, one by one. But with this automatized model, we were able actually first to make a macro model of the gate to detect the most critical point of the gates, and after concentrate our attention only on the critical nodes of the structure and not to all of them, because sometimes many of them are without any load. And this is other application for ships. We work together with Hamburg University, where they have a very strong history for ship design, and we apply to the energy approach to these kind of details that are quite strange, with very good success, because the master curve that I have shown before is the red lines, and all the data for three-dimensional model are exactly falling inside the scatter band. So the master curve is respect also for these kind of details that are quite complex. Actually, if you want to understand or to read more about this, there is a recent works by Professor Dieter Radai and Michael Worman that is called Advanced Methods of Fatigue Assessments, that is reporting all the basics of notch mechanics and is also reporting a lot of the consideration that I made today regarding the approach. Actually, we support Radai right in the book. We are mentioning in the introduction, but after that it's always useful that other people are saying that what you are proposing is good, because if I'm saying that I'm proposing something good, I'm not trustable because it is my approach. But if the German school start to believe that this method is useful, I think that is probably useful. And actually, we also summarize in a recent paper. This was the best paper that I wrote with Professor Lazzarin in this journal with impact factor. I think you are familiar with impact factor now. This journal is an invitation. They make an invitation only to special authors, and when we publish in the journal, it got an impact factor of 30 almost. So it was a very high impact factor, and actually they dedicate a complete issue to a paper. So we made a 50-60 page journal paper, and the issue was also reporting in the cover our tests. So it was quite nice, and also they pay me, I think, 600 euro per page or something like this, or probably less, but no, I think 600 euro to all the, but I also received a kind of honorarium for writing the papers, which was the first time in my life. And I wanted to close this lecture with, because actually what we are considering is in fracture mechanics are mainly defects, cracks, and notches. But this is very relevant if you consider additive manufacturing, because nowadays I think more of us are speaking about additive manufacturing and three-dimensional components, 3D printing, both in polymers or in metallic material, steel, Inconel, or titanium alloys, so we can print different kind of components. And what it is very interesting is that all the tools that we have seen before and all the analytical solution that we have seen and all the approach, including the strain energy density, can be adapted to the additive manufacturing design in a very smart way, in a very quick way. So we don't need to reinvent the wheel, but we can really use some of the previous concepts that we have developed. Of course, what it is critical for additive is that sometimes you have a notch, and close to the notch you have a defect that is induced by the process. In that case, the problem becomes more complex. But I think it's possible to treat it, because the overposition principle is possible if you don't have a large plasticity. And if you are working especially at high cycle fatigue, the plasticity is not so big. So what we did is to start to play a bit with the topic. We made different kind of notch configuration, a notch specimen, semicircular notch, a V notch with the notch radius of 1 millimeter, a V notch with 0.1 millimeter, and also we plot the fatigue curves showing the size of the defects that we find in the component. So we are not only plotting the stress level, but also for each shape of for each Euler curve, we are also reporting almost the size of the defect that we find in the component. I think is a nice representation. And we try to propose a kind of diagram to understand for no-notch, blunt notch, sharp notch, and crack, what is happening in terms of failure, in terms of mechanism. And after that, we also try to apply the strain energy density. We consider only mode 1 at the moment because the topic is quite new, but actually the results are very promising, and it is very evident that the strain energy density, if used properly, can be a very good tool also for predicting the failure of under fatigue loading, at least under linear elastic condition for these materials. Of course, this is an engineering approach. I don't want, if you want to study the mechanism of failure to understand the physics behind this, it's a very complex tool. If you want to design and give to an engineer which is the stress level that you can have at a certain number of cycles, you have to accept an intrinsic scatter, and I think it is what we can do as engineers. So I'm an engineer, I'm not a physicist or a mathematician. I want to have at the end something for some tool for designing purpose. And we also change different materials, so we are working on titanium. Of course, the process is affecting a lot of the surface roughness, and what it is also important to consider is the residual stress effect that you have close to the surface for these components, for these materials. But I think with post-treatment that can be mechanical or HIP, so hydrostatic pressing, you can actually reduce the level of porosity, and you can also making post-treatment for releasing the stress, the residual stress, so you can actually apply very easily a concept that we have developed before. I want to close this lecture. I was actually quite lucky and proud of my career, because I was so lucky to meet a lot of interesting persons in my life. Actually, first I want to thank Professor Lazzarini. I worked for him and with him for 15 years, starting from a course that he taught to me in 2001, and after that we worked together until he died in 2014. This is Professor Murakami. We made this picture in Trondheim when we went to the European Conference on Fracture in 2014. This is Professor Adai. I met him in Vicenza when we invited him in 2011. This is Professor Sia. I organized with him several conferences on mesomechanics. This is Professor Tanaka. This is John Hutchinson. This is Paul Paris in this hotel in 2014. This is Jim Rice. So this is Ali Fatemi. This is Leslie Banks. This is Yoshi Ong. This is Ali Fatemi, is very famous for multi-axial fatigue. This is Professor Lazzarini, me, and Professor C and Professor Risitano in Vicenza, in my own city. And so I think, as I said before, this lecture is not only for teaching you something. I think probably I was very quick, but at least you have a lot of materials, and I think if you want, you are welcome in Norway for collaboration. Some of you guys have just visited me, so I'm quite happy about this. Some of the disadvantages of Norway is that this is the summer time, so it's not very good, but the advantage is the typical Norwegian family for male. For par condicio, I have also put this for girls, because we have a very good gender balance. And so this is the end of my presentation, and thanks a lot for your kind attention. I made a long presentation, but I hope it was useful. I think tomorrow you will be more focused. You will be more focused on different topics. Okay, thank you so much.
Thank you, Filippo. And well, let me first say, whenever I go too fast, or whenever you understand something, just wave your hand, or when you have a question, please ask. And remember that there is no such thing like dumb questions or stupid questions. They don't exist. Usually they are the questions that put the lecturer most at ill ease, because he doesn't know this or she doesn't know this. So don't hesitate to pose them. Now I would like to talk a little bit about the role of simulation in general in behavior of structures and materials, and I will focus obviously today or here on fracture. And broadly speaking, there are two approaches to the simulation of fracture. You can do it in a discrete way, or you can do it in a smeared way. I will come back to that. Today, we will be talking primarily about smeared concepts. And I will also talk a little bit about the deficiency of what is sometimes called the local approach to fracture. Now, to not immediately plunge you into the deep, that's my pointer, of course, in my pocket. To not plunge you immediately into the deep, I first want to tell you a little bit about philosophy. Of course, we are here in Sicily with a large tradition of philosophy, and we're not so far from the ancient Greeks which colonized Sicily, and people like Archimedes made big scientific progress here. So, when we go to the ancient Greeks, there's essentially the Plato school versus the Aristotle school. And Plato was a proponent from the following. He said, well, you have a certain concept, and from that you derive something else, and from that you derive something else. This is called deductive reasoning. Out of a theory, we derive a specific proposal for certain things. Aristotle had a different idea. He said, no, we do an observation, and from that we build a theory. So essentially it's the inverse process, because from a single observation, nowadays we say, from a number of observations, we make a theory, and this process is called induction, and it's another cornerstone of modern science. Now, we jump 2,000 years. Not so much happened in those 2,000 years until we came across a couple of scientific giants. René Descartes and Sir Francis Bacon. And exactly, they went in the footsteps of Plato and Aristotle. René Descartes, he was a mathematician, and he was further developing Plato's method, namely the method of deductive reasoning. You have an idea, and from that you derive a concrete theory. It was called Plato's theory of ideas. So, we have an idea, in the words of Plato. We have a different word for that. We use a Greek word, hypothesis. You have a hypothesis, and from that you have systematic reasoning, and you derive conclusions from that. Roughly at the same time, with Sir Francis Bacon, the father of the empiricism, which means we have observations, and then, along the lines of Aristotle, based on these observations, you can develop a theory. So, obviously, these two things are complementary. And you have here the pillar of the theory. Here you have the pillar of experiments. And of course, they mutually influence each other. From a theory, you can deduce certain conclusions. You can verify them with experiments. And then, with experiments, you can, again, see something is right, something is wrong. And you can then refine your theory by induction again. So, we have here this two-way street, which has been the foundation of modern science up to, well, let's say, mid-19th century. And then something changed, mid-19th, early 19th century. Because in the meantime we had Newton, we had Leibniz, and they had developed differential equations. Differentials, integrals, differential equations. And as we all know, in engineering and natural sciences, many of our phenomena are captured in terms of differential equations. So now we went from a two-polar system into a three-polar system. Because before you could make conclusions, you had to do some analysis. So you did experiments, you derived a theory, but the theory is framed in terms of differential equations. So you have to do analysis before you can have your answers and draw conclusions. Well, this is fine. However, we all know that we can solve differential equations on nice squares or something like this, or a cube or so. But for our engineering structures, they're useless. They're not so useful, always. So, here is how essentially the role of simulation comes in. Simulation replaces analysis for complicated geometries, for nonlinear systems where analysis has no closed form solutions. So essentially you can say simulation is next to experiment, next to theory, the third pillar in progress in modern science and engineering. So this is why I think that simulation in fractional mechanics has some relevance, and that we there stand essentially on a very long history. Now I come back to what I said in the beginning, very briefly on the first slide. Discrete versus smeared model, or discrete versus smeared approaches to solving. Now, if I ask you, is your system continuous or is it discontinuous? You may probably all give me a different answer. Who thinks that our systems are continuous? Raise your hands. Oh, so the rest, you all think it's discontinuous. So you all go back to Democritus and think that the world is made of atoms. Well, I don't want to haggle with the particle physicist, but maybe if you really go deep enough, the world is discontinuous, made of all small particles. For me, that's not the question, that's not the issue. The issue is, what is the level where it is meaningful and possible, also possible in terms of computational resources, to make a model of a discontinuity. And that can be that the model is a smeared version. I mean, we all use continuum mechanics. While we know that there is nothing like a stress. Who can measure a stress? I can't. I can measure a displacement. From that, I can derive the value of a force. But I cannot measure stresses. Stresses are a concept based on the notion of a continuum. So, the choices we have is for a certain application, depending on the level of observation we want to choose, is a smeared approach more appropriate? Or is a discrete concept more appropriate? And that depends on the physical phenomenon you want to model, but also sometimes on the complexity of the software you have to construct. Just to go very fast, discrete approaches may be intuitively appealing to you. Because, okay, if you fracture a body, it's two parts, and you clearly see the topological change. In 2 dimensions, that's fairly simple. Okay, that's still possible to program, but to program 3-dimensional fractures, simulation of that, well, already from the bookkeeping task, it's a very horrendous task. So, it's the physics that play a role, but also what is just doable to do. So, how to capture discontinuity? That's the question in simulation of fracture. Well, 2 ways, basically, discrete way or smeared way. The discrete way, of course, as I said, is intuitive. I mean, a fracture is a fracture, and at the end you have 2 bodies. But when you go to computational things, you get issues like remeshing. I mean, for instance, when you have meshed a body with a finite element mesh, the fractures are never going to run along the boundaries of the inter-element boundaries. So you don't want to be constrained by that. So you have to do some remeshing there. 3-dimensional things. I mean, cracked fronts can be very complex in shape. To capture that is not that easy. On the other hand, smeared approaches are relatively easy to implement, but we have a number of issues there. Cohesive zone models for fracture, nonlinear fracture models. How do we do it? How do we do things like multiphysics, where you have not only a mechanical problem, but for instance also, like in hydraulic fracturing, a fluid. And you have the problem that, as we will talk about, if you just translate your degrading strength into a stress-strain relation, you get a phenomenon which is mathematically called ill-posedness. And you think, okay, that's a mathematical problem. Well, not quite so, because the mathematical problem translates into numerical solutions that are physically meaningless. So, what we will do is we will discuss, and that's mainly today, modern smeared approaches to fracture, their relation, merits, and question marks, because we are not yet there. It will be quite a while before we, if we ever come there. And it's mainly tomorrow, provide an overview and assessment of the possibilities of modern discretization technologies. Of course, we all know finite differences, we all know finite elements, but there's more out there. And I will talk about what's more out there as well. Not to make you an expert in those, but to at least make you aware that there is more out there. Okay, smeared concepts. Essentially, when I look into a fracture, orthogonal to the fracture, I have here a displacement, and then essentially I have a jump in the displacement. In a smeared way, you would like to distribute this jump. And there are 2 ways to do that. One is you use the discretization, and that's the engineering approach, which can often bring you far, but is not correct. And the regularization approach, which is the neat one, but it's a little bit more complicated. So essentially, what you do here in the discretization approach is that you say, okay, I here have my jump in displacement, which has a zero width, because the crack is defined to be essentially having a zero width, at least originally. And I distribute that over a finite width W. So you smear it over a finite width. And the simplest approach is that you say, okay, I use my finite difference grid or my finite element grid to define W. So we have a bar of elements, we pull the bar, give one element the imperfection, that element cracks, and essentially the width of that element is then setting, or the size of that element is setting the width over which you get the fracture. Here you enrich your model. You say, okay, apparently my standard continuum mechanics model is not applicable to this case. So I have to change my standard continuum mechanics model. And that's possible. There's a whole range, a host of models that can do that. And essentially, what those models do is they introduce in the constitutive equations something like an internal length scale. I mean, look, for instance, into linear elasticity, as you know it. In isotropic case, you have a Young's modulus, you have a Poisson's ratio, but you don't have a parameter with the dimension of length. So it's impossible to introduce something of this W from the constitutive equations. Now, imagine that we have always been taught, let's say in the first and second year of our mechanics courses, we have a force acting on a square block, and we have stresses on that. They are varying a bit. We make the block and block smaller, and the stresses become homogeneous. That was taught to us. Well, this is a hypothesis. It's an assumption. The next, a little bit less restrictive, is, for instance, an assumption that our stress does not collapse to a homogeneous stress, but to a linear varying stress, which would be statically equivalent to a normal force plus a bending moment on this elementary quadrilateral. And a bending force gives you, of course, a curvature. And the relation between the curvature and the bending moment is a bending modulus. But now you have something nice, because now we have here a bending modulus in addition to a Young's modulus. And when you divide the bending modulus by the Young's modulus, you have a parameter with the dimension of length. So you have to relax the restrictions of standard continuum mechanics in order to introduce length scales into your model. So we'll come back to later to it. Now we'll show what this can give to you. And we go to a very simple case. I already talked about it. We here have a bar, one-dimensional. We load it by a stress here. We divide it in m elements. And we keep it simple. It's just 4 noded elements with a linear displacement interpolation. So the strains are constant per element. And we define a constitutive relation which is linear elastic until the tensile strength and then degrades, for simplicity's sake, linearly. So pre-peak we have stress equals Young's modulus times strain. Post-peak we have stress is the tensile strength plus the softening modulus here, h, slope of the curve, times the difference between the strain and the strain at which fracture occurs. So, a simple model. Now we are going to do a mesh sensitivity study. And, well, for this simple case, you can do that by hand. You can derive a closed form solution. And you can derive, very simple, the back of the envelope, an expression for the average strain. So the average strain is stress divided by Young's modulus, plus an expression which involves the Young modulus and the slope here. And here we have the difference between the current stress, the tensile strength, divided by the number of elements. You can rework this a little bit if you define M as the ratio at which you have complete failure, the strain at complete failure, and the strain at which the peak stress occurs. You can rework this average strain over the bar, so the end displacement divided by the length of the bar, as sigma over E times N over M, Ft minus sigma over E. Now see what happens for this point when you have calmed down completely. Well, at that point, stress is 0. And we have just M times the strength divided by M times E. Now, our Young's modulus is a material constant. Our tensile strength is also a material constant. And it's the ratio of Ku over Ki, essentially the ductility of the material. It's also a material constant. So, what we have here is that your average strain is inversely proportional to the number of elements. You have always been taught in finite element classes that when you refine a mesh, the answer should converge to the true solution, to the analytical true solution. Now, see what happens here. When we bring M to infinity, and that should be the real solution, then you divide by infinity, and your average strain becomes 0. So, what you do then is for an infinitely dense mesh, you go up to the peak strength, and you go back along this line to this point. Is this the true solution? Yes, it is. It's just, this is the true solution for this model. It's not so that there is something wrong with the numerics. No, we've done it all by hand, and this is exactly the case. But physically, something very weird is happening. Because we go here up, and down. And we have always been taught that the area, or the area here under the curve is your dissipated energy. So the area of this up and down back here is 0. So you have here the, let's say, interesting case of failure without energy dissipation. And this is not a defect of your numerical model. It's just a defect or shortcoming, or better, that you've come to the limits of your standard continuum model. A standard continuum model cannot simulate failure in a smeared way if you don't explicitly put some extra in. So just the extended continuum model, try to have softening in order to put failure, and it doesn't work out. Essentially, what you do is, I would measure a force displacement curve, something like this. I divide force by load by area to arrive at stress. I divide displacement or element displacement at the end by the length of the bar to arrive at strain. And then you construct a stress-strain diagram which you use as input. Well, this is wrong, because also it ignores that in experiments you can never keep a homogeneous deformation until the very end. I mean, you always get some localization of the deformation, which ultimately culminates into a fracture. Well, here you see a finite element solution showing exactly this behavior. So what we have here is a very fine mesh of a silicium carbide carbon fiber reinforced specimen. We put a stress here and a stress here. And you see, for a coarse mesh, you get something like this. For a fine mesh, you get a decreased load and a much more brittle behavior. And for the finest mesh, you get something like this. And at this point, you have failure to converge. And this failure to converge is not because we have not enough sophisticated solver, or because we have made some errors in our programming. It's just because we are here trying to solve an ill-posed problem. And if you're doing that, trying to do that, you get always computability issues. It's always at some point hitting. So it was a bit easy, it went a little bit more difficult. We go now into the mathematical issues why this is happening. All still crystal clear? Good. Now, who knows what is stability? We have in mechanics the notion of stability. Who knows that? What is stability? Well, I'll tell you, in 1773, D'Alembert and Diderot published the famous encyclopedia. And they had a bit of a weird idea about stability. They said, well, stability is something that is rigid, unmovable. Well, we would not say that. But in fact, stability is one of the most ill-defined notions in mechanics. For elastic materials, materials at infinitesimal strains, you can have a rigorous definition. In the Lyapunov sense, which means that if you don't want to have a large disturbance, you must make sure that, stability is that if you give disturbance to the system, it damps out. For most cases in mechanics, there is not such a good mathematical definition. So what we mostly do is we adopt what Hill has proposed as definition of stability. In this case, for material instability, saying that the inner product of our strain rate and our stress rate is greater than 0. Means obviously that when you go up, that you have stability, but when you are going down, softening, you have no stability. Because then you have an increase of the strain rate, but a decrease of the stress rate. Now, if you have material models that are so-called incrementally linear, which means that there is a linear relation between the stress rate and the strain rate. So you can just write the stress rate as a stiffness times the strain rate. You can replace this by this. Problem is, there are almost no material models which are incrementally linear. Also, well-known models like damage models, all plasticity models, they are not incrementally linear. Because they always write down that you have a stress rate equals, for instance, a stiffness times a strain rate. But there's always a nonlinearity. Namely, we have loading and unloading. And there's always a loading-unloading condition. And you never know which one applies. So it is always nonlinear. Nevertheless, we assume that you can do that. Another assumption. And we arrive at this condition. Now, this is quadratic form. So this means that this fails to hold if the determinant of the symmetric part of this stiffness equals 0. And in the same way, we can define structural stability just in a product of strain rate and stress rate, but now integrated over your entire body. So it's getting a bit more complicated now, because now we're going to discontinuities. Fractures, for instance. And on a plane with a discontinuity, like here, which has a normal n of the discontinuity as d, we have a jump in your traction which equals the normal times your jump in your stress rate. And now again, assuming that we have this incremental linearity, so this so-called linear comparison solid, we can transform this into the jump in your traction rate across your discontinuity equals your normal times your stiffness. We have assumed that both stress rates are related to the same stiffness, which is an assumption, times your strain rate. We now look specifically into displacement fields that have a jump. So our displacement field is one continuous displacement field plus a jump here times another field. Now, if we substitute this, if we differentiate that both in space and in time, we arrive at a strain rate field, which is the symmetric gradient of this field, plus our Heaviside function times the symmetric gradient of this velocity field, plus the derivative of your Heaviside function times this, times the normal, symmetric. And the derivative of this Heaviside function is your Dirac delta function. This is a bit of distribution theory. So you have this, and we now have our, so this, we have this. So this is the unbounded term here at the discontinuity. So here our strain rate difference goes into the sky. But we can substitute this into here. So for this we substitute here, and we obtain that our jump in our traction rate equals this unknown scalar, can be any value, times our normal, remember there was one normal here, times our stiffness, times again the normal which comes here, times our added velocity. Now, when does this become singular? Well, this becomes singular when the determinant here is equal to 0. So this is called the acoustic tensor. And when this acoustic tensor becomes 0, you lose what they call elasticity of the system. And that is exactly what happens in this very simple example of a bar at this point. In this special simple example, we lose here material stability, which is not a big problem, but the biggest problem is in this case, it also makes it possible, and in this case it is really happening, that you lose elasticity of your system. Now, material stability or structural stability is not that big of a problem. You can compute. We are all used to computing, for instance, buckling phenomena. If we have the Euler strut, at some point, at some load level, it can buckle away sideways. And we can still go on computing. Even though we have lost structural stability. The thing is, when you lose stability, you have the possibility of more than one solution. When you lose elasticity, you have the possibility of an infinite number of solutions. Well, when you have 2 or 3 or 5, at least a countable number of solutions, your nonlinear solver is still able to find one. When you have an infinite number of solutions, usually it gets lost. And this is the basic issue, what happens with computability of systems that have lost nilpotence. So this is something that always worries me. Now, if you have small displacement gradients, loss of material stability must precede loss of elasticity. So as long as you have material stability, you don't have to worry, you can compute, and everything is fine. Life is easy. If that's not the case, then you may have this as well. If you have large displacements, life becomes more complicated. because large displacements may also cause destabilization. And then you have the possibility that material stability and structural stability interact. And both can contribute to the wrong way, to the bad side. They can also, one can go to the bad side and one can go to the good side. So that's very difficult to say. It is boundary value case dependent. Well, for this simple case, you can show it. You just substitute your discontinuous trading field in your condition for loss of material stability. You then get this. Now, your left-hand side vanishes again for arbitrary displacement fields if and only this happens, which was just your symmetric part of your acoustic tensor. Then you are held by some theorem of linear algebra, which says that the eigenspectrum of the acoustic tensor is bounded by that of its symmetric part. So that means that your symmetric part will always be first compared to the full one. So you can never have loss of this prior to loss relativism. So now so this is when you do it via discretization. And you can trick it a little bit. And you see that often happening, that, and I should have made a slide for that, but okay, that people say, okay, I add an additional material parameter, namely the fracture energy. And that's a normal parameter, of course, in fracture mechanics. So what I do is the fracture energy, which is normally defined as the amount of energy which is needed to create a unit area of fracture, you smear that out. So you translate it into something per unit volume. And then you have something which you can relate to stress strain. And then this quantity is the area under this curve. So you introduce this as an additional material parameter. And if you do this calculation again, you will find out that you can get mesh-independent solutions if you introduce this and make this area your fundamental parameter rather than the slope h. Because in that case, this slope h becomes a function of this energy. And epsilon bar becomes again a unique non-zero value. And you have guaranteed that for this simple boundary value problem, you have again a unique physically relevant solution. But, and in this sense, you can have lots of solutions that are, in engineering sense, very relevant. However, the basic problem, namely that you get loss of elasticity at some point, is not repaired. For instance, when you look into dynamic problems, we take again this problem. We put a wave into it. We hit it here. or better here. So a wave starts traveling. We make the intensity of the wave such that it is a little bit below our fracture point here. So it hits the wall here. It doubles in intensity. It exceeds your fracture strength. So at that moment, you get a fracture here, in this element. Now, remember, at that moment, your slope becomes negative. The phase velocity, the velocity of your traveling wave, equals the square root of your stiffness over your mass density. In the elastic regime, the stiffness is Young's modulus. So you have the square root of Young's modulus over mass density, and that's all fine. In the inelastic regime, this becomes the expression of the stiffness. And at some point, and well, E minus h is positive, but E times h is always negative. So you have a negative number for the stiffness divided by your mass density. And the square root out of a negative number is of course imaginary. So you get imaginary wave speeds, which is physically nonsense again. So by prescribing the fracture energy in a volumetric sense, you repair, in an engineering sense, the problem that you remove some of the worst deficiencies. But mathematically, the problem still persists. And when you go to more complicated boundary value problems like this one, or to dynamic problems, you get all the mess back. So in that case, you have to go to what I call proper regularization techniques, where you enrich your continuum in order to make it well posed. Now, you have a number of approaches, and we will go through them, that can do that. One of them is rate-dependent models. Many materials have some viscosity. And when you introduce viscosity, you introduce a time scale. And a time times a certain length is a length scale. So through that, you also introduce a length scale, and they can help to get your problem fixed. You have so-called non-local theories, and after a brief break we will delve into those. Essentially the idea is we always have a point continuum considering. This means that the stress in this point depends through a constitutive relation on the strain in that point. We can also say, okay, that's too simplistic. We make it dependent on the strain in a certain surrounding of this point. Or we can say we make the stress not only dependent on the strain, but also on its gradient, or even the second order gradient. We have Gauss-Rho theories, which introduce not only a tensile force, but also a bending moment on an elementary particle. For instance, when you think of granular materials or blocky rocks, that's a very physically relevant model for those. Because the level at which you would consider them is below the level at which you would consider is different from the continuum mechanics level. For instance, when you look into rock falls, as you can see in rocky masses, or in shear bands on a beach or something like this, typically the number of grains that is involved is smaller than the minimum number of grains you would need for the assumption of a homogeneous stress distribution. You have phase field models, which are very much related to gradient theories, and we will talk about them tomorrow. Now, the bottom line is that all these strategies introduce, in one way or the other, an internal length scale. For instance, in these non-local theories, the area over which you average gives you a measure of length. Here, with the Cosra models, the quotient of a bending modulus and the Young's modulus is something with the dimension of length. Now, the other side of the medal is that because you have an internal length scale, you not only make the problem well posed, and therefore you get meaningful numerical solutions and analytical solutions, because your analytical solutions are also flawed. But you can also, because you have length scale, capture size effects. Size effects cannot be captured in standard continuum mechanics. They can be in fracture mechanics because you explicitly introduce there a fracture energy, a fracture toughness. And when you divide the fracture toughness by Young's modulus, you can have something of the dimension of length. But in a continuum theory, the standard continuum theory you're using, is never the case. Is such that we have a slight imperfection. So that means that one of the elements is slightly weaker, say 1%, than the other elements. So we load the bar until the moment that the weakest element fails. So this weakest element then goes on this branch. Now, since we must have stress continuity in the elements, the stress in this element must be the same as the stress in the weakest element. But since this element, the stronger element, has never been broken, the only way to arrive at this stress level is that it goes back here. So the total solution is m-1 times this solution plus 1 time this solution, and if you then elaborate that a bit, you get this solution. So the crucial point is you must have an imperfection, and you must include stress continuity here. So, second part. What I'm now going to talk about is damage mechanics, also called in the French school the local approach to fracture, non-local approaches, gradient damage approaches, and how do you do this numerically. Now, the simplest possible damage model is just a bunch of bars. So here we have a wall. We force them all to be formed the same. They have a length L, and we have M bars. So the force is the sum of the stiffness of each bar times the displacement of each bar. Now we go to the case that we have some bars that now we go to a case that we have a distribution in the strength of these bars. Some bars are a bit stronger than other bars. So we use the model of that each bar is brittle. So you go to a tensile strength of a bar and then go down to here. So the force at the moment that n bars of the m bars have broken is m minus n times stiffness, spring stiffness, times displacement. We can translate that into a continuum model, and we then say, okay, we here have our spring stiffness, we replace that by E times the cross dimension, and here we replace m minus n by 1 minus the ratio of n over m divided by the length. So we go to a stress-strain relation. And then we have the force equals our Young's modulus times our cross-section times our strain times 1 minus the ratio of broken bars. And this ratio of broken bars is the damage parameter. And clearly, when we have an intact system, n equals 0, and therefore omega or d, which is sometimes used, equals 0. So we have just the force equals 1 minus 0 times Young's modulus times A0 times epsilon. Or if we divide F by A0, we have our stress equals 1 minus omega times Young's modulus times the strain. And that is essentially the basis of every damage model you find in the literature. So the next thing is that we derive the tension stiffness. So we here take our derivative of F. It's 1 minus omega times E times A0 times epsilon dot minus the derivative of omega with respect to epsilon times E times A0 times epsilon. So our stiffness of the system is 1 minus omega minus the omega, the epsilon times epsilon times E times A0. Now, again, we have this loading, unloading condition I talked about the previous lecture. Because suppose that we load and load and load until a number of bars have been broken. So omega has a certain value, and at that moment we start unloading. I mean, the bars will not unbreak again, they will not heal. So they will remain broken. So this omega has the role of a history parameter which memorizes the amount of damage that has taken place in the past. So we have, in case of unloading, omega doesn't change. So the rate of omega is 0. But when we have loading, omega increases. So for our effective stress, which is essentially the force divided by the load carrying area A, rather than the original load carrying area A0. We have now 1 minus omega times Young's modulus times A0 times epsilon divided over A. Now you can generalize that to 3 dimensions, and in most general way you say my stress is equal to my stiffness, my secant stiffness, times my strain. And this can depend on a scalar, on a second order tensor, fourth order tensor, whatever you want. And you want to make it complicated, you can. So for full anisotropy, you can do that in principle. Question is, of course, where the hell do you get the parameters from? How do you measure them? So, most cases, any damage model is a scalar-based damage model, and in that case, your secant stiffness depends on the degradation of Young's modulus and of Poisson's ratio. And in a further simplified version, usually it is assumed that Poisson's ratio doesn't change. So it's just Young's modulus which degrades. So this is the summary. Our stress-strain relation of damage models is we have a stress which is 1 minus the history variable omega, your damage parameter, times your elastic stiffness, your original elastic stiffness, times your strain. And your omega degrades. But you cannot degrade it directly. You have to incorporate, you have to allow for this possibility of loading, unloading. So you have to supplement this stress-strain relation by a loading-unloading condition, where you make a loading function which is dependent on the current strain, some scalar function, depending on your material, and the history. And you check the current strain with the largest value of epsilon tilde that has happened in the past. So the largest strain that has happened. Now, an example of that is this expression, which is often used for metals, and which is a half times the strain times the elastic strain, the elastic stiffness times the strain. Essentially a work expression. Now, if this indicates that you have unloading, you put your omega equal to the omega that was there before in the previous loading step. If omega indicates loading, which means that this one is bigger than this one, and therefore F is bigger than 0, in that case we have to update our omega according to the material function that is here. So the whole structure is, we have a one-to-one relation. We have a relation which expresses the stress as a function of omega and strain. We check, based on the strain, we compute an equivalent strain. The equivalent strain we feed into our loading condition. If F is smaller than 0, the history parameter remains unchanged. If it is bigger than 0, we update our omega. So here I've written out the algorithm, how you do that. So from your finite element or finite difference or whatever numerical approach you use, you compute always displacement increments in nodes. From that you get, usually in integration points, you get your strain increment. So you update your total strain as the strain that was left behind at the previous loading step, plus this increment which you've computed. Now you have your full strain tensor, and you compute your equivalent strain. For instance, using this function, or when you have another type of material, the function that is appropriate. You evaluate your loading function as the difference of your equivalent strain, which you just computed, and the history and kappa, which you have memorized. If f is greater or equal to 0, you have loading, and you update kappa. Else, if it's smaller than 0, you keep it to the old value. You update the damage variable, and that holds whatever you have done here, because it always has the right value here. So you compute, you have the right value for kappa here, so you can compute the right value for omega, loading or unloading, and then you'll compute the right stresses. S1 minus the updated omega times the elastic stiffness times your new strain. So this is essentially the algorithm you use to, in damage mechanics. Now you have to do a little bit more usually, and that is related to the fact that you not only have to compute your stresses from your strains, also you have to compute the displacements. And you've always, in nonlinear processes, a double loop. You have a global equilibrium loop to update your displacements. Then you feed your updated displacements into your constitutive relation at integration points. So you transfer the variables, displacements in nodes, to strains in integration points. At these integration points, you compute the stresses. And from that, you compute the internal forces in the device. Then you check whether your internal forces are in equilibrium with the external forces loading on the structure. If the tolerance is sufficiently small, you say, I'm happy, I have sufficiently good equilibrium. If they are not happy, if they are not sufficiently close, you're not happy, and you use Newton's method, the Newton-Raphson method, to improve your estimate for your displacement increment. Now, in the Newton-Raphson method, you need the tangent stiffness matrix. So, how do you compute that? Well, you have your relation between stress and strain. You have to differentiate that to obtain a relation between stress rate and strain rate. So when we are here, we differentiate this. This means that we first keep this, this one is a constant, and the elastic stiffness, but this is varying, and the strain is varying. So we use the chain rule, so we first differentiate this, keeping this constant, and then differentiate this, keeping this constant. So here we have 1 minus omega times d times the strain rate, minus the derivative of this is minus omega dot times d, e times epsilon. And now we have to use the chain rule to compute omega dot. Omega dot depends on the history parameter. And the history parameter depends on your equivalent strain. And your equivalent strain depends on your total strain tensor times the strain rate. And you see, this is a scalar, this is a scalar, this is a scalar, and this is doubly contracted. So it's also a scalar. Now, if we have loading, well, this you can always compute. This is an interesting one. Because, look here, if you have, if we have loading, this equals 1. If we have loading, look here, this is 0, so this is equal to this, and therefore the derivatives are also. If we then, therefore, if we do d epsilon tilde, d kappa, that's therefore equal to 1. However, if we have unloading, then it's not defined, so the derivative becomes equal to 0. So, if we have loading, this is 1. If we have unloading, this becomes 0. And the whole term falls out. That's not strange, because if we have unloading, we go back to the origin in a secant branch. And this 1 minus omega times dE is just the secant stiffness at this point. Yes?
Please, one slide back.
Sorry?
One slide back. One more. Yeah. So, F will be 0 during unloading.
F is 0 under unloading.
And then this derivative will be 1.
Sorry?
The derivative which you said, del kappa by del epsilon.
I mean, here 0, then you have 0 is E epsilon tilde minus kappa.
Yeah.
And by implicit differentiation,
Yeah, it's 1.
you have the epsilon d kappa equals 1.
But for unloading.
For unloading, it's undefined. Unloading, this is smaller than 0. So you don't have an equality sign here. You have an inequality. A strict inequality. So you cannot define it. Mathematically, you can do that. You have to work with a concept which is known as subdifferentials. So you can do it properly, but that goes quite a bit into functional analysis. But let's say, in an engineering sense, it's an inequality here. There's no relation, they are not equal, and therefore the derivative by implicit differentiation becomes 0. So for loading, you have the omega, the kappa, the epsilon tilde, the epsilon times epsilon dot. For unloading, this whole term cancels, and therefore you only have this term, which is essentially the secant stiffness. 1 minus omega times dE is the secant stiffness. You have here, you go up here, then down here, or somewhere here, and then you go down in a secant branch to the origin. So, substituting this into here, you get 1 minus omega dE minus the omega d kappa, the epsilon tilde, times dE times epsilon, outer product times the epsilon tilde, the epsilon. double contracted to the strain rate. Now, what you see is that already for this very simple damage model, and it's essentially simple because we started just by a bunch of parallel strands, we get an expression which becomes pretty complicated, and to my horror is non-symmetric except for some special cases. Because this times this is unsymmetric. It only becomes symmetric when you choose epsilon tilde as this. Because in that case, if you substitute that into here, you get dE times epsilon, which is the same as dE times epsilon, and then you have a symmetric expression. So, but that's a special case. So in that special case, you get, as I said, dE double contracted to epsilon, cross product times this, and that is easy. So that was a simple bit. Now we go to the non-simple bit, the non-local damage mechanics. And I told you that damage mechanics becomes ill-posed as soon as this expression times a normal vector times a normal vector and then a determinant, so the acoustic tensor of this expression vanishes. And then we get all the problems with mesh dependence, which are plaguing often damage calculations. So to solve that, we can say, okay, we don't make the stress in a point depending on the strain and strain history in that point only, but we also make it dependent on a finite neighborhood. So we replace this loading function, which is a local loading function, by a non-local loading function, where instead of deriving this epsilon tilde directly from the local strain, we compute an epsilon bar, which is the volume average over a finite neighborhood of all epsilon tildes. So here we have our epsilon tilde. We multiply it by a weighting function. I mean, obviously, nearby strains are more important than far away strains. And you can use a Green's function, you can use a Gaussian function, a triangle function, whatever. You have to normalize it by the integral of the weighting function, of course, in order to get back the strain, in order that you don't increase the strain. So you can do this integral. You can then substitute this epsilon bar into the loading function. Here you see such an example. This is a Gaussian function. And you get something that is working. Now, what you see is such a weighting function always contains a measure of length. This is a typical thing. This LC comes here back. that is the amount over which you spread. And obviously, when LC is larger, you spread it over a larger area, and long-range forces, long-range influences are more important. Physically, that translates into that your crack bend zone, the width of your crack bend, for instance, if you have a number of microcracks, or your fracture process zone becomes larger. This L is directly related to the length of your fracture process zone when you are computing, for instance, quasi-brittle materials. An alternative, which you also see sometimes, is that you don't average epsilon tilde, but you average the history parameter. You do exactly the same then, and then define a k-bar, which is 1 over the 1 over psi averaging function times kappa integrated over the volume. Computationally, this is a bit easier. People have argued that it is mathematically, physically a bit better. Now, how do you do this? Pretty much along the previous lines. So we compute the strain increment from our displacements. We update the strain. We compute our local equivalent strain as a function of our local strain. We compute a non-local strain, and here you replace the integral by a finite sum. Here with weight function, the weight factor times this value times your strain there times the volume. I mean, you have to discretize that. Then you do exactly the same. You feed this in your loading function instead of epsilon tilde. You check it, you update kappa or don't update it. You compute omega and you compute your stress. So from there it runs exactly the same. So the interference is quite small in fact. Now there are some computationally some nastiness things. One thing is that in principle such functions are unbounded. I mean, they unbounded in the sense that they become small, but never completely zero. You can cut off it at some point, but even then, they increase the bendedness of your stiffness matrix enormously, because there is an influence between this point and this point. So that's not nice. Even worse, even if you manage to keep a damage formulation that is symmetric, this will destroy it. So an integral formulation gives you rise to very nasty stiffness formulations which are not symmetric. So what we have done is we have come up with some approximations in the sense of you can develop, for instance, this integral expression in a Taylor series. And then you make it the local one, and then when you develop it on basis of such a Gaussian function, you get first the Laplacian, then the fourth order expression, and so on. This is still a bit nasty. Why? Well, here we have at some point the second derivative of the Laplacian. And to compute derivatives accurately is a hell of a task. So you can manipulate this a little bit, and you can say, okay, we differentiate left-hand side and right-hand side twice. And then we get a second order term here. We then move that to the right-hand side. And we obtain something like this. So we get the Laplacian and the fourth derivative on the left-hand side rather than on the epsilon tilde. So epsilon bar is our unknown, is our global variable, and epsilon tilde is our local variable. Now, this is much nicer than this, and that seems strange. But I will tell you, I explain. But before I explain you, I will tell you a little bit about the difficulties that hamper all these higher order models. And that's the boundary conditions. Again, we always tell our students, beware of the boundary conditions. Obviously, when you go to an integral formulation or a higher order formulation, gradients, you need additional boundary conditions. And you have to do something else additional on the boundary. And for instance, in here, for this gradient model, we also have to impose something for this epsilon bar on the boundary. So we either have to prescribe it, or we have to assume a natural boundary condition. Now, in practice, it's not such a big issue, because according to the 7L principle, these kind of things have short-range influences. So unless your problems are close to the boundary, they will not have much influence. But it is an issue, and you have to be aware of it. There's no good solution available. Now, you have some alternatives. You can expand, of course, also kappa bar, and since kappa omega is a direct function of kappa bar, you can also expand omega. So how do you do this now? Now, you compute the strain increment and the non-local strain increment. How we exactly compute this one, I will reveal in a moment. We update both the strain increment and this non-local equivalent strain increment, strain. We evaluate the loading function, and then do the usual thing. If it's bigger, we update, else if not, and we evaluate our damage variable and compute our new stresses. Now, why is this implicit gradient function damage formulation so nice? Because we can do mixed finite element formulation. We can interpolate our displacement, but we can also interpolate our additional strain field. And usually we will do that with different interpolation polynomials. So capital H is different from capital H bar, because strains are usually an order lower than displacements. So you must adapt your interpolations from it. You have the interpolation of your test functions in a similar way, and you obtain your equilibrium equation, usually like here, but an additional one for this averaging equation. And essentially what we have done is we have taken this equation with only this term and this term. We have integrated this by parts, and then you arrive at this for epsilon bar and this for the additional term, which is the gradient of epsilon bar. So you have now two equations which are coupled. Because if you elaborate it, you get here 1 minus omega times your stiffness. But you can get also an additional term of the second part of the stiffness matrix, which is the derivative of omega with respect to kappa. So that comes here. And from the second equation you get also different contributions. This one, which comes here, and this one, which comes here. And this one, when you differentiate it, you get then this one. Now, the nice thing is, the system is symmetric. It's nicely coupled, it works easily. And the only disturbing thing is that this thing may be not the same as this, but that was in the standard damage formulation. So we cannot improve something which was a problem already. Now, does this work? Yes, this works very nicely, in fact. So this is the case, again, of a bar with a small imperfection. So here we load it. We have a cross-section here over 10 millimeters, which is 1 square millimeter reduced. And when you then refine mesh, you do see that you get convergence to a physically meaningful solution, because the area under this curve is finite and therefore shows energy dissipation. This is another case where here you see that it's a single astronaut specimen. Here you have a loading, sorry, here you have two loadings, here you have 2 points, there's a pre-notch here, and the crack starts propagating from here to here, and later from here upwards. And you see that these damaged zones are properly reproduced independent of finite element discretizations. There is some issue though, and that is when you here look at this 3-point bending test, you see that the damage zone not only propagates, so here you have a 3-point bending, a load here supports here and here, not only propagates but also broadens. And this is something that is more than or not really physical, and we will come back how to solve that later. In effect, one of the solutions that have been proposed is make this length scale dependent on the amount of damage. So when you have progressive damage, the length scale should vanish, should become smaller. And then you can reduce it. So we have seen in the previous lecture how we can introduce damage mechanics to simulate fracture in a smeared way. What problems you have and how you can extend it, how you can repair these problems by resorting to non-local approaches or gradient approaches. One of the other approaches which is often used in rocks and soils is the Cosra approach. And I alluded to that already a few times when I said you can also drop the assumption that when you go smaller and smaller that you arrive at a homogeneous stress distribution, but instead have a linear varying stress distribution, which is statically, of course, equivalent with the normal force and the bending moment. That idea was conceived more than a century ago, 1903 to be precise, by the brothers Coseret, and was, I think, the first enriched continuum model. You can, and I will show that now, also combine that with things like plasticity. And I will give you some examples of how you're doing that. Now, what are the kinematics of such a model? Well, normally you are used to the fact that you define your shear strain as half dux dy plus half dy dx, and that you define epsilon yx identical to epsilon xy. Your strain tensor is symmetric. This does not have to be the case. You can define the rotation of a microscopic element by an independent rotation. For instance, when you think of any granular material where the particles are relatively rigid compared to the total stiffness of the medium, where deformation is caused by, for instance, rolling of particle or displacement of particles rather than by deformation of the particles itself, then rotations of the particles are important. They can roll over each other rather than purely deform. And in that sense, including the rotation of the particles, even in an average sense, over small volume makes sense. So what we here have is we define now our epsilon xy as dux dy plus the rotation around the z-axis. So we have x, y, z. We have a rotation around the z-axis as an independent kinematic variable in addition to ux and uy. So we have three independent kinematic variables. So here we define epsilon yx as duy dx minus omega z. Of course, if you add them, epsilon xy plus epsilon yx, then the rotation falls out, and the total shear strain, total amount how this angle becomes smaller, still remains dux dy plus duy dx, as it is in our classical continuum. Now, since we have a rotation, a kinematic degree, we also have curvatures, microcurvatures, which are possible. So, for this elementary particle, we of course have the strain, the axial strain in x direction and in y direction. They are not affected, they are as before. We have our shear strains, a different one, epsilon yx from an epsilon xy. But also, we now have our rotation, which can cause a curvature. So we consider this as a sort of mini beam, a micro beam, which you can do like this. And also like this. So we can do it in both this direction and in this direction. So this microcurvature is kappa zx. It's the derivative of the omega z dx. And similar, we have in the direction orthogonal to that, kappa zy is the derivative of the rotation, the additional degree of freedom, with respect to y. And it's the simplest possible extension of a standard continuum mechanics theory. Now, there is a special case which you sometimes have as constraint constraint theory. And then if you define omega z as a half times this minus this, then you would retrieve what you classically have. Indeed, substitute this expression into here. Then you get dux dy plus half dy dx minus half dux dy is half dux dy plus half du dx. Same when you substitute it here, you get dy dx minus half dy dx minus minus, so plus half dux dy. So in that case, when you have this rotation as this, as a traditional implied rotation which you would have, then you get back the classical kinematics. Now, if you have additional kinematics, you also need additional stresses, additional statics. So you need stress measures that are conjugate to these additional strain measures. So, of course, we have our normal strain, nothing changes, our normal stress is their conjugate. We have our shear strains, also there our shear stresses are conjugate. But already there's one thing. We have different shear strains. They can have different values. So sigma xy, which is conjugate to epsilon xy, can be different from sigma yx, which is conjugate to epsilon yx. So we have, in that case, a non-symmetric stress tensor. Normally, you would think non-symmetric stress tensors only appear for large strains. Here you have non-symmetric stress tensors already for small strains. In addition, you have stress measures that are conjugate to these microcurvatures. And these are little bending moments. And they have been drawn here. So here are the normal stresses, sigma xx, sigma xy. But also we have a moment m xz, the moment on an x-plane directing in the z direction, because it's around the z-axis, which is a moment which is causing this kind of curvature, this kind of bending. Similar here, in addition to the normal stress and the shear stress, we have a bending moment, and here, which causes something like a bending, a little curvature. Now, these effects already play in the elastic regime. So, what we do here is we have now, we simplify for the moment to 2D configurations. We don't go to 3D, which makes it would make it a bit complicated. So as independent strains, we now have epsilon xx, epsilon yy, And for the plane strain case, we would also have epsilon zz. Epsilon xy, epsilon yx, plus our microcurvatures. And here I have multiplied them with an L, parameter with the dimension of length, in order to make them dimensionless. To have them, give them the same dimension as the normal strains and shear strains. Because the curvatures are of dimension 1 over L. Multiply them with L and they are again dimensionless. Essentially, this L is the size of the smallest volume over which we can homogenize. In classical continuum, we assume that we can homogenize up to a point. That's physically not always possible. So in some cases, you have to say, okay, there's a lower limit, and this length is set by this parameter. Similarly, the conjugate stresses, the normal stresses, the shear stresses, and our micro bending moments, which are again now divided by L in order to make them of the same measure as this. This is Newton per square millimeter. The bending moments are of course Newton per millimeter. Therefore you have to divide them by an additional length in order to have them of the same length, dimensions. Now, if you go to the balance of momentum, of course, longitudinal balance of momentum is not a problem. But when you look into the balance of momentum, then you get a different term. Normally, you have sigma xx equals sigma xy. Sigma xy equals sigma yx. Now you have these bending moments in addition. So when you take rotational equilibrium, you have this times this lever arm, minus this times this lever arm, plus this bending moment, minus this bending moment. Or plus this bending moment. So here you get that derivative of the bending moment of this one in the x direction, plus this one in the y direction, minus this shear stress, plus the other shear stress equals 0. And here you see that you have a non-symmetry indeed of your stress tensor. Also here you see it, because normally this term will not be 0. The bending moments are not 0. So you see that you have no symmetry anymore of your Cauchy stress tensor, and you get an introduction of your internal length scale, of an internal length scale. Now, we have had the kinematics, we have had the statics, we still need some constitutive relation. Well, the simplest possible case, that is of isotropy for 2D situations, is this. So here you still have your normal shear modulus. Here you have your normal expressions C1 and C2, which depend on your Poisson ratio. So this is for plane strain conditions. Here you get additional terms. So when you look into your relation between your shear stresses and your shear strains, you have an additional modulus, mu c. And this is the relation, the shear relation here. So in total, you get 2 additional material parameters, mu c, mu c, and L. And mu c has a normal, is the same dimension as the normal shear modulus, but L has the dimension of length, and therefore introduces an internal length scale, and therefore you can have size effects in such a continuum. And also, when you do numerical calculations with softening, for instance, then you get mesh-independent solutions as a consequence of this. Now you can extend this also to plasticity. So you do the usual thing, you separate the strain into an elastic part and the plastic part. You take, for instance, a Drucker-Prager yield function, which is something like, here you have the J2 invariant, here you have a friction coefficient, your pressure, and here you have a yield strength. Obviously, you have the von Mises yield function as a special case when alpha equals 0. But what you have to do is you have to enrich the expression for the second invariant. You have to include now not only the deviatoric stresses, but also the bending moments. And again, in order to make them of the same dimension as the normal stresses, you have to divide them each by this length L. So normally you would have half here and half here. Now this is only a constraint. So your choice becomes much wider. So in matrix notation, you here have just the normal ones. Here you have additional terms, and this is related to the bending moments. So you have now in a matrix vector notation your yield function as this, sigma times this matrix times this, plus alpha times the projection vector of the stresses minus your yield function. Now in plasticity you not only have yield functions, but you also have plastic potential functions. And for metals there is normally no difference. For geomaterials, but also for ceramics, there is a difference. These materials are pressure dependent, and in that case, the flow room, the expression for the plastic strain rate equals a multiplier times the derivative of this plastic potential, rather than the yield function. So we have typically a plastic potential that's very much similar to the yield function, but with a dilatancy factor rather than a friction factor. So if we substitute this in here, we can get this by simple differentiation. And again, we have to define a different expression for our hardening parameter. Normally, we have just 2/3 times this, or 1/3 times this, plus another third times this, which doesn't matter because epsilon ij is symmetric. But now we have also to add the plastic microcurvature rates. And again, you can put that in a matrix vector form, which is convenient, and you can go back in the end to a classical scheme for elastoplasticity, except for the fact that you've extended the vectors for the stresses and the strains with two entities, namely the microcurvatures and the bending moments. Plus, you have to make distinction between the epsilon yx and epsilon xy, and a sigma xy and a sigma yx. Now, you can then write that your new stress is equal to your old stress plus an elastic part minus a plastic part. You can write this plastic part as such. You substitute this into here to obtain this, and you can finally solve for this unknown amount of plastic flow. This is a little bit technical. You substitute it in here, but in the end you enforce the yield function, and from that obtain your plastic multiplier. Again, problems are not over, because you also have to define a stiffness matrix. You still have to solve the system at structural level, which means Newton-Raphson method, which means derive tension stiffness matrix. Now, there's something there, is that we have to start from this expression. Sometimes in the old literature, you see still the expression between the stress rate and the strain rate. That's wrong, because if you differentiate things, you again have to first differentiate this part times this, and then the other part times this thing, times this delta. And that gives an additional term. And this additional term is crucial for obtaining rapid convergence. So how does it work? So we want to arrive at something like this. Your stress is some tension stiffness matrix. We want to arrive at something like this. Stress rate is something like strain rate. So we start at something like this, where here you can derive that this H is this. You then substitute this into here. You enforce consistency, means that your yield function keeps to be enforced. And then you do quite a bit of manipulation and arrive at this. Now, the important thing is that in elastoplastic computations, you get mesh independence. Well, this is an example of calculations with elastoplasticity. In this case, I have used a plastic potential function which is different from the yield function, not even including softening, no large deformations, but already the difference between having a different yield function from plastic potential is sufficient to lose elasticity, which means it's sufficient to get mesh dependence without even material softening. And then you get this. You see, for a coarse mesh, it's one element white. For a finer mesh, it's one element white. For an even finer mesh, it's one element white. And the finer you go, the smaller thinner become your shear bands. Now, if you include the constraint effect, you get a different picture. Obviously, when your mesh is too coarse to resolve the shear band or the fracture zone or whatever, you still have some mesh dependence. But when you go finer, it becomes good. So obviously your mesh must always be fine enough, but when it is fine enough, it should converge to a finite width of your localization zone. In this case, a shear band. In the case of fracture, a zone of distributed fractures. And that was it for today. Good morning.
Good morning.
So the first thing we are going to do is to talk about phase field approaches. Phase field approaches have come over from, I would say, the mathematics community, where they have been used to replace what they call sharp interfaces by diffuse interfaces. And essentially, it's the same thing as replacing a discrete description of a crack by a smeared description of a crack. In the mathematical physics community, they use these approaches also for many other phenomena. For instance, when you have two liquids with different phases which don't mix, the interface, for instance, between an oil droplet and the water is a sharp thing, which is then sort of described by these kind of phase field approaches. Well, the idea is essentially the following. If here we have something like a strain at the crack, which is described by a direct function. So here we have a jump in the displacements. So that means that when we differentiate that, we get strains which have a direct function. So many phenomena can be described by that. And the idea is that we replace this direct function by a continuous function, something like this. For instance, where here we have the shape of an exponential function. Obviously, you have to introduce a parameter which controls the width. And this parameter, which mathematicians have introduced as a regularization length, turns out in mechanical processes to have to be this internal length scale, which we also yesterday saw in many of these gradient damage models, these non-local damage models. So we have here a regularized direct function, which is a function of x, the ordinate orthogonal to the crack, and where the strain has this exponential function. Now, the important thing is, of course, the definition of a direct function is such that it is 0 here, in principle infinite here, but the integral of the direct function over the domain is finite. So if we make it such that this finite integral is equal to the integral here, then we should have an equivalent problem. So that's the whole idea behind any phase field model, and, well, the exponential function is the most often used. You can also use any other function which abides the property that the area below here equals the area here. And normally you will always need a parameter to control the width of this zone. And obviously, when L goes to 0, you retrieve back the original formulation. So the closer L is to 0, the better, the closer you approximate the original problem. The downside is, the smaller you have L, you essentially distribute a discontinuity over a finite width, and you have to resolve that with your discretization. So if you make this small, the area over which you distribute the crack is small, and you need a lot of elements, small elements, around the crack. So you resolve it better for small L, but you have to pay a price with more elements and therefore more computing power. So now we go a step further. So this is the basic idea. How is these kind of things implemented in practice? Well, in practice, this function is never used directly. It's rather used indirectly. So if you look at this linear second order differential equation, with these boundary conditions, it is 1 at the center and 0 at plus or minus infinity. Then this function, this exponential function, is a solution of this differential equation. Now, in many problems, or many solution techniques, like finite elements, we use rather weak formulations. We use integral formulations rather than directly the differential equation. So we convert this into a weak formulation. And here, when you look into this functional, well, here you see the first derivative, and obviously when you have this, when you multiply it with a test function and use Gauss integration theorem, you obtain the first order derivative. Well, that's nice. That means that as classical in finite elements, you have reduced the order, and therefore you can reduce the continuity which you have to apply. So the nice thing is, this is just there are just first order derivatives here. So you can use normal shape functions, like normal triangles, normal quadratics, functions that have C0 continuity at the element boundaries, which means that the function itself is continuous, but the derivative is discontinuous. So this is allowed by this. This is one of the reasons to go to this function. You can go to other functions, but they may require higher order derivatives here, and therefore you get second order derivatives, for instance here, and then you need more advanced interpolation functions. Now, the crack surface can be interpreted as this problem when minimized, divided by L. So this integral is or should be the crack surface. Obviously, this is something which has a volume and not a surface. So the crucial point is, upon mesh refinement, does this converge to a discrete crackling? So do we have a problem which upon mesh refinement the smear problem really converges to the discrete problem? Now one other thing. What you see here is you have the phase field parameter here, and you add gradients. Well, if you go back to one of yesterday's lectures, think of the gradient damage models, where you also had the damage parameter, where you added gradients in order to make the problem well posed. At first sight, this looks a little bit similar. And it is in fact quite similar. Now, you can do that, of course, in a this is one-dimensional. You can do it in a multidimensional generalization. And then this becomes, of course, this is the same, but now here we have the multidimensional gradient operator, which we square.
Excuse me.
Yes?
Please advance it. Here, can you please why this integral over L represents the crack surface?
Sorry?
How this gamma equals ID over L?
This is just defined like this, and it turns out that it is the case.
And while coming from like the second last line to the last line, how do we get this nabla d square, the norm of gradient of d from that term?
Yeah. I mean, here I've gone a little bit too fast. This is the one-dimensional case.
Okay.
And this is the multi-dimensional equivalent. I mean, in fact, I should have had this line before that line. So this is the one-dimensional case. Now I want to go to a 2-, 3-dimensional case. And then I replace the gradient by this. And in fact, there's a typing error here. This should be ddx squared. Now, what is in the specific application to fracture, and in fact to brittle fracture? Van Voor and Margot have said, okay, we look at the total energy of a body, and this is composed here of the elastic energy in the body, plus here the fracture toughness integrated over the crack length. Just energy. And then we replace this, which is for a discrete crack, by this expression. So here we have the thing for a discrete crack with the fracture toughness here. Here we have the value, and this is the distributed value, which, like here, you have borrowed from here. So you can say this is a sort of the distribution of how this energy is distributed, orthogonal to the crack essentially. And then we can replace this, which is discrete. You want to get away from that. So you replace this line integral or surface integral by a volume integral, using this trick. Essentially, you say, I have a discrete crack here. The energy you dissipate is Gc per unit cracked area. I replace that by Gc times gamma L as the energy that is dissipated per unit volume. And obviously this is, well, has something like this shape. So we now have two volume integrals. We can put them together, and this integral we have to take on and to minimize. So, for the case of brittle fraction, we have a potential energy, which is the part stored in the body and the part distributed in the grain. Now, you have to do one more thing. It's a bit of a trick. You have to say, okay, this is my, because if you propagate the crack, you get something like a degradation, a lowering of the energy in the rest of the body. And this is modeled by multiplying the original elastic energy by a degradation function. Well, here it becomes a bit messy. I do admit that. This is a little bit where empirism, pragmatism comes in. So the beautiful mathematics is now gone. This is something like a fitting function, which, however, does have to obey certain mathematical continuity conditions. I mean, in the beginning, it should be 1. If everything is intact, when everything is degraded, it's 0. And you have also to have some requirements for the derivative of it. Now the energetic driving force is the derivative of the potential function with respect to the phase field parameter, and is the derivative of this degradation function with respect to d times psi. And here you see this one must abide certain continuity requirements also, and that's imposed on this. Now, the simplest possible, in fact, degradation function that is used is 1 minus d squared. Well, for d equals 0, so when you have no crack, gd equals 1. When d is 1, and remember the analogy with damage mechanics, then g equals 0. The derivative is 1 minus d. So that means that when d equals 1, at complete failure, we have no slump, which is imperative because at that moment we don't want to have growth of the phase field. Then you must have something that at some point levels, and at the end of the process there is no growth, no slowing. This is one of the differences with gradient damage. But typically we have this 1 minus omega or 1 minus d, and there you get some differences. So here you see them together. Here you have what you would get for your driving force when you have gradient damage. Remember, this is your driving force. It's your dg dt. And in case of a linear function, like in gradient damage, dg dt is just -1. So here we have just -1 times the elastic energy. And that means that you have a constant driving force in these gradient damage processes. And that's the explanation why you have this broadening, which I showed you. I mean, you would want that the damage profile only propagates in this direction for this 3-point bending test. But instead, it also broadens. That is the consequence of this driving force. Here you see that the driving force in the phase field formulation is more convenient. Because when d equals 1, so at the end of the failure process, the driving force has gone to 0. So at the end of failure, we don't have additional driving and no propagation. Which is why, as I will show in an example, the broadening does not, in the wake of the crack, does not occur for these phase field formulations. So in that case, you have a constant bandwidth in contrast to these gradient formulations. On the other hand, in both cases, you have essentially, of course, your equilibrium equation, which you supplement with a differential equation to distribute your damage or your phase field parameter. I mean, you distribute it from a discrete line to a finite distance. And when you look into the differential equation that is supplementary in the gradient damage formulation, it's something like this. Now here we have our parameter, which is the dimension of length squared. And look at here, we have the same here. Well, we have 4L squared here. We have the Laplacian of, in this case, the damage parameter, here the phase field parameter. So the left-hand side is completely identical, provided that we choose Cg equal to 4L squared. And here we have D, the local value of the gradient damage, or of the damage, not gradient. And here we have, well, something that's a little bit more complicated. Here we have the length scale, here we have the derivative of G, and here we have a history parameter, and here we have GC. So it's slightly different, but there are clear similarities. You indeed see that they behave in a similar manner, but there are some subtle differences which make, for instance, that this broadening doesn't occur in phase field. And you see that here, this is a case where you have an initial crack. You have a step load here, so it's a dynamic problem. You get propagation along this initial notch, then further propagation, and at some point you even get branching. But you see that in the wake of the distributed crack, you have no broadening. Now, how do you solve that? Well, you have two coupled partial differential equations. The equilibrium equation and the equation to solve your phase field. Essentially not different from the gradient damage model. Always, or broadly speaking, you have two ways to solve a set of coupled differential equations. Either you do it monolytically, like I showed yesterday for the gradient damage model, that you assemble everything in a big stiffness matrix. You solve at the same time for the displacements and for the damage parameter. Or you do it in a staggered way. stacked way means that you first solve the displacements. The values for the displacements give you a value for the damage, the local damage, or the local phase field. You feed that into your differential equation for your phase field as your load factor, your right-hand side. You solve for the non-local or gradient displacements or the phase field parameter. You look whether that's satisfactory. You go back to your equilibrium equation and you loop until you have Riesz conversions. Well, obviously, the staggered scheme is simpler to implement. It has a drawback. It's simpler to implement. You can also use, for instance, two packages, one standard package for your strength problem and a separate one, and you can, via a common database, iterate between them. Or the monolithic scheme, which is more difficult usually to implement, but has the advantage that it's a bit more robust. I show that here. Here we have looked at a simple case of a one-dimensional bar with an imperfection which we put in tension. Well, in the monolithic scheme we have something like this, where we have a neat snapback. So at some point not only the load goes down but also the displacement, because in this case there is so much elastic energy stored that you get a sort of explosive failure. And if you want to simulate that in a quasi-static manner, you can only do that by reducing also the displacement at the end. And the monolithic schemes are far from that. Sorry, the staggered schemes are far from that, and it's very difficult to get here. You need very fine load steps, time steps in order to get it. So essentially, staggered schemes are easier to implement, are more versatile, but monolithic schemes are more robust and allow you for larger load steps or time steps. Where exactly is that depends on your boundary value problem, but this is sort of the broad message I want to give you. Now, I told you at the very first slide that this parameter L, which was introduced to regularize your Dirac function, was introduced by the mathematicians as a pure perturbation parameter, to perturb the solution. Now, if you do a simulation with that and vary L, you see that for a large L you have this, for a smaller L you have this. Sorry, for large L you have this red one. You have a rather low peak load and a ductile behavior. For a smaller L you get this, the black curve. And for a high L you get the blue curve. So sorry, for a low L you get the blue curve. So I told you in the beginning that the smaller you make the length scale, the better you approximate your original Dirac function. But you need then more elements. And you see also that, I mean, essentially you would have, we are simulating brittle fracture. So you would assume something that has here a peak, a sharp peak, and then goes down. Well, clearly the blue one approximates this the best. And when you make the blue one even, well, the L even smaller, you get something like this. And in the end, you really approach a real brittle fracture. But you need, of course, a very fine measurement. Here you also see that the results are sensitive to this G function, this degradation function. The red one is the standard quadratic function. But you can also use, for instance, cubic functions, which more closely reproduce a brittle failure. And you see that here, when you have a cubic function, you get something like this, which is much more linear elastic, brittle, than this rather ductile response. So the observations here are both L and G have a physical relevance. You must calibrate them. They are not just mathematical functions. They must be calibrated and have a real meaning. This is related to the width of your fracture zone, fracture process zone. This one is related to how well you approach your brittle fracture. Well, we have said at some point, I go a little bit back, we have said here that we approximate this line integral or surface integral by a volume integral. And that this crack surface is defined as this functional divided by L, and that upon mesh refinement, this expression for a smeared way should approximate the discrete. So we have looked at that, and a simple case, and actually we found that's not always the case. The reason is that you have some boundary effects at some point, and that this approximation function not always works that well. But you can come very close. Here you see that we have played a little bit around with this. Here we still have a 20% error, but here we come close to zero. So there are still lots of subtleties, and it goes a little bit too far to go to all these subtleties now. The field is in pretty much development. It's a development of the, let's say, the last 15 years or so, and still very much being developed, and not everything is yet understood. Now, the following thing. Essentially, you have two approaches to fracture in computations. One is the computation of fracture properties. You compute stress intensity factors, J integrals. Based on those data, you decide whether further fracture occurs or not. If so, you propagate the crack by a certain amount, which usually is a bit of experience, and then you carry out a new calculation, usually a linear elastic calculation for this mesh. You compute new stress intensity factors or G integrals, and you propagate the crack, and you make a new mesh, etc. Essentially, this is a series of linear elastic calculations. The other way is a full nonlinear approach to fracture, where you include the fracture law in your whole calculation. So here the central thing in so-called nonlinear fracture calculation is that you try to simulate in a full nonlinear process the crack propagation. And usually you use cohesive zone models for that. Now, there are lots of cases where you can use linear elastic fracture mechanics, but there are also some cases where you can't. You can use linear elastic fracture mechanics primarily if fracture is the main source of energy dissipation. Usually you have some inelastic processes around the crack. But if the energy dissipation there is small compared to the energy dissipation due to fracture, then this can be disregarded. On the other hand, if this is not small, then you have a region with dissipative processes, which is large compared to the structural dimensions. That's always key to that. Is this zone small or large compared to the structural dimensions? Then you are usually obliged to go to cohesive zone models. And what is the essential difference? Well, the essential difference is that in linear elastic fracture mechanics, the energy dissipation is confined to a point. So you have here an open crack. Here you have a point where your energy is dissipated. Just ahead of that, your stress is singular, and then you have an intact material. That's different in the concept of a cohesive zone, also called the Dugdale-Barnum-Blatt approach, after the founders of it. Here you have an open crack. Here you have a closed crack. And there's here a finite zone, a fracture process zone of finite length, where you have dissipation. For instance, in metals, due to plasticity. In materials like ceramics, for instance, fiber reinforced concrete rocks, due to microcracking, if they are reinforced with fibers, fiber debonding, breaking, and all these kind of phenomena. Now, like linear elastic fracture mechanics, the tensile strength is one of the parameters. Like in linear elastic fracture mechanics, fracture toughness or fracture energy is one of the fundamental parameters. There's one big difference where the fracture toughness is dissipated suddenly. In cohesive zone models, it is a function of the crack opening. So GC is now a function of the crack opening and is released gradually. Therefore, also the shape of the decohesion curve becomes an important parameter. And that's especially so when you go to brittle fracture, quasi-brittle fracture. So when you look into concrete, rocks, ceramics, these kind of materials, which roughly have a decohesion curve something like this, then the shape is a very important parameter for the outcome of your fracture process. This is much less the case when you're having ductile failure. So elastic plastic fracture in metals is typically having a curve which remains at the tensile strength for a while and then only drops. So this is a curve that has been used quite often, for instance, by Vigert Vergaard, by Ellen Edelman, John Hutchinson, and this is quite commonly accepted. It turns out that when you do calculations, that in such cases it doesn't matter so much for the outcome what the shape is. On the other hand, when you have more this materials which have more this shape, then it matters very much whether it is very steeply falling back here and then has a long tail, or whether it is falling back much more gradually in the beginning. Now, obviously, in all cases, the area below the curve, which makes the traction over the fracture a function of the opening, which is the fracture energy. So this area is a material parameter. This same like here. So it's defined formally as the traction over the crack at a point integrated over the displacement history, crack opening displacement history at that point. So you now have a discrete traction separation relation where you can derive the traction as the derivative of the fracture energy function with respect to the crack opening. And you can write this as the traction is a function of the crack opening plus some history parameter. And a history parameter is needed, again, because at some point during the process, you can have that the crack starts to close again. And then you have to memorize the value of Vn, the largest crack opening that has been attained so far. Because also here, you go down here, when you have unloading, you go, like in a damage model, to the origin here, you go back here and then follow again. But you then have to memorize this point. So it has the same role as the damage parameter in damage mechanics, or the plastic strain in elastoplastic models. Only it's not a strain, it is a crack opening displacement. Now, I said already yesterday at some point, continuum mechanics, standard continuum mechanics, the standard Boltzmann continuum, does not introduce a parameter of the dimension of length. As a consequence, you get these ill-Poserness things, but also it's impossible in a standard continuum mechanics model to reproduce size effects. Fracture mechanics is different there, because in all fracture models, either be it linear elastic fracture mechanics or cohesive zone models, you always introduce fracture toughness as an independent parameter. Now, when you divide the fracture toughness by the Young's modulus of the material, you have something which is proportional to length. So, by the fact that you have an additional material parameter, which divided by Young's modulus gives you a dimension of length, you have, in any fracture mechanics model, you have a length scale, and therefore can describe size effects. In fact, when your length scale becomes much smaller than your structural dimension, the cohesive approach reduces to linear elastic fracture. Because if L goes to 0, in that case, your traction at the crack tip becomes singular. And you retrieve the classical stress singularity of linear elastic fracture mechanics at the sharp crack. I mean, normally, a cohesive zone model blunts the singularity. So different from linear elastic friction mechanics, in a cohesive zone model, you do not have a singularity at the crack tip. You smoothen the thing. Of course, when this length goes to the limit of 0, then you retrieve the linear elastic friction mechanics case, and you do get again a singularity. However, as we know, the energy dissipation remains fine, because, well, you here have your traction, which is essentially, you can then write as your fracture toughness times a direct function, integrated over the length gives you the fracture toughness. So it's again the direct function property which gives you that the integral of the direct function over the length equals 1. That's just the property. Yes?
So I find this a bit confusing. Previously you said that the LEFM works if the energy due to the fracture or the crack opening is much larger than the inelastic dissipation.
Yes.
And now if we say that L goes to 0 or L is very small, that means GC is very small. That means the energy for crack opening, the total energy for crack opening is kind of getting smaller. And then how is this
GC is a little bit ambiguous. In linear elastic friction mechanics, it's principally just the energy dissipated in friction.
So over the crack.
In cohesive zone models, it also includes some of the energy that is dissipated in the other processes.
The inelastic.
Yes. That's a bit confusing, yes. So here I'm a little bit, I sort of start with something that is a little bit broader, and I reduce it at the same time to something that is the fracture toughness in a narrow sense. Because I assume that when bringing L to 0, also all the other processes, the other dissipative processes, become much faster, smaller than the fracture toughness. Which is, well, essentially, this is a constant thing. But the other things reduce. And the total energy dissipation is the pure energy that is required at the fracture toughness to create unit area of crack as the only inelastic effect. In this definition here, you lump all the other inelastic effects in it. So this is why in linear elastic friction mechanics you better talk about fracture toughness. And in cohesive zone models, you better talk about the fracture energy that is dissipated. It's a fine but indeed important point. And I do admit that the distinction is not properly made often in the literature. And I also have the tendency sometimes to be a bit sloppy there. So the bottom line is, when you look into the cohesive approach to fracture, the crack opening is a part of the constitutive relation. And that's not the case in LEFM. And in fact, you can also formulate a phase-shift model for cohesive fracture. Now, let's go back a little bit. Well, we have to go back quite a bit. Yes. So, look at here at the expression. We have here two parts. The volume part plus the part of the crack. This is a constant. It's the fracture toughness. Really the fracture toughness. It's not dependent on anything. When we define the equivalent for a cohesive zone, this term is the same, of course, but here we have a fracture energy function which is a function of the crack opening or the crack sliding, can also do, and a history parameter which is the largest value of the crack opening which is occurred. So this is essentially the difference then. Well, the regularization is exactly the same. The approximation of the direct function by a regularized direct function is not different. So you plug this in here, and this part remains the same, and you replace this integral over the surface by, again, a volume integral where here you have this regularized Dirac function, this delta L. And here you have a function, a fracture energy function, which is a function of a field V, which is the interpolation of this crack opening. Now, there are some subtleties. One of them is that you must sure that your crack remains really orthogonal, that the line over which you measure your crack opening really is orthogonal to the crack, and you can enforce that by an additional approach here, and then you get, in the end, something like this, where here you have a double cantilever beam, you pull here and here, you have an initial notch, and, well, this is a peel test, so you have a glue layer here, and you get a propagation like this. Oh no, this is even a peel test without glue layer, and here you have the propagation of your phase field, and here you have your propagation of the crack with the stress concentration here, and it's a concentration, which means that it is not a singularity. Yes?
So, for this approach, how do we in general estimate the crack direction if we have something like a composite with particle, which it is not known that it will be?
Good question. I don't know. Work in progress. I mean, there are some, I mean, as I said, this whole field, it's becoming enormously popular, it's exploding. It's seen as an enormously promising approach to fracture because it's essentially a smeared approach, but it's mathematically sound and retains many of the features of original fracture mechanics in a transparent way. But there are quite a few questions. And yeah, what I show now on cohesive zone is in a sense relatively early work where we see that there are still quite a few question marks. I just want to tell you what is, this is one of the modern trends in computational fracture mechanics at the moment. And there are still quite a few questions. One of the questions is, for instance, this. We have, for instance, in this cohesive formulation, we have a three-field formulation. We no longer have only the displacements and the phase field, but we also interpolate the crack opening. And you have to do that smartly. Because the displacements, as I said yesterday, are always, because when you differentiate displacements, you get strains. And strains are the same order as the damage parameter or the phase field. So you must interpolate them higher than the phase field. So in this case, if you see that if you interpolate all these variables with the same order, you get some funny oscillations in the stress. Well, if you do it smarter, where you interpolate, in this case, the displacement field cubically, both displacement fields cubically and the phase field linearly, then you get a perfect smooth behavior. So this is things where I say, okay, this is just not ready yet for large-scale use, but it's quite promising. This is another problem. We have problems still with unstructured meshes, where we, even with the right interpolation orders, have some oscillations. So, what's the big thing about phase field approaches? It's an elegant approach, mathematically sound and elegant. It's enormously straightforward to extend it to 3 dimensions. And there it is very different from the discrete approaches I will talk about just after the break. There are question marks about the internal length scale and this degradation function. It was introduced from a mathematical perspective, but it has a mechanical interpretation. You have to calibrate it on tests. And as I alluded to, they are, and that's nice again, related to damage approaches, which gives you a sort of more intuitive physical feeling for something that was here in this way introduced in a rather mathematical way. And this is, I think, no. There's a bit more there. This issue of convergence to the discrete crack is not yet fully resolved. There's an issue of boundary conditions. The irreversibility which you impose is still a bit unclear what effect it has. You can do it for linear elastic fracture mechanics, but not for cohesive fracture. There are a number of publications regarding multi-phase problems. For instance, a typical problem there is hydraulic fracturing. Don't believe too much the papers you read there. It is not resolved. So there are some approaches, but I think the good solution is not out there. So it's a hot research topic. Promising, but at the moment still of somewhat limited use, limited to linear elastic fracture mechanics calculations. So, and this was indeed the last slide. We've now a short, I would say, 10-minute break, and then we go further with discrete approaches. So, the treatment of phase field methods was the last on distributed methods for capturing fracture and failure. I'm now going to give an overview of methods which can capture cracks in a discrete manner. I will start with interface elements, discontinuous colloquial methods, meshless methods, and after that I will carry on with XFEM, extended finite element methods, and isogeometric analysis. Now essentially we have most of these approaches, discrete approaches, use, not all, but quite a few, use again cohesive zone approaches. And we're going to talk first about interface elements. So we have seen that we have a traction which is a function of the crack opening displacement and history parameter. And obviously the limiting case is that you have no traction at all. So then you just substitute 0 for this. Now, the simplest possible way to implement discrete fractures is like this. Now here you have a continuum element, the blue. Here you have another continuum element. And here, the green, is an interface. A zero thickness interface. And, well, I have plotted so that this point, and this point are separate, but in reality they coincide. So here, this point, and this point are lying on each other. What you do is you give this continuum element its own degree of freedom, its own displacement degree of freedom, and this one also its own degree of freedom. Now when you look into this interface element, it is attached to this degree of freedom and to this degree of freedom. So over this zero thickness interface element, you can compute the difference between the displacement here and the displacement here. So you can compute over this interface the crack opening and in both directions the crack sliding. So like you have here assembled all the displacement degrees of freedom in this vector U, and now you assemble the crack openings in this interface in this vector V. Then this matrix L is filled by minus and plus ones. Because this contains this degrees of freedom here and here. So essentially, the crack opening V1 is the displacement here minus the displacement here. And for the sliding, it's the displacement here minus the displacement here. So here you have plus 1 and minus 1s. You interpolate the displacements in a standard way. So you interpolate them like polynomials contained in a matrix times the null displacements, and you retrieve your relative displacements at your interface as this matrix with minus and plus ones times this one, which contains the interpolation polynomials, times the null displacements. Now this is very similar to a standard continuum element, because you can there also multiply L with H, and you obtain a B matrix. Only this B matrix is different from the standard continuum B matrix, where you have ddx ddy, etc. Yes?
What's exactly the difference between U and
U and?
A? So V equal to LU, U are the nodal displacement.
This is the continuum displacement. This is the displacement at the nodes.
So what exactly is it?
Well, U is a displacement that can be anywhere in the element. And you, in a standard finite element way, you interpolate the displacement by polynomials times the values at the nodes.
Okay. So V is a continuous function defined all over the element.
Yes,
Ah.
yes. I mean, indeed, I pointed here at the nodes, but you can have V at any point in the interface element. I mean, essentially, indeed, you're very right. I should have phrased it more properly. V is the relative displacement at any point in the interface as this operator times displacement at one part of the continuum here minus the other part of the continuum here. And then the continua you just interpolate in the standard way, and therefore you bring V also back to the nodes.
Just to confirm, L is like both sides continuous operator. The input is also continuous, output is also continuous. But for H, the input is discrete and the output is
These are continuous operators.
operators.
I mean, like, compare it with strain is a matrix with differential operators times a continuous displacement field. Indeed. Just think in your head as epsilon is L times U, where epsilon has ddx, ddy, etc. Where it's just the strain operators. Now, you can derive a stiffness matrix for this interface element in very much the same way as you do it for standard continua. You multiply this B operator, the transpose, times the matrix you get for from your constitutive model, times again the B operator, and integrate this over your volume of your interface. In this case, in a three-dimensional configuration, a two-dimensional interface. When you have a two-dimensional body, you have a line. How do you get this? The T. Well, exactly the same as you get your tangent stiffness matrix for any constitutive model. So, let's go back here. Here we have, for instance, for our cohesive model, our traction as a function of your opening and your history. So, your T is just the derivative of the traction with respect to the crack opening plus T with respect to the history, and the history is again then, of course, a function of the crack opening. So this is exactly the same way how you derive for any damage model, any plasticity model, but then using strains and stresses. Here you do exactly the same using tractions and relative displacements. And the only thing is, the difference is that here V is a vector instead of a two-dimensional second order tensor. I mean, now these interfaces you have to you can do two things. You can either put them a priori before the whole process begins, or you can do a kind of remeshing and insert them during the fracture process. The last one seems the more elegant one, but this was also, from a software point of view, the more complicated. So most people insert them a priori before the whole fracture process starts. The problem is, you have to do something with this stiffness prior to cracking them, because you have interface elements sitting there which should do nothing. Well, that's in principle impossible. So what you then do is you say, okay, for this T, I insert stiffnesses which are very high value. Sometimes they're called dummy stiffnesses, high dummy stiffnesses. In order that we prevent any opening with the N or sliding with the S and the T prior to crack formation. I mean, we don't want to have additional compliance of the total system prior to crack formation. I'll already warn you of a problem here. You should make them as high as possible in order to prevent deformations, but not too high, because else you get unwanted oscillations which will give you incorrect crack initiation. So for that case, if you then elaborate this, and I've done that, then you obtain something like your stiffness in a normal direction times vectors which contain the interpolation polynomials, and the same for both shear directions. Now here I show you some disadvantage with these oscillations. Here I have a simple notched specimen with a notch here, a point load here, and I just don't look at any fracture at the moment. I just place interface elements here. And what you then get is, you get obviously a singular behavior. But when you increase the values for dn too much, you get these kinds of oscillations. So you capture the singularity better, but you also get these kind of things. So this is one of the things you have to be careful at when you are using these interface elements. When are they useful? When you know the crack propagation direction. One case where you quite often know that is in composite laminates. I mean, you know that delamination will occur between the plies. So you here have just continuum elements for each of the plies. You connect them by interface elements between each of the plies, and you get perfect results. Here, this is a calculation where you very nicely see the size effect 1 over length, and in this case we even had experimental values, and you see that the computations are exactly in the experimental band. It was in fact a class A prediction because the computations were carried out before the experiment. So this is a case when you know where the fracture is going to be for some reason, and with delamination, that's often the case, you can use that very effectively. It's a very effective means, and almost all commercial packages have these interface elements available. This is another case. Here you have a strong backing plate here. There are some thin layers here. There is a round part where you don't have any attachment. You pull all around it, and what you see here is here you have buckling, and then you have nonlinear propagation of this initial round crack. So this is a similar case where you get good predictions, and these are supported by experiments. Another case is when you have an experiment available. For instance, when you know that the crack is going to propagate this from experiments or what other reasons, you can make a mesh, put interface elements along the expected crack path, and get results that are pretty good. Obviously, you must here know something about the crack path, because these interface elements can only be put between existing elements. I mean, it's the easy solution to discrete fracture, but it has the limitation that you have to align them with the mesh. And therefore, you exclude the possibility of a crack freely propagating. The other way, another approach, is to say, okay, I don't know anything about the crack. And Alan Needleman has done that, but I just put interface elements between all continuum elements. That's a good way to do it. However, there can be some mesh bias. For instance, when you change here the directions of the crack. So here you see it for different element layouts, that if you make the, in this case, triangles a little bit steeper, you get also steeper cracks. So there is some mesh dependency. You can do this. It is probably the only way that is a bit successful for crack branching using discrete approaches. There are some criteria around in the literature for crack branching in discrete approaches, but they don't work. At least they are not robust and reliable. With this kind of approach, some success has been made, but you see here also you have to be careful. Now, in fact, you can conceive interface elements as a special case of what is called discontinuous Galerkin methods. And discontinuous Galerkin methods are not so popular in solid mechanics. They are very popular in fluid mechanics. And, well, normally you're used to finite elements that have the same a priori for an element from here and an element from here, the same node here. You can also say, okay, I don't do that. I have an element here with its own nodes. I have an element here with its own nodes. And I try to find a smart way to connect those nodes and to connect those nodes. Well, in that case, we have this. This is for the interior of an element. This is for, and that means that around each element you have the volume and also the boundary integral for each element. So you have the volume here, and you have here the plus boundary and the minus boundary, if we integrate just over all the elements. Now, the big question is, what do we assume here? Well, one possibility is that we assume that the displacement is continuous and that the traction is equal to minus the traction from the other side. So, and then how we do that? Well, if everything else fails, you use Lagrangian multipliers. So you can do that. You can assume the Lagrangian multiplier to be t plus and minus t minus. So when you go to this, here you have lambda, here you have minus lambda. So this becomes lambda here, unknown. Here you have the difference in the displacements here at the boundary. And you have to supplement that when you use a Lagrangian multiplier with such a type of additional equation. So that's one way. You can also say, okay, I try to enforce this pointwise. So then we directly substitute here for the Lagrangian multiplier the interface traction. And then when you elaborate that, you get this, and this should be reminiscent of the tangent matrix which we previously derived for the tangent matrix for the interface element. So you can say these interface elements are nothing but a special choice of discontinuous Bernoulli methods. And as they do it in fluid mechanics and many other cases, they say, okay, we have half times the normal times the average of the stresses at both sides, and we elaborate a bit, and then we have to add some things for proper condition and for numerical stability. The whole thing becomes a bit complicated, but it also works. Now, here you see a typical example of elasticity, and here even you can do some crack branching. So you can work with that. It's not popular in solid mechanics, except for the interface elements, which can be viewed as a special case. Another approach is meshless methods. Well, traditionally, you have here a finite element discretization. That means that we make a number of elements here. So here we have a number of nodes, and this element is connecting all these four nodes. When you look, conversely, when you look at this node here, this node is having shape functions non-zero in all the great domain. So this is called mathematically the support of this node. The gray area is the support of the node, the area where shape functions are non-zero. Now in the finite element method, this support is directly one-to-one tied to the elements that surround a node. You can decouple that. You can also say, okay, I take a node and I choose a support with a shape function, for instance a Gaussian function, where this shape function is non-zero, for instance here. And I do that for every node. Now what you see then is, in this case, we can have overlapping shape functions, because this has this area. This one is also in this area, but has its own area, which is overlapping with this one. So what you do now is you say, okay, my displacement is some monomials, x squared, x cubed, as high as you want, times some parameters. And then I make a so-called moving least squared sum, which is a weight function, times this one, the interpolated function, minus the true function. I square that in a least square sense, and I minimize it. Just least squares approximation. So you have here this quadratic form. You differentiate it, you minimize it, you differentiate it with respect to your parameters, and you obtain this expression. So if you differentiate this with respect to A, you get this expression. And then you can manipulate a little bit again, and you obtain your displacement as these functions times a matrix A inverted, this matrix, which has the weight functions, and again these monomials, times this C matrix, which contains again the weight functions and the monomials. So now you have your shape functions, and you can compute it. It has some advantages. You don't have connectivity. You have few to enforce. You can just put nodes wherever you want. Remeshing is easier. Well, everything comes at a price. You still have to integrate. So in finite element methods, your integration cells are coincident with your finite elements. So you don't have that, so you have to do something extra with background integration cells in order to evaluate these integrals. And here I've already written them as sums. In addition, finite elements have the very nice property that their value, their interpolation, is 1 at the node. Which means that you can easily impose Dirichlet boundary conditions. In this case, you have multiple nodes in this domain, which means that the imposition of Dirichlet boundary conditions, just that your displacement is 0 here, or that you impose a displacement here, which is so convenient and easy in finite elements, is not so easy anymore in meshless methods. But there is a relation. If you go to low order monomials, so to low order functions in this P, and to weight functions with a very small support, then you retrieve almost the finite elements. And you see it here. Here it is still a bit distributed, but here you almost already go to the head of a linear interpolation triangle. Now, how do you cater for cracks here? That's also an interesting one. Originally, meshless methods were very much proposed as something where you can do easy remeshing, where you can easily propagate cracks, where you can also enormously easily add the singularity functions of linear elastic friction mechanics to your base vector. I mean, in principle, we started with monomials, so 1, x squared, x cubed, and so on. But there's nothing against extending this p vector with singularity functions. So you just add the 4 independent singularity functions of linear elastic pressure mechanics. No problem. There is a problem for this integration. Because a crack is essentially a non-convex, a concave domain. Now, you have to integrate. Suppose we have a crack running here. We have this node with, suppose that this is the domain of influence, the domain on which its interpolation function is active. It would be a little bit weird to have the integration also over the great part here, because it's the other side of the crack. I mean, it's not realistic or not physical to assume that there is a relation between this part and this part. So, in this case, it's fairly simple. You just integrate only the shape function over this part and exclude simply this part. But it becomes a bit more tricky when you have a crack that runs into part of a support. So, what do you do here? Well, they've come up with 3 solutions, neither of which is really good. One is just do as if nothing has happened. So this is the so-called see-through criterion, where you just integrate over the whole domain, as if this part contributes as much. Well, that's not very accurate. This divisibility criterion is already much better and is used in most computations, where you exclude this great part. So here you have the node, you draw a line to the tip of the crack, and then further, and you exclude this great part. Well, if you want to be even more accurate, but at the expense of quite a bit of extra effort, you can have this so-called diffraction criterion, where this line diffracts around this crack. Again, there is no real good solution, but these are the approaches that are being used. Well, this is an example of computation. It's a 3-dimensional computation. Here you have a linear elastic fracture mechanics calculation with an initial penny-shaped crack in a square cube, or in a cube. Here you see it growing and growing, and here you see how it finally goes into 2 separate bodies. You can also combine, and that's quite good idea in fact, these meshless approaches with gradient damage approaches. And why is that? Well, unlike finite elements, you don't suffer from the problem that you need, that they are restricted to C0 continuity. You have no element boundaries, so the C0 element boundaries don't exist. And these bell-shaped functions, which are normally used, are usually differentiable for quite a number of times. So, if you have higher order derivatives, no problem. So, they are very suitable, for instance, to combine or to use within gradient damage approach. And here we have done some calculations for a bar with 2nd order, with 4th order, with explicit, with fully non-local approaches, and this works in those cases enormously smooth, enormously well. The only little headache you get is the boundary conditions, because that's a bit nasty. Here you see it also in a two-dimensional context. Here you have a 3-point bending bar. The load here, supports here. We take only a half with a symmetry boundary condition here, and we put nodes like this. We have a fourth order gradient damage model, and you get results that are very well converging. So this is one, in my mind, one of their big problems, big advantages. They have a high degree of continuity, which is ideal for higher order models, gradient damage, gradient plasticity models. Refinement, a local refinement, is extremely simple. You just put in some nodes, the shape functions come with them, and you're done. Most of the methods, and I emphasize most of the methods, need a background cell for the integration of the integrals. There are some schemes which have a null integration, so which have integration at the nodes. But this may not always be that accurate. So a Gaussian type integration with background cells is usually to be preferred. Now, these Glick boundary conditions can be problematic. Again, there's a host of solutions. One of the obvious solutions is again Lagrangian multiplier using. Yeah, it's a point of attention. Remeshing is simple, but when determining the domain of influence, especially when the domain is not convex, and like with a crack protruding into something, that is, yeah, you have to pull some tricks there. But in principle, it's a method that is suitable for discretization of discrete Glick propagation, but also for smeared approaches. And although it was originally proposed in the context of discrete Glick propagation, linearistic friction mechanics, in my mind, smeared approaches like gradient damage combined with specialist methods are the more powerful approach. To the best of my knowledge, it has never been combined with nonlinear friction mechanics such as cohesive zone models. And I think I would like to, because it connects very well, now directly go on with the extended finite element methods and the isogeometric analysis. So, extended finite elements. Well, the extended finite element method relies on the property that the shape functions, the polynomials in finite elements, satisfy the partition of unity. Now, what's that? Think of just a linear interpolation, just a one-dimensional element, which a linear interpolation here from 1 to 0, and another one here from 0 to 1. If you sum up these two shape functions, they are together 1 everywhere. These two shape functions are a partition of 1. They are part of 1. Together, they always sum up to 1. And obviously for linear, it's easy to see that. But this holds for any polynomial. So for quadratic, the quadratic Lagrangian functions, for cubic Lagrangian functions, for quartic Lagrangian functions, this property also holds. So when you sum the shape functions over the domain of a finite element, and it holds for 1D, for 2D, and for 3D, they always sum up to 1. And in fact, that's a property that is shared by many numerical schemes. For instance, in the functions that we just used for the meshless approaches, it's also the case. These monomials in this P vector contained there are also a partition of unity. If you then manipulate them and come at the final function. Now, when a set of basis functions satisfy this partition of unity function property, you can add other functions. So, originally, we interpolate our displacement as our interpolation polynomials, phi, times the values at the nodes, the nodal values. So it's a sum of I from 1 to n of phi I times a bar, ai bar. Now, if these satisfy this partition of unity property, you can prove that you can add other functions to this nodal value. So at each node you can define other functions. For instance, these psi j functions. So at node I you can define m other functions. Now, for instance, what you now can do is related to linear elastic friction mechanics. At each node, you can add those 4 singularity functions of linear elastic friction mechanics. And then this way, try to capture the singularity, which is very hard to capture using normal polynomials. So what you do then is at the crack tip, you enrich this by injecting singularity functions. So, going to finite element notation, we interpolate our displacement field as our interpolations are polynomials times our standard displacement, nodal displacements, plus another matrix which contains these additional functions. For instance, these singular functions. Of course, they have their own degrees of freedom. And note that here, for those ones, you have a multiplication. So when you elaborate it, U is equal to capital H times A bar plus capital H times capital H tilde times A tilde. The null displacement, the displacement parameters related to the additional functions. But you multiply the additional functions by the original polynomials, and that has the advantage that you keep this enrichment local. You keep it, if you have one node here with surrounding elements, they are non-zero only for the support of these elements. So these singularities, functions, the additional functions, are only there in the surrounding of the enriched node. So farther away, they don't bother. You only have them there, and it's a big advantage, and you want to have them. You don't need the singularity functions far away. Now, this can contain singularity functions, but it can also contain other functions. And another function is, for instance, this one. The Heaviside function times the unity matrix. And when you insert that into here, you have H times A bar plus the Heaviside function at this discontinuity times H times A tilde. So essentially, you split your displacement field in a rigorous kinematic way into one continuous displacement field plus another continuous displacement field, but separated by a Heaviside function which is exactly placed at the discontinuity of the gradient. So this is the whole idea of extended finite elements. Now, when you are doing linear elastic fracture mechanics, you have to do a mix of those. Suppose that your crack has gone to here, then in the part where the crack has already appeared, you put Heaviside functions as enriched functions. And at the crack tip, you enrich the interpolation with singularity functions. Well, I've said for cohesive zone models, you don't have a singularity, so their life is simpler. You only have to enrich the cracked part, the fully cracked part, and the partially cracked part with this Heaviside interpolation. Now, how does it work? Well, as usual, we have our balance of momentum. We have our interpolation of our trial functions, but we also have our interpolation of our test functions. And we do that in a strict Galerkin sense. So we interpolate the test functions in the same way as the trial functions. So we also interpolate them as one smooth field plus another smooth field, the continuous field, separated by the Heaviside function. Or at the crack tip for linear elastic fracture mechanics, we here then enrich it with the singularity function. So you get two fields, W tilde and W bar and W tilde. You can separate them, you get two sets of coupled equations. One related to one displacement field, to one side of the crack, one related to the other one. And at the crack tip, you have the jump, which in case of a cohesive zone model, you can use to feed your cohesive zone model. Now, there is a strong relation between these extended elements and the interface elements. In fact, interface elements can be regarded as the limiting case of extended finite element method. Because if you place so in principle, the discontinuity can run anywhere through the element. But if you put it at the edge of the element, then you can elaborate this, that you get the stiffness matrix of an interface element matrix. So then it gets a limiting case of an interface element. Now, it would be wrong to say that it is the same as an interface element, because in the extended finite element method, we propagate the crack during crack propagation. So we sort of generate, so to speak, the interfaces on the fly during propagation. So the whole issue of having infinitely stiff dummy stiffnesses prior to cracking does not arise at all, and therefore also not these traction oscillations. Well, this is an example of a linear elastic fracture mechanics calculation using XFEM. What we have here is a rectangular specimen loaded in tension here, which has an initial crack here and here. So an initial kinked crack. So let's zoom out in this area. And then you see here the crack. You see here that we have meshed it such that we run through the elements. And all these elements, where the square nodes are, these are enriched with a Heaviside function. Because there we have a fully open crack. Here, this element, where the crack tip is in, we have enriched with singularity functions. Because here, we want to capture the stress singularity. So, all these elements here, we have enrichment of the Heaviside function, and here, these three nodes, we have enriched using singularity elements. This is an example of a 3-point bending test using cohesive crack propagation. So since it's cohesive crack propagation, we don't need a starter crack. We can start with an entire specimen. And here you see some effects of mesh refinement. What you see here is some bumps for the coarser mesh. And this is related to the fact that you propagate, in that case, the crack through one element, and if this element is too coarse, you get a little bit of wobbles here, which disappear when you refine the mesh. So, how do you do it in cohesive crack propagation? Especially when you have heterogeneous materials. Well, you nucleate a crack, you look into the integration points. When some criterion has exceeded there, and here we have used a quasi-brittle material, a ceramic material, we looked at the principal stress direction, which is then reasonable. We initiate the crack here. And then at some point we look here and we propagate the crack here. And we propagate the crack here. But you can also have crack joining or crack branching in these cases. Here, this is a case of dynamic loading of a so-called Kaltov specimen. So you have, this is the symmetric part, so here is free. There's an indenter hitting here, there's an initial crack here, another initial crack here, and then the free part here. So here you see our simulation, which we did using X value. So you can do these things. I mean, this is, and the inclination angle is roughly the same, around 70 degrees, which was also observed in the experiments. Now the last bit, the most modern bit. Isogeometric analysis. What's that? It's essentially replacing the Lagrangian polynomials, which you normally use in finite elements, by so-called B-splines. And don't tell me that you've never worked with B-splines. Who has never worked with the cut package? All cut packages are based on B-splines. So, how do you define B-splines? Well, let's first show it graphically. In case of linear basis functions, there's no difference between Lagrangian functions and B-splines. This is the Lagrangian functions of a linear one-dimensional finite element. These are the B-splines of linear, these are the linear B-splines. So you start from the same point. But when you go to higher order B-splines, you get differences. I mean, here you see the Lagrangian polynomials. And here, the red one, the dark blue one, and the green one are the B-splines, the quadratic B-splines. Now there's one thing which you immediately see, hopefully, and that the B-splines have a so-called non-negativity property. You see, Lagrangian become negative here. Higher order Lagrangians. Higher order splines will not become negative. And especially when you go to dynamic analysis, this is a huge advantage, because when you construct, for instance, the mass matrix using Lagrangian functions, you have all sorts of negative entries there. When you do the same using B-splines, you don't get negative entries. And that gives you much better behavior. Now, how does it work mathematically? Well, again, we have some function A, which we interpolate with B-spline functions, the n here, and we have some parameter. Again, it's an interpolation function times its magnitude. And here, Ni is the ith B-spline of order P. And these are the magnitudes of them, which are measured at so-called control points. And these control points are usually not nodes. So they are defined recursively. So for a simple constant B-spline, it is 1 at a domain and 0 outside. Same as for Lagrangian functions. Then for higher order ones, they are defined recursively. And the B-spline function of I of order P is this interpolation times the one of one order less, plus here for the other node of the order less. Well, for linears, it just gives this behavior, same like a branch. But for quadratic, cubic, it gives different ones. Now, in fact, we don't use B-splines. And in fact, in cut packages, they don't use B-splines, they use nerves. And nerves are made out of B-splines. But they're a little bit more sophisticated, in the sense they are made by weighting them. So here you have your B-spline interpolation, you multiply it by a weighting function, and normalize it again by the sum of the weighting functions. Now, the advantage of that is that you can exactly capture certain geometries, like spheres. I mean, there would be no hope to ever exactly capture with a Lagrangian polynomial a sphere or circle. With nerves, you can exactly capture a circle, which has, of course, advantages when you want to describe a complicated geometry. For instance, when you want to model bone or something like this, then I can tell you nerves have a big advantage compared to Lagrangian polynomials, because you don't introduce artificial stress concentration. Because with finite elements you have a little bit like this, which gives you an artificial stress concentrator. Not so with nerves, there everything is totally smooth. Now, nerves, or B-splines and nerves, are essentially defined in one dimension. How do you do 2 dimensions? How do you do 3 dimensions? Well, 2 nerves in each of the directions. So you just make a tensor product in 2 dimensions or in 3 dimensions. You just have nerves in this, times a nerves in this, times a nerves in this direction. So you then, for 2 dimensions, you get a double sum. For 3 dimensions, you get a triple sum. Times here the parameters, which are these control points in 1 dimension. Now, a nice thing, these B-splines and nerves do satisfy the partition unity problem. So that opens up, in principle, adding singularity functions, adding discontinuities. Life is not that simple, but in principle it's possible. So that's nice. The next one is less nice. We have a tensor product structure. So you have interpolation in this direction, times 1 in this direction, times 1 in this direction. This prevents you from local refinement. So that's the disadvantage. There are ways around that, but I will not go in, which are called T-splines, but I will not go into that. That's really going pretty far. But they have some nice properties. You can very easily go from linear to quadratic to cubic nerves. That's a very easy process. And the nice thing is, you get higher order continuity, not only within the element, but also at element borders. So at Lagrangian functions, you always have at the element border C0 continuity. Not here. If you have a NURBS that is second order, and therefore C1 continuous, which means that the function is continuous, but also the slope is continuous. This holds inside the element, but also at the border of the element, at the edge of the element. Now, for structural engineers, displacements are interesting maybe, but the stresses are the most interesting. Stresses are obtained from displacements, and displacements are obtained by differentiating, stresses are obtained from strains, and strains are obtained by differentiating displacements. So if at some point you have a C0 continuity, a kink in the displacement field, this means that when you differentiate there, you have a jump in your strain field. This means that you have a jump in your stress field. In practice, and definitely around crack tips, this means that you have a messy stress field. This means that if you go and do the same calculation with NURBS, that your stress field is much smoother. And definitely around crack tips. It's an enormous difference which we have found. And in fact, this not only applies to stresses, it applies to any derived quantity. For instance, here I have a typical coupled problem, where I have deformation of soil coupled to flow of water. So a typical consolidation problem. Now, the important thing here is the flow of the water. Well, you interpolate the displacements and the pressures. The flow of the water is obtained from the pressure gradient by Darcy's relation. Now, when you do this with standard finite elements, you get this staircase behavior when you have finite elements. Essentially, your pressure is piecewise continuous, and therefore you have a discontinuity, your pressure gradient, and therefore you have this staircase, and therefore, since you have here a different value for the water flow than here, you have a loss of local mass conservation. Lots of efforts have been done to repair that, but if you have just a high order NURBS, and here we use only 3 NURBS, contrast to the 8 finite elements along this column, then you get it automatically. So any derived quantity is captured much better. The other advantage is that you get a new way to insert discontinuities. Because I told you that you have the possibility to very simply go to higher order NURBS. And you can go from linear to quadratic to cubic and so on. Similarly, you can easily lower the order of continuity. And if you have somewhere a C0 continuity and you lower it to a C-1 continuity, you have a crack. Because that means that there's a jump in your field. So you can exploit that. And essentially, that is what is shown here. You can do a knot insertion to lower the order of continuity. But you still have the good old interface elements, which you can also formulate using nerves. And you can also formulate splines directly on triangles. There are some buts still, but you can do that. And you can try to marry the best of two worlds. You can try to combine XFEM and IgA. And then you get an extended IgA where a crack can run through an element. These things are at the moment quite a bit in development. It's not that trivial because one of the issues is that, like measureless methods, nerves have a little bit of a problem with irregular boundary conditions. It's easier, but you still have to be careful. And that shows up when you do this kind of things. So let's first go to interface elements. And I go back to this example which I showed for the traditional interface elements. Here an interface, pre-put, here a notch, and well, here we go to more stiffer behavior. And in fact, for interface elements, one of the remedies which is now known and which is often used and also implemented in most commercial packages is that for interface elements you don't use Gauss integration, but you use Newton-Cotes integration or Lobato integration. That helps. Well, unfortunately it doesn't help for isogeometric analysis. So we looked here at this beam, where here we have the notch and here we have interface elements. And then we looked at Gauss for low stiffness, all fine. We got huge oscillations for high stiffness, much bigger even than with traditional interface elements. And in fact, this is what I call the curse of higher order interpolation. In these cases, a higher order interpolation, more smoothness does not help you. At some point, I also did a calculation with a shell element, a thin shell element, where you get wrinkling. In this case, the standard finite elements converge much faster than when we had an interpolation using NURBS. And the reason is, when you have wrinkling, when you have the possibility to have a bit of kinking at the C0 continuity line between elements, that helps you. I mean, it's not the good way, in fact. You make an error to an error, but it helps you. Well, if you do it totally properly, using the right continuity with NURBS, it converges slower. So, it doesn't always help. The problem is now even that with Newton-Cotes it doesn't work. So the only way where we could get it working is when we had here a lumped integration. So only then, with nodal integration, we got it right. Don't ask me why exactly. This is just trial and error. Now, this is regarding knot insertion. So we start with a case where we have the blue interpolation. These interpolation functions. So we use these nodes. Now you see that at this point, at point 5, we have a C0, so this should be C0 continuous, typo. This should be C0 continuous here. I mean, the function is continuous, but we have a kink. How can we make this into a jump? Well, we just multiply the number of degrees of freedom at this point, and then we add essentially a direct type function for the stress. We add a jump there. And this is a way which in nerves is very easy to realize. So this is an example of that. Here we have epoxy. Here we have a hard fiber, and we have an adhesive layer here, which is loosening up at loading. You see here the meshes about mesh refinement, you get very quick conversions. This is another case where we have really followed a crack and adapted the mesh to that. The advantage is you have a much smoother stress field and therefore a very good prediction of your crack direction. Here you see the crack, and here you see the gray area, you see experimental evidence. Another one where we have a double notched specimen, cracks propagated like this, and here we have, no, we don't have here. The point is this is one where we have still some issues, which is related to the fact that it's very difficult to mesh such a domain with two cracks. To propagate cracks such that they really cross mesh lines is difficult if you don't have IGA. And then you would have to construct this like in cut packages of multiple patches. The problem is then that you have a patch here, a patch here, a patch here, a patch here, one here, one here, one here, that you have zero continuity lines here which destroy exactly what you want. So this is something we are currently working. Now finally, splines, B-splines constructed on triangles. So here we have the black triangles, the big black triangles, which we have just a normal linear interpolation. And we split each of these triangles into 6 mini triangles. And then we construct these green points, and we make red triangles around each of these nodes. And then on these red triangles, we can construct splines, which are then smooth across these elements. Now, this works enormously well. There are some problems. This exact capturing of the geometry is not possible. The order elevation, as you know, is not as easy. And the extension to 3D is not rigorous. But you can do very nice crack propagation. Here you see again the notch specimen, and you have a curved crack propagation with easy, very easy standard remeshing. And here you see the stress profiles, very smooth, very continuous, and the convergence when you go to a higher number of degrees of freedom. Another case, this case of the Nora Mohammed specimen with double notches. Here you see the crack propagation with the stress contours, again, smooth contours, well defined, and these are just the advantages of these approaches. Also the crack propagation paths are in agreement with the experimentally measured ones. So, in sum, isogeometric analysis has promise for discrete fracture. There are 4 potential approaches. At the moment, each with its advantages and cons. you can use NURBS or T-splines with non-insertion. It's enormously elegant, fits excellently with all concepts. You are somewhat restricted to the crack path. Powell spin B-splines, very straightforward. If you can arbitrary crack paths, you can use traditional remeshing schemes. The disadvantage is that it doesn't really conform with the isogeometric concept. And also, it's not really totally, it's not evident how you can extend it to 3D also for unstructured meshes. Isogeometric interface elements, very easy to formulate. The disadvantage, as with standard interface elements, is that you have only for predefined crack paths and for spurious traction isolations, you have to do some special meshes. And yeah, finally, extended isogeometric analysis. A beautiful blend in principle of XFEM and IGA. There are some results published in the literature, but they are not really, I mean, there are some drawbacks if you really go dive into it. We are working on it to make them better, and it could become a very nice development. So I think that was what I wanted to tell you. Don't expect that you have necessarily understood all the details, but it's giving you a flavor of what is possible, and I've tried to sort of warn you for some of the pitfalls and show you some of the avenues to possibly go. Thank you very much.
You have heard the last few days some fundamentals about fracture mechanics, and you have seen that fracture mechanics is a certain type of continuum mechanics. Yes. And continuum mechanics has, in principle, no scale. Yes. But even when we look, now look to our fracture mechanics, which we use for industrial application, we usually use this for dimensions in centimeters, or the fracture mechanics samples are usually also larger than typical 50 millimeters or larger. That's our typical size. And even in this region, we have a lot of discussion of sample size effect on, for example, fracture toughness, or in the case of short cracks, the problems that short cracks grow different to long cracks, and so on. So even in this case, and there are for many fracture mechanic scientists thought that fracture mechanic to microsamples is not really applicable. But I will try to show that we have to go this way, and this is really a new area in fracture mechanic. And this, on one side, is important for design of sensors, of microelectronic devices, and also in order to understand better the fracture behavior of our materials. I am working mainly in this area, but also working together with some industrial partners to use this also for microelectronics. So let's go. So here you can see the main reason why we are doing this research. One is the industrial-driven things are, you have a miniaturization of components, especially in electronics, sensor technique, and also in medicine, but also in many other areas. Here you can see a stand, or if you look to wires where they try to connect nerves and so on. Yes, so these components are extremely small, and they are heavily loaded under fatigue, and so it is very important what happens under fatigue, what happens when they have small defects. Will they grow or not? This is one driving force for this development. The other area for the development of these techniques is that material scientists often want to know, they have complex structures, and they want to know the individual properties. Yes? For example, this was one of the driving forces at the beginning of our researches. It was to know the mechanical properties of bone in different regions. Yes? And or to know the mechanical properties of wood in a certain area, for example, in the wood wall of the cellular material, or if you look to simply steel materials, what happens when you have this, for example, lamellar arrangement of cementite lamella in pearlitic steel. How are the mechanical behavior in the different direction, or what is the interface strength, and so on. So there are a lot of problems in this area. And here you can see typical failures. This is a typical coating failure. In this case, it was a hard coating on a relative, or yes, it was a hard coating on hard metal, so they are to relative brittle material. Here you can see the thin film on a polymer substrate. Then there is a large development in flexible electronics. You simply think on these rollable screens, or but also for medical application. And here you see a typical failure of a power electronic component. This is a part of a transistor where you have a disconnection of the component, and it is nothing else than the growth of a crack and the failure. And most failures now are not cars, bridges, or something like. Most failures are failures of microelectronic devices. The power supply of these, and all these they are not simply a failure due to the stress. They generate crack, growth crack, and the component fail. And the electronic engineers have not realized this, so they have done a lot of stress strain calculation, yes, like what mechanical engineers have done nearly more than 200 years, since more than 200 years, the electrical engineers do this also. Yes. But they have not introduced structure mechanics, and this is a new area for them. Okay, so here you can see different test techniques, micromechanic test techniques. Here you can see that's one of the first, which goes down to the nanometer region. It was nano-indented, so where you simply make hardness measurements, yes, or friction measurements. There are different types of test techniques in this area. But you can go down to indentation depths of really few nanometers, yes, and really get mechanical response. Because the difference to classical hardness test is that it's really instrumented. Yes, you measure the amount of indentation and measure also the force which you need. And from the indentation, from the force and the depth of indentation, you can directly calculate the hardness from simple geometrical relations. Then here you see another very popular, now popular test technique, which was introduced about 15, 18 years ago, the so-called pillar testing, where you simply machine such small pillars and then you make a compression test. Or case of bending, this have we introduced for semiconductors. It was introduced somewhat earlier because with etching technique it was easier to produce it, but then for metallic materials we have introduced this in the beginning of 2000, and also fracture mechanic tests on this scale. So these are typically few microns, yes. These are 3 microns, these are also 3 microns, 2 micron thick. This was a fracture mechanic test on these dimensions. Or here you can see a tension sample, yes. Also 2 microns, or you can, but you will see it on, I think, on the foils which you get. I think the resolution is not sufficient here. Or here, and these are the smallest tension samples, really tension sample where you get stress strain curves, yes. And the size of them is 200 nanometer, yes. You can really look what happens in the interior of the sample. Okay, in order to get the feeling for those which are not so familiar with these small dimensions, yes. I have plot here, this is a human hair, yes. The human hair has a diameter of about between 50 and 80 micrometers, so somewhat smaller than 1/10 of a millimeter. Yes. And this was the micro tension samples, yes, which are tested typically in a scanning electron microscope, and this would be the real 200 nanometer thick sample in relation to the human hair. That's really tiny things. Yes. But in your electronic devices you have a lot of these. Yes. They are even smaller. And you have to predict the mechanical properties of them and the failure properties of the different structural elements on your device. Or functional elements of your device. Okay, so you would say, okay, that's really tiny. Yes, it is hard to look to a hair. And the question is how we how did we have to go? Okay. How we perform such experiments. Okay, we have to do this always in the scanning electron microscope or transmission electron. They're very fine in the transmission electron microscope. What you have seen is we have this tiny sample. We arrange this in the scanning electron microscope. Then you bring, for example, this gripper into the focus of the system. Then you take out the sample out of focus, go above, and then you move the sample below as long until the sample is again in focus, and then you can perform the tension experiment. Okay, now what are the ways to produce these samples? The most used tool, especially for metallic material, ceramic material, are these focused ion beam systems. In most cases now, since this focused ion beam workstation was introduced in the 1990s, originally I think the semiconductor industry have it developed. They always call it for inspection, but in reality, they have buy the instruments for the inspection of the other companies' product to look how they made the devices and how they could realize really such small devices and so on. But then they also use now this really for repair of prototype and so on. So what is this is now a typical system which in this form, they're about 20 years old. You have always electron microscope, a really high-end electron microscope, typical of field emission microscope, so that you have really a resolution of 1 to 2 nanometer. And then you have here an ion microscope, typically usually the so-called gallium, they have a gallium source where there is simply a droplet of gallium, and they apply a voltage on the droplet, and then they form a needle like the droplet. And from the tip of this needle you get ionization of the gallium, and then you simply accelerate and use it. You can use it for imaging, you can use it for removal material, and sometimes you can also use it for deposition. And if you use it for deposition, then you introduce a gas in typical, for example, tungsten, chlor-tungsten, or platinum chlor gas mixture, which you very localized deposit or flow over the sample surface, and then you crack this, and then you can deposit, for example, tungsten, platinum, or other elements on the sample. But we use it in micromechanics usually only for removing of materials. This is the gallium is in a gallium FIP has approximately a resolution similar to a standard scanning electron microscope. So with approximately this precision, you can machine also samples. The xenon is a different type of source, so but much higher current, and you can remove much more material, but the accuracy is not as high. Yes. Or what is now? Okay. Another technique which we have recently developed in our institute, and I think this will come in the future, is this femtosecond laser ablation. This is a new technique where one can, this is again, I apologize, these are about, I think 1 millimeter, no, not one, I think 1 millimeter. So they're medium-sized samples in a tungsten foil. So you would say, okay, that's our, at the border where what we can machine with classical machining. So if we would produce, these are all tiny bending samples. If we would use the FIP with this, one would work about 1 year. Yes. With a femtosecond laser, it was half an hour. Yes. So you see the enormous difference in time with this system. It is not as accurate, and you cannot produce very fine notches because you are always limited with the focusing of the laser. Yes. The reason why we use femtosecond laser is very simple. In this case, the removal of material is different to classical laser machining. The classical laser machining melts the material and it evaporates. Yes, if you use, for example, a nanosecond laser, and with a nanosecond laser, you can really buy such a system, which is also connected to a FIP. It is here in the pre-chamber, this femtosecond laser. Then we can really move. We can machine the sample in this pre-chamber, go to the SEM, and can further refine the cutting with the FIP. You can buy a nanosecond laser system, but with this nanosecond laser you have the typical evaporation of the material. You have an enormous heat impact. But with the femtosecond laser, the pulse is so short, it's only one wavelength or two wavelengths, yes, in length. And what you do is you get the ionization of the near surface atoms, and these ionized atoms flow away. And you have nearly no heat impact into the material. And it is also important that you can remove any kind of material. Yes, you can also remove from transparent material. Yes, in principle, it is the same technique what the eye doctors use for cutting of or removing of the iris and so on. Okay. So here you can see a typical prepared one of our first fracture mechanics sample, which we have prepared. This is now here 10 microns. We need about half a day for this. Yes, it's quite time consuming. Yes, I will now try to show how we can prepare such a sample in a very simple way. So one prepare a sample with an edge, and then one look along the edge on which area I want to have my for example painting sample, but the same can be done with a tension sample. Okay, then I remove it first in order to get all the machining problems away from polishing or preparing the edge. Then one remove the material behind, and then one turn the sample, remove this type of materials, and then one cut this. And finally we have a simple like this sample. This was a special sample which will come at the end tomorrow for residual stress measurements in this thin film. You see that this beam is bent, which is a consequence of the Another simple, which is somewhat faster, is when we prepare samples from needles, needle-like pre-products, where we use etching techniques. And then one, especially if we look then to single crystal behavior, then we use this needle technique, because in this case it is not necessary to take the sample at a really well-defined position. In case if we do this in a microstructure and want to measure, for example, the interface toughness, then it is required to prepare the sample at a well-defined position. But if we do it in a single crystal, we can start with a needle, then one remove the material on these two sides, rotate the sample by 90 degrees, and then you have the final shape of your tension sample. Another simple technique which you often use, especially for mass production, is you have a very tiny stainless steel plate, typical 10, you can buy it with dimensions from 8 to 20 microns or even larger. Then when replace this above the sample, then you remove the material with a powerful unisized argon beam. Then you have here, these are now millimeter in length, and the thickness is, you see, 4 microns. And then you have a wall with 4 microns, and then you can simply machine what you want, yes, in this wall. And again, you can tell bending, fracture toughness, fracture experiment, tension experiment, fracture experiment, tension experiment. Then you can perform. So now, how you test it? Usually, especially when you go to the nanometer dimensions, you have to do this always in the transmission electron microscope. When you have samples in the micron dimension, you usually do it in a scanning electron microscope, sometimes only below an optical microscope, within the optical microscope. Especially when you want to look to environmental effects, then you go to optical microscope, but sometimes there exists also environment scanning electron microscope, but it works at somewhat lower pressure than so it's about few millipascal pressure. Okay, this is one of the devices, what we use, which is originally designed for fiber testing, or in the most cases one uses nano indenters, type of micro or nano indenter instrumented instrument which can measure the load and the displacement, which are originally designed for this nano indentation experiment, and one uses it now also for these micromechanic devices. Here you see one, this was our first device which we have used for tension and compression devices. So this is a piezo-driven system, nano indenter. You have here this gripper, and then you come with the sample with the procedure what I have explained before. We go to the sample, go above, bring the gripper from the nano indenter in the focus plane, then we take our sample, go out of focus, move above, and go above the sample, the gripper, go with the sample into the focus plane, and then we can perform our tension experiment. Okay, so much to simple the testing procedures and how we can do. We can make the samples and how we can perform the mechanical experiments on these length scales. But the course here, we're not focused to this mechanical experiment. It is more to fracture mechanics. Yes. And at first, let me start with a very basic thing related to the length scales, which are important, which we have always taken into account. Sometimes we have also taken into account this in macro experiments. Yes, it's not only limited to micro experiment, but in micro experiment is really evident, and only very seldom that we can forget them. Yes, that's and therefore I will say some basic things about the important length scale, and then I will talk about the important things which we have to take into account when we think about the scaling effect, the effect of scaling on the fracture resistance. Before we discuss this, we have at first to discuss or to understand what is the effect of scaling on plasticity. Yes? Because when plasticity evolves, this plasticity is also affected by the scale, especially when we go down to the micro dimensions. And then in the second part, we go then to the fracture resistance. In order to do this in a really some way to understand what is the impact of the scaling effect on fracture, it is very helpful to look what are the effect of this scaling in ideal brittle material, in semi-brittle material, and in ductile material. Okay. And then I will discuss during this course only the effect of this mechanism on toughness and fatigue crack propagation, not on creep is also important, especially in electronic devices, power devices. So they get heat pulses up to 200-300, the copper layers of up to 200-300 degrees centigrade, and copper creeps, also aluminum creeps at this temperature. So it is really a creep fatigue problem in many of these cases. But in my talk, I will only talk about toughness and fatigue crack propagation. But in principle, all what we discuss during this course can be also transferred to these creep and or environment-assisted cracks and so on. Then I will, during the story, I will also look to some case study, and then at the end, I will also, I hope that we can become so far, talk a bit about thin film problems, which is an area for itself, yes, because it is a bit more complex, because we have always the problem that we have different type of materials, we have a mismatch between the different materials, we have different elastic properties, we have different plastic properties, we have different fracture resistance, we have interfaces, and interfaces have again its properties. They have again fracture resistance, a fatigue resistance, and so on. So, and this makes it a bit more complex, but I will. Hope it works. I don't know why. Here. Okay. So you have heard yesterday, I think you will have heard it, that we have in principle two ways to go to fracture mechanics, or in every textbook you see this, yes. You have one way, it is an energetic approach. This was originally introduced by Griffith. And then also Irwin have used this to transfer this idea to engineers, yes, this energy approach. But in principle, he has also developed this stress-strain approach. And I will mainly follow this stress-strain approach. The reason is quite simple, because in this stress-strain approach it is so easy to see the important length scale, which we have to take into account when we look to the fracture of microsamples. Okay? So I think that's well known for persons which work in fracture mechanics. These are the stresses, these are the tension stresses of a crack loaded in tension, so it involves one loading. And what happens at very small loads in a linear elastic material, and also even in a linear elastic elastoplastic material, at very small load you will always have this type of behavior. You have near the crack tip, you have the near crack tip field, which has the square root relation of the square root decrease of the stress as a function of the distance. And then you have the far field stress. Okay? When your material is is ductile, and you load it further, then it will start to the plastic deformation. You will form a plastic zone. This is for a hardening material, non-hardening material. The stress would be constant in the non-hardening material. In here within the plastic zone. If you further increase the external load, the plastic zone will increase in size. Yes. And as long as the plastic zone is embedded in this K-dominated area. We call this small-scale yielding. We can use the stress intensity to describe all properties of a material. Because at a certain stress intensity, we will always have the same stress field in front of the crack tip. That's the basic idea, yes, for small-scale yielding. If the ductility of the material is sufficient high, yes, we can further load up our material. And if the applied stress becomes near the yield stress of the material, we come to the full scale and large scale yielding properties of the behavior. And then in the near crack tip field, we have the so-called HRR field. Also here, in reality, we have also here in the near area this HRR field. In reality, we have here a certain transition. I will not go into detail, but for simplicity, I simply draw this in this way. Okay. Yeah.
For linear elastic or ideal linear elasticity, won't the curve go to infinity at crack tip?
Yes. But the problem is, it makes no sense to draw this line at distances smaller than 1 atom distance. In continuum, it goes to infinite, yes? At some femtometers or something like, yes? But at these length scales, the stress have no meaning, yes? But from continuum mechanic point of view, it goes to infinity. But definition of a stress for a material has only sense if we talk about distances of our atoms. If we go smaller than it makes no sense to talk about stresses. So in reality, it goes further here. Yes, it comes later. Then also what really happens in this area in detail. Okay. Good. So it is in principle, you would, if you simply look only to the stresses, it would not be clear why our material failures. This is much easier to visualize if you look now to the strains. In the linear elastic case, you see this here, it is clear, it is a linear elastic relation. The strains behave exactly as the stresses. So we have, again, this square root relation here. In the small scale yielding region outside the plastic zone, we have again the same behavior. But when we now come into the plastic zone region, then we see the singularity of the strains become much stronger than in the linear elastic case. Yes. If we would have a non-hardening material, we would have a 1 over the distance singularity. It's much stronger than 1 over the square root relation in the elastic case. Okay, so if you compare this. If we have a non-hardening material, we would have the yield stress here, or we come somewhat later due to the multi-axiality. Only the equivalent stress is equal to the yield stress, not sigma 2. It can be 3 times. That's another story. Okay. So that's important. And so the strains here very near the tip curve are extremely high. And these are the reason why we have this localized crack propagation. Okay? So now we have seen the different regions of the stresses, and in all our consideration we have to look how large are the different areas in relation then in relation to the fracture process, in relation to the sample, to the in relation to the microstructure of our material. Okay, so the first important length scale, I would say the most, or one of the most important, is the so-called K-dominated region. Yes, I call it here the RK. Yes, in this region you can use the near-tip solution, what you usually find in every textbook about fracture mechanics. Okay, this is important. Also, when you look to linear elastic fracture, to pure ideal brittle material, then the next point is the plastic zone size. In the case of, yes, which is embedded in the K-dominated zone, and this is related again, is only related to the K value and the plastic deformation behavior of the material. The same, no, somewhat different is with the HRR field. It has a similarity to the K-dominated area. It is usually somewhat smaller. Yes, one can look how far are these simple description for Bauer law material describe the stress field, but nevertheless it is again related similar to the sample dimension as RK. They are only dependent on the sample dimension. They're not dependent on loading. Okay, and then we have a region where the fracture really takes place. A different type of materials. This has a different size, but it's, I will call it the fracture process zone. Okay, so let us now at first look what is the size of this K-dominated region. So you always see, and for this I have here plotted or here used the most condensed form of the real complete solution of the stress field in front of an infinite plate with a through thickness curve. Yes. And here you can see the equations. They are, yes, one may say difficult or not difficult, but I think it is very condensed in this form. So the only thing you have to take into account what are the different radii and what are the different angles. But in principle, this is what you can do even with high school mathematics, yes, to calculate the stresses. Not to derivate it, but to look how are the stresses. So here we have plotted now the maximum shear stress for a mode 1 loading crack of this length, and you see here at far distances the maximum shear stress is about 1/2 of the bright stress. But you see the stress is really complex. Here it is nearly 0, and here we have an increase, but the increase is not as dramatic as one thought at the beginning. Yes. Okay. Now I have looked now to the. This is now the half the crack length. Change the scale, and you can see here. Oh, that looks very similar what we know from the textbook about this equation here, the near-tip relation. And here, when we really go very near the crack tip, then you can really see. Okay. That seems to be that it is really possible to separate our stress in a radius-dependent term and in an angular-dependent term. The postage remains always similar to the shape. That's a very indication that such things happen. So these are the well-known equation which you have already heard yesterday. Now, with this square root relation of the stresses, sigma 1 So the important thing if you go along in front of the crack is that you have enormous hydrostatic tension loading. Sigma 1,1 here in front of the crack is equal to sigma 2,2. That's at first a bit surprising, but it is so. Yes. Really, the two stresses, you have loading in this direction and the stress in the crack growing direction is exactly the same value. Yes. And that's a shear stress for the other. And in the thickness direction, you have simply, for the plant strain case, the 2 times this value, or this value minus 2 times the Poisson ratio. Yes. Okay. Now I have plotted here the stresses sigma 1,1 again in front of the crack and sigma 2,2 in front of the crack. And this is the near tip solution. This is the square root, because in a log plot it is a line, yes, with a slope 1/2. It's quite easy. Okay. So, and here you see this is about the crack length, the ratio, the distance divided by the crack length. So this is about the crack length. And, oh no, excuse me, this is 1/10 of the crack length. And what you can clearly see that up to about 1/10 of the crack length, the near tip solution is a really good approximation for the stress in the loading direction. The crack for the stress in the crack growing direction, yes, it is a good maybe approximation, but there is a certain deviation. And I would always say, okay, for stress, for distances larger than about 0.2 times the crack length, the deviation becomes really large for the loading direction and extraordinarily large for the crack growing direction. So these near tip solutions, yes, are valid approximately in this area. Okay. As long as you have the crack is small compared to the other dimensions of the sample. This holds for a relative long time only when the crack becomes is nearly as long, or the ligament is small compared to the crack length. Then the ligament is the controlling. The ligament size is the controlling value for the size of the K-dominated area. It is approximately again about 0.2 of the ligament width. So that's a rough estimation. Yes. Okay. So the important length scale and the small scale yielding are first which we know now more accurately is the K-dominated region. Then important is the plastic zone size, and the small scale yielding the HRR field is not as important. In some cases, when you look to the special semi-brittle materials, then the stress state is also, the real stress state in the plastic zone is sometimes important to understand it, but important are the plastic zone size and then the fracture process. So when we go to linear elastic fracture mechanic, then you have this K-dominated zone, and in order to be in the small scale yielding, the plastic zone size must be embedded in this K-dominated region. That's the reason. And then we have here in front a certain region where really the fracture takes place. And then we have another parameter which we often will use for as an important length scale, because the fracture process zone, especially ductile material, is in is always a certain in certain relation to this corrective opening displacement. But it is the plastic opening displacement. We'll have to distinguish. In the elastic case, you have a certain elastic opening, and then you have, in addition, when plasticity starts, you have a plastic opening. So in order to understand the different lengths, there is a very nice things in fracture mechanics. Really, if you simply take in a small scale yielding the square of the stress intensity and divide it by a stress to the square, yes, then you always end up with a length scale. And these length scales are really characteristic, yes. If you divide the square of the stress intensity through the applied stress to the square, you get immediately the crack length. Yes. If you divide the square of the stress intensity to the yield stress, you get the plastic zone size for a plastic deformable material. And if you divide the stress intensity factor to the square through the elastic modulus or the shear modulus divided, and the yield stress, which is again stress to the square, yes, two different stresses, then you come to the corrective opening displacement. Yes, and funny things which may be not so familiar is if you divide the stress intensity to the square through the yield to the shear stress to the square, you obtain the opening, the elastic opening of the crack when the first dislocation starts to propagate from the crack. That's really, really nice length. And I think, I do not know if he was the first, but I have found it the first time this in the book of Wertmann. Yes. He called it the magic length scales of fracture mechanics for small scale yielding. And it's really impressive because, especially for persons which are new in fracture mechanics, I have studied physics, and when I come to fracture mechanics, I was always, why we have this crazy parameter with megapascal times square root of meter, yes. It's really, this is a driving force for crack. Not so easy, yes, to understand in the beginning. But if we do this, this is really, really clearly visible. In the elastoplastic case, then the difference is, if this is the size of our sample, important that our fracture, the fracture mechanic properties which we determine, if they should be size independent, the requirement is that the HRR field, which develops in front of the crack tip, the Hutchins-Rice-Rosengreen field, I think you have heard this yesterday, this HRR field should be significantly larger than the fracture process zone. If this is not the case, then you have always to expect that you will have a significant size dependent of what you measure. Okay? In order to look now about the size of the fracture process zone, it is really very helpful to divide our material into different classes. Yes. The first one is the same ideal brittle material, and you may know also the last one is the ductile, and then we have somewhat in between. We call it the semi-brittle. Maybe I should make a one comment to the definition of brittle and ductile. This terminology is not so clear in the community. For example, civil engineers and sometimes also mechanical engineers have a different definition for brittle failure than material scientists or physicists. Yes. The reason is quite simple. For civil engineers, if a structure fails without macroscopic plastic deformation, you think, okay, this was a brittle failure, yes, because I have not seen any plasticity before, yes. But in reality, it may be really a ductile fracture because it was a small scale yielding problem. The yielding and fracture was very localized, and he could not see this on the macroscopic structure, yes. On the other side, and only when they see that the component really is plastically deformed before it fractured, they call it ductile, yes. But that's not really related to the processes. In the case of the material scientists, have a definition, okay, I have a ductile material, a ductile behavior when the crack, when I have a crack, during loading we have a blunting, and then we have a generation of pores in front of the crack. The pores grow during the further loading, and finally the coalescence, and finally this area coalescence with the crack tip, and I have the crack propagation. This is ductile from material science point of view. And the crack tip opening displacement can be extremely small, yes, in some of these materials. For example, if you look to ultra fine-grained hard metals, which you would say is exceptionally brittle material, yes, but they fracture in such a mode. But the crack tip opening, the cobalt film between the hard tungsten carbide particles is so thin that these films and these pores are only the size of a few nanometers. Yes. But it is a ductile process. That's the real brittle material is the best ideal brittle material is silicon. Yes. There are several semiconductors which are more or less ideal brittle. And in this case, the fracture process zone, that's always in the order of few atom distance, so few nanometers. Yes, typically 1/3 of a nanometer is the distance between our atoms in most of our materials. Very, very easy. I don't know why this happened.
Maybe we need the power source.
Okay. Yes, sir.
To avoid the standby.
Okay. Okay. And so there is easy. The length scale, the fracture process zone, it is always in the order of 1 to 3 nanometers, not more. Yes. And in this case, it is always few times the crack tip opening displacement. So it is, but this crack tip opening displacement can vary in our materials over extreme large values. Yes. In most of our engineering material, if we look to steels or aluminum alloys, titanium alloys, it is in the order of 20 to 100 microns. Yes, 100 microns is usually relative ductile or tough metals. Only in pure metals or austenitic steels you can reach 500 microns. So the semi-brittle material, the fracture process zone can be exceptionally large. Yes, it can be very low. If we look to nano composites, it can be quite low, but it can be exceptionally large. The most well-known fracture process zone large one is concrete. Yes, in concrete you can have fracture process zone in the order of meters, and even in meter-sized samples, it is always questionable: are these not size? Are the determined fracture parameter not size dependent? Simply due to the reason that our fracture process zone is larger than our K-dominated region or our HRR-dominated region. Yes. So even in really large samples, we have this problem of sometimes of size dependence, even in meter-sized samples. I will show you here one example of a material. Unfortunately, you cannot see this. Should be a fine lamellar microstructure. Its colony size, well, this is, I think, 50 microns, which is used nowadays as a high temperature material in airplane turbines, especially in the temperature region below 700 degrees C, typically. So the last 4 to 5 rows of blades. And it is used in this so-called lamellar, fully lamellar microstructure. You can have this type of materials in many different, like steels. It is really very complex material. You can generate enormous different kind of microstructures. But for this high temperature application, you always have this fully lamellar microstructure, which has a very good creep resistance. And the size of these are a few microns. And I will now try to show what happens during fracture of these, if you have a crack here inside, and how the crack propagates through such a microstructure. And what we have plotted here is the stress intensity factor and the crack extension. And this is the fracture surface, yes, of a fractured sample. This was the notch. Here, very tiny, small area is the pre-crack, okay? And we have measured the crack extension during the loading in situ in a scanning electron microscope. And here it was the notch somewhere. And now we have loaded the sample, yes? And if the load is transferred to a stress intensity factor, so first, you see even during this very first loading, from here to here, you see the crack is extended over this region. This is 2 microns. Yeah? No. This is 1 micron. Okay? About 1 micron grown over this distance. Relative brittle. Then, in the next step, you see that it's only planted this area. Excuse me. From here to here. Now that's one further. From here to here. It is only a bit planted because it opened. These are now 10 microns. Okay? And you see a certain amount, even in this, yes, semi-brittle material, you have plastic deformation. Now we have further loaded. Crack is grown over the short distance, and it seems that the crack develops here in front of the crack. Then, if we further load, this was the crack position before. We have this cracking, and here this remaining crack. And then, if we load here, these colony fracture, this is exactly this colony here, okay, which fracture. Okay. And then, if we load further, this was the crack before. See? Okay. The scale has changed here from if we have here before. These are me, but you can clearly see this was the crack before. Now, the crack developed here in front of the crack. This is in principle surprising. Many fracture mechanic persons often discuss, yes, there's a crack generation in front of the crack, yes. But that's not true. The stresses here, if we load this crack, and the stresses here are very low, it is unexplainable how a crack could generate here. What really happened is, if we look here to this region, the crack funnels here in the interior, and here is a, unfortunately it is not so clearly visible, but here is a really nice lamellar area, and this lamellar area fracture, and only this bridge remains. Okay? So the fracture process zone is here in the order of a few hundred microns. Yes, we see here from, or nearly 1 millimeter. Yes, half a millimeter. Yes. Where you have, if you load further, then you have this fracturing of the bridge, and finally you have the fracture. A similar behavior a long time before was seen, for example, and this is the case in many of stable grown cracks of steels in the low temperature region. Yes. Here again, this is a pure iron. It was not published. It was one of my first diploma students who worked in this. And you can see this is a crack in a DCP sample, and the crack is grown here. Some of the grains are fractured, but in reality they form into a network, and it remains a kind of bridging zone. And this can be really large, yes, in the order of several hundred microns. So the size of the fracture process zone in semi-brittle material can be extraordinarily large. So in such material you will never determine a size-independent fracture toughness on a micro scale. What you can measure are intrinsic properties here, but you cannot measure, or you can measure fracture resistance, but it will always be size-dependent. Okay? Okay. So in order to have in our macros, if we come from the mechanical engineering area, we usually work with metals, and most of our metals have grain sizes in the order of 10 to 100 microns. Yes, and in most of these cases, the microstructural dimensions are small compared to the size of the K-dominated area of our macro fracture mechanic samples. And they are also small compared to the plastic zone size. And therefore, get really a single value material property value. In case of, or especially of ductile material, in case of semi-brittle, it is not always and this is usually now not the case when we go to micro dimension, with exception if you have really grain sizes or composite sizes in the nanometer region. Then the microstructure is again small compared to micro dimensions. So if we now look to the fracture processes, especially in the if our sample size come into the micron region, I have to take into account these length scales of fracture mechanic, and I have to take into account in many cases also our microstructural dimension. because then our structure of our material becomes important. It's not, we cannot homogenize our material. And here, this is a typical, for example, typical grain size of a deformed aluminum alloy. Yes, typical microns, say 100 microns or larger. But on the other side, you see there exist also materials, ultra fine grain, nickel, where you have here grain size in about a few hundred nanometers. So if you have a sample with 10 micron size, then you could be homogenize the properties of this material. But if your sample is only 1 micron, then you have to take into account the real microstructure of these materials. It will depend where you have the crack in the microstructure. And when you go further, these are about 0.5 microns. This is a transmission electron microscope, and these locations, I will come somewhat later to this. These are the carrier of the plasticity. They form, you can see that small deformation, you can see this simply as line in the microstructure. These are typical precipitation, I think it is an aluminum alloy. And so you have, if you have now sample dimensions which are in the 10 micron, then you have not to take into account these local microstructure. But if you make samples of 100 nanometer, you have to take into account. This is a heavy deformed metals where the dislocations are extremely dense back. These are 500 nanometer or 500 nanometer where you have millions of dislocations. And this is here one dislocation in a crystal where you see here, this is a perfect lattice, a high resolution image, and here you see one defect. And if you look to a metal, always in this with this resolution, you will see always a nearly perfect crystal. Sometimes you will see such a defect. That's one of the really big questions 100 years ago. They have performed X-ray analysis they have developed the diffraction technique and have seen, okay, if we deform our material, it always remains crystalline. What happens there, yes? And the only thing what happens is that this defect moves. And if you look very carefully, you always see these nearly perfect crystals. And so if you make a modeling of the material and you say, okay, maybe your mesh size is not sufficient, it makes no sense to make your mesh size finer and finer, because if you make a mesh size with 1 nanometer, it is senseless, because the mechanical properties which you use will not reflect what happens at this scale. Okay, let us at first start with ideal brittle or nearly ideal brittle materials, because some of the nearly ideal brittle material, like a window glass, can also be considered, but it is not really ideal brittle. It is a bit larger than the Griffith toughness, but you can treat it, and the fracture process zone is not significantly larger. In this case, it is quite simple. You can also, because the surface and the non-reversible process which may happen in, for example, window glass, they are also related to areas similar where the fracture process zone takes place. So, and this is what we called before about 1 nanometer or 2 nanometers. Yes, that's not large. 2 nanometers is the maximum size. But when the fracture takes place, when the non-linearity of our deboning process really are important. And also the nonlinear, the effects which may cause a deviation from the ideal brittle behavior are in many cases are related to this area, for example in window glass. And in this gamma the surface energy is more or less independent of the size. And therefore, the fracture toughness is in principle independent. You can also go even to nanometer size. Example, it ends when you go to maybe the size of few nanometers. Then it becomes again a atomistic problem. But as long as your sample size is larger than 2 nanometers, then you are out of the range. This is very seldom that you can do this because in most cases, for example in metals, you form an oxide layer which has approximately the size of this. It's only gold. Gold you can really make wires of nearly one single atom of gold, but this behaves then somewhat different. But that's a special story for physicists. Okay, but nevertheless, testing of because it is really often the case that one tries to understand this ideal brittle behavior, especially fractured interfaces, but also the semiconductor industry have very often this problem of nearly ideal brittle behavior of materials, and they do not know how the toughness change when they change, for example, the chemical composition of their of the coating material and so on. And so they have nearly ideal brittle, and so they want to measure it, and not only with trial and error. Usually, in the nearly whole semiconductor industry, they work with trial and error, like the Smiths in the medieval time. Yes. But they want really to understand this, and therefore they use now this technique also to quantify it. But it is not always simple, even if it is size independent. Yes. And what are the reasons that one of the problems is the notch root radius to really produce a crack, atomistical sharp crack, and the other one is to locate the crack, the notch or the crack at the plane with the lowest fracture toughness. That's the two. But at first, let me say what is the shortest crack length where the simple fracture mechanic works. So what happens? You see again here our atomistic crack, and this here are the stress fields which we discussed before as a function of the distance of the crack at the same stress intensity factor. This is the sigma 2 value. Yes. So in the loading direction, and here for different. This is a 10 millimeter long crack. This is a 500 nanometer long crack, and this is a 10 nanometer long crack, and all are loaded with the same stress intensity factor. So if it's loaded with the same stress intensity factor, it means nothing else that our near-tipped field is exactly the same. Yes. Only the far field stress is different. Yes. And so what you here now clearly see, okay, this K-dominated zone, the long crack is really large. Yes. It's nearly 1 millimeter. In this 500 nanometer long crack, it is 50. At least yes, about 50 nanometers. But in the 10 nanometer long crack, it is only about 1 or 2 nanometers. Yes. So it is in the order of the fracture process zone. And therefore, and if we now look to the fracture stress divided by the theoretical stress of a material, you always have a theoretical strength where you can separate the atomic bonds, yes, by shear or by decohesion. This is the theoretical strength by decohesion. If you have a defect, your stress cannot be larger than the theoretical strength. Yes, that's clear. Okay, and when your defect size is very large, the fracture toughness describes the strength of your material. It is simply the square root 1 over the square root of the crack length in this area. And when the crack length, this is the Burgers vector, you can say the lattice spacing, yes, which is typically 2 to 3 angstrom or 0.2 nanometer. So when the crack lengths come in the order of about 20 nanometers, then we get the deviation from the simple fracture mechanic estimation. And then we have a transition to the long crack behavior. And here, Wertmann has used to describe this transition with fracture mechanic tools, where he used the so-called Barnblatt model, or it is a cohesive zone model, which is very often used now for complete other things, but it was originally developed for the description of ideal brittle material from Barnblatt on the base of on a stress-based concept in the beginning of the 60s. Wertmann has now used the same concept simply to look what happens when we go here to nearly nanometer cracks. And in principle, it works. The only difference is one has to use one has to take into account the nonlinearity in the cohesive zone. Okay, so that we can really use it to really very, very small crack lengths. In standard micromechanic experiments and even nanomechanic experiments, it do not really have an impact, this very short crack length, because crack lengths in the order of, you will see, of 2 nanometers are nearly impossible to realize with machining technique. But one should, in the discussion of the properties of material, is often important, because, for example, aluminum forms an oxide layer of typically, yes, 2-3 nanometer thickness. And the question is always, when this layer fracture, behave this crack as a real crack or not? So, and here we are really in this area with this type of cracks. But this is out of the range of standard fracture mechanics. But it is important when one discuss this phenomenon. One should know this relation, that when the crack is so short, then you can assume also the theoretical strength. It is not really dangerous if you have a crack in aluminum in the oxide layer. Okay, the next point is focused ion beam workstation really allows machining with nanometer precision. Exceptional. But if you machine a notch, the notch radius is typically, if you use very small current, it is always larger than 5 nanometers. Yes? But 5 nanometers are large. Yes, this is atomical sharp crack. Yes, and these are 5 nanometer crack. Yeah. So it is not really atomistically sharp. And that's often when we measure then the toughness of these nearly idle or ideal brittle material, then it's always the discussion: is this really the toughness? Can it not lower if we would have really an ideal brittle, atomistic sharp crack? One of the ways which we usually try to do is to introduce not a straight crack front, to introduce irregularities along the crack front. So, for example, one machine the notch, and then really good resolution. And here we have a small bridge, and then we load up the crack, or we load like the chevron. This in principle the classical chevron technique what we use, but it's difficult to produce a really well-defined chevron notch with a fit. Especially to have a chevron notch with a very sharp notch root radius. Because the stress intensity, which usually at a constant load increases with increasing crack length, but in this chevron notch, it decreases because the length of the crack increases. Or the length. The width of the crack increases by appropriate design of the sample, the stress intensity, and the advantage of this chevron notch is that it is not really necessary to measure the crack length. The only thing you have to measure is the load. Because if you know at this load you will have critical crack propagation at this length and at this load, and then you can simply calculate the stress intensity. But we don't, in micromechanics, one usually do not use the chevron notch because it is a bit difficult to really fabricate it. But one introduces some irregularities, and then the crack starts at these irregularities, and then one have a pre-crack along this notch, and they can then travel through the notch. Here you can see some of the experiments also for semiconductor, in the semiconductor area, where we uses here different, or where we have measured the strength and toughness of different type of isolation material, silicon oxide with a certain amount of nitrogen and hydrogen. And what you see is the strength of these materials is always very near to the theoretical strength of this material. They have an elastic modulus in the order of 80 to 100 gigapascal, and the strength is about in the order of 6 to 10 gigapascal, which is about 1/10, and that's always the rule of thumb that the theoretical strength is about 1/10 of the elastic modulus. Or in other words, if you have no defect, you have no dislocation, and you load up a sample, you the maximum, the strength which you can obtain is the theoretical strength, and this is approximately, or the strain which you can apply is about 10%. In 10%, the distance, change the distance between the atoms. That's not so different in different types. And then we also measured the fracture toughness. And in reality, what you see is the fracture toughness of the semi-brittle material in this case scales relatively good with the elastic modulus, which is not so surprising, because one would assume, okay, this different type of doping, they affect the elastic properties, but it will not significantly affect the surface energy. And then the relation between surface energy and fracture toughness, they are related to elastic properties. All these things, what we have discussed here, is also a problem in semi-brittle materials. Yes. If we have a problem in semi-brittle material, we always, in most cases, we want to study individual processes in the semi-brittle. But even when we try to measure, for example, the interface toughness, the problem is here at first the notch root radius, and the second one is to fabricate a notch which is really perfectly located at the interface. If it is not perfectly located at the interface, it is not surprising that you measure completely different story. And even if the interface is only 20 nanometer away, but 20 nanometer is really a huge distance, yes, for atomical sharp cracks. Maybe here. This was a trick where we have measured the interface between silicon oxide and copper, where we have simply, you see here this bending beam of copper, and here is the silicon, and we load up the sample here, it will fracture. Unfortunately, this video will not work here in this version. But okay. Oh, it doesn't work. Excuse me. I don't know why it doesn't work. Transfer. Okay, then let's start again. Yes. Yes. Okay. So you can see here a typical experiment. So it is, you have seen before this low displacement curve, and here, yes, because it is fast running, the scan was very high, but now you see the crack is generated, and then you can look to the growth of the crack, and from the growth of the crack at the interface, you can then really determine the interface toughness of these materials. So that's one of the other things that can work. Okay. Another problem which we recently also studied, this is a semi-brittle material. When we will make a break, I think we yes, and we'll go through this part, few parts, and then we make a break. This is we are looking for the fracture behavior of tungsten foils and wires. The reason is tungsten foils and wires are interesting material for high temperature application, for fusion application, but also for many other applications. But tungsten has one drawback. Tungsten is as a polycrystalline material, really brittle at room temperature. Yes. And in order to overcome this, we have looked if we can overcome this problem with a microstructure, a very lamellar or needle-like microstructure with grains of few nanometer thickness. And really, at room temperature, the toughness of this material is exceptionally high. Yes. It's in the order of 80 megapascal per square root of meter. And here, we could not really measure it with linear elastic fracture mechanic techniques of these wires. We clearly can see this is really neck. Yes. But what you see, it is really a fibrous crack with large plastic deformation, and the fracture toughness is again in the order of 100 megapascal per square root of meter, like a steel. Yes, this is for persons which work with tungsten. It is fantastic. Yes, but what you see is we have always this delamination. One of the questions we try to solve is what is the fracture toughness of these for this delamination of the grains. And we have again for the foils and the wires. And what we have done is, you see these small samples we have cut out from the wires and also from the foils. So it's nearly DCP samples, not really. But we have a certain mixed mode loading, but nevertheless, you see we have loaded this with a special fiber loading device and measured the propagation of the crack. What you see here is the change of the fracture toughness as a function of crack length. So it is also this type of loading is a semi-brittle, but this is nearly ideal. See this at 2 megapascal per square root. That's exceptionally low for fracture toughness. That's the reason why we get this delamination and the good fracture toughness in the other loading direction. And here you see it is significantly lower than in the case of wires. And the reason becomes quite evident if we look in the wires. We had these needle-like grains with about 200 nanometer, 1 to 200 nanometer needle diameter, and here we have this pancake structure with about 1 to 200 nanometer thickness of the pancake. And when you look here, now this is the wire, the foil which is splitted, and here the crack was nearly laid exactly in the plane of the lowest fracture toughness. But in this case, since you have the needles with 200 nanometers, yes, which has this 200 nanometers and we have a notch, and the notch is in most cases not at the weakest point along the crack. And therefore, we start significantly higher with the decohesion, and also then the bridging is more pronounced in these wires. Yes. And this shows clearly how important it is, if you really want to measure the intrinsic properties, to really look to place the crack at the position where you have the lowest toughness, where you expect the lowest toughness. Another example is here, where we, for the brittle fracture of tungsten, of single crystal tungsten, it is we have looked in microsample what is the effect of the deviation from the ideal brittle crack plane. So we again machined that microsample and deviate the notch. Oh, that's wrong. Okay, tungsten. I want to say only a few few words tungsten because it is very helpful material to explain why fracture mechanics is important. These are the stress strain curve of single crystalline tungsten at different temperatures. Okay, so you can see the single crystal at room temperature. We are here, or this is we are here. Here we are at room temperature. It's exceptional ductile. Even at liquid nitrogen, this is here in between 4 and 5. The ductility is even better at liquid nitrogen of the single crystal, enormously ductile. Yes. Only when we go to the temperature of 20, in the order of 20 kelvins, which is the temperature of liquid nitrogen, then you see really a significant reduction in the ductility. When you now compare the fracture toughness of the same material, and you look to the fracture toughness here at liquid nitrogen, it is 3 megapascal per square root of meter. This is nearly Griffiths toughness. It behaves nearly ideal brittle. And even at room temperature, it has only 6 megapascal per square root of meter. It's like a ceramic. And we come to a ductile to brittle transition, we have to go to 300 to 400 degrees centigrade. So this clearly illustrates the enormous difference between ductility in a tension experiment and in a fracture toughness experiment. And this is so that mechanical engineers, some of the groups, they don't like fracture. I do not know why, but then if one show him this story, then he see why it is important. So we have already, I've mentioned that we have made samples with different notch geometries, and you see the interesting thing on the micro dimension, the behavior is again relative ductile. It is not really ductile, it is a semi-brittle fracture process, but the semi-brittle fracture process is extremely dependent on the angle from the deviation of the ideal angle. So the fracture toughness becomes exceptional dependent on if we are at the lowest crack plane or on the crack plane with the lowest fracture resistance or not. And this is the case for semi-brittle as well as for ideal brittle. Okay, then we make here a break, and then we come to the next point, which we have especially to take into account when we go to semi-brittle material and ductile material. It is that plasticity becomes size dependent, and when the fracture process zone comes in the order of our plasticity dominated atomistic defects. Okay, thanks. We make a break of 10 minutes or so. Fine. So let us continue. Yes, before we discussed the problem with the size dependence of resistance, toughness, or fatigue crack propagation. It is important also to discuss the size dependence of plasticity. In order to understand this size dependence of plasticity, it is important to look to the real deformation process. The most important is dislocation motion, and since you're mechanical engineers and maybe also civil engineers, they are not so familiar. In order to give a very short introduction to this area, I will try to show what happens when you deform a metal. Plastically deform. If you elastically deform, you simply stretch the spacing between, you change the spacing between the atoms. But when you plastically deform, you do not destroy the lattice. The only thing what happens is that such defects moves in the crystal. So if you deform it, you simply go from here over such way. This was really 100 years ago a big question. How could we deform a metal and the crystal structure remains? And then in the beginning of the 1930s, Taylor introduced this so-called edge dislocation, where we simply have a additional half plane which moves. It is not really the half plane moves, it is only this defect moves through the material. And this is this half plane in a simply cubic lattice. But this half plane, it can also be curved. And then they form this so-called screw dislocation. This was realized 10 years later, or 8 years later, that dislocation is not always such a single half plane. It is that also you have, if you go around this crystal, you make here a step. In this case, you have here a missing area. This is the Berger effect. And all the plasticity is caused by this movement of dislocations. There are millions, billions of dislocations which realize periplastic or plastic deformation. Okay, good. This is an important point. So what happens is dislocation moves on specific crystal planes. Yes, and therefore you can see here. This is a microsample and tension loaded microsample, and you can clearly see that these are always a certain number of these Berger factors, these steps which forms always. And you see that this part of the crystal is not deformed. Only the deformation only took place on these special planes. And so if you apply continuum mechanic, you can apply continuum mechanic only on this scale, but it makes no sense to apply the stress strain behavior on the scale, which is smaller than typical distances between the slip planes, or where these locations are activated. I will not go through. Important is there exists a certain stress to move the dislocation. This is the pile stress. Then there is a lot of things related to the hardening of the material. It is a thing, a funny story about this hardening, how to understand hardening. And even I think Taylor made this, or Taylor or Orwell made this comment. The hardening was the first thing what physicists thought to be important to solve, and it may be the last which will be solved. Yes, it is even today not completely solved. Important for the understanding what happens, especially in front of cracks of semi-brittle material, also is the multiplication. The most important multiplication process is this Orwell mechanism. The dislocations are usually they are pinned between boundaries, dislocation boundary, or between inclusions, second phases, and so on. And when you load up this dislocation, which is always a line, yes, it's always a line, because it must somewhere end. Even if you take out, then this line goes in the depth, then down, again down. So it is always it must end at the defect, or it must be a closed loop. And this is a mechanism how you simply multiply dislocations. You pull it out, you form a ring, then this part moves in this direction, this in this direction, and you have again the source and it multiplies. So you can multiply the numbers of dislocations. So the density of dislocations varies. If you have a recrystallized material, so if you slowly cool down from high temperature, the typical density of these locations is 10 to the 12th per square meter. What does it mean? If you take a square meter and you count how many of these half planes you found, yes, on this area, and then you found 10 to the 12th of such defects on 1 square meter. And the mean distance then between these defects, you can simply calculate, is 1 micron. This is the typical density of these locations in metals at when they are recrystallized, so when they are really cooled down from high temperature. When you deform, the standard deformed material have a dislocation, yes, about 40–50%. You have 10 to the 14th. So the mean distance is about 1/10 of a microns, or 100 nanometers. So if you look on atomistic with atomistic dimensions, it is not so easy to find them. Yes, there are other techniques, the contrast technique in the transmission electron microscopy, where you can see it much easier. And if you deform it extremely heavy, you come to about 10 to the 16th, but not more. Usually, maybe 5 times or 2 times 10 to the 16th, or not more. Then there exists mechanism where there is a recombination and there is an equilibrium between generation and annihilation of these processes. So in this case, you have a distance, a mean distance of these locations, which is about 10 nanometers. So every 30, if you go 30 atom distance, you will find one of these defects. In reality, when you have this high density, then you make they are not homogeneously distributed. They are usually arranged in walls, cell walls, and a region where there are less dislocation. So when you, it is now important, especially when you look, if your crack size become very small compared to this length, yes. For example, in semiconductors, the density of the dislocation density is even significantly lower. Yes, it is only, yes, I would say 10 to the 3 or something, or 10 to the 10 to the 8. So the distance between defects is really very large. Yes. So, and if you have a crack with a length of 1 micron, the crack will not see any dislocation. Yes, it is so far away that it will not, the loading will not be affected by the dislocations. And this is also important when we look then to metals. If our crack comes in the order of microns, then this question, if it is only 1 micron, then I have nearly no dislocation in front of the crack, or the next dislocation is at a distance which is equal to the length of the crack. And we have already seen that the stress the distance equal to the crack length is significantly lower. Yes, it is nearly equal to the stress, to the applied stress. So the dislocation will not see the crack, the stress field of the crack, will not really see the stress field of the crack. And if we want now to describe plasticity, that's also important, that we can only describe plasticity in regions which are smaller or which are significantly larger than this length. If we are smaller, then we have a perfect crystal. Okay? And that's important not only for microsamples, it is also important, for example, for fatigue loading. In fatigue loading, especially when we look to fatigue crack propagation near the threshold, the load which we apply are extremely low. Yes, they are, you know, the threshold is in the order of a few megapascal times square root of meter. And in this case, the size of the cyclic plastic zone, if you calculate it, is in the order of micron or below. And if you think that your plastic zone is 1 micron, but in this 1 micron you will not find the dislocation. So what you do is in principle nonsense, yes? In this case, if you calculate the stress. So in order to do this, you have to really, especially in this, small, if you have heavy plastic deformation, then your spacing is quite small. So it is easier to, or you can use the standard elastoplastic concept with Mises plasticity, even to significantly smaller scale. But when you are in this region where you have only very small dislocation density and very small loads, then it is most probable that we will not find a dislocation in front of the crack. So, what happens when, what happens in a metal or intermetallic material, or even in ceramic silicon? What happens when you load? When you load a crack, and if you have no dislocation and no dislocation sources here in front of the crack, it has two possibilities. One of the possibility is that if you have applied a stress intensity which is equal to the Griffith stress intensity, it will fracture. Okay, but we know in most of our metals this doesn't happen. What happens is that the crack tip itself generates dislocation. So the dislocations are generated, and if you hear, this is a pure elastic loaded, simply linear elastic loaded atomic arrangement. And when you carefully look to this line, so if you look here, it looks really perfect crystal. But if you look here, okay, this may be like an embryo of a dislocation. And that's exactly what happened if you load up, and in some of our materials, and these are the ductile materials, the stress intensity to generate the dislocation at the crack tip is smaller than the stress intensity to fracture the atomic bonds here in front of the crack. And that's the reason, that's what we call, from physical or material science point of view, is intrinsic ductile material. They may fail semi-brittle, but they generate dislocation before the atomic bonds are fractured. Okay, and you clearly can see there are only one dislocation. Here's one dislocation moved and one dislocation. This is the same crack. The only difference is that one dislocation moved here and one dislocation moved here. Yeah, that's the only difference between these two. Okay, so that's in silicon at room temperature. There was a long discussion in the 1980s. Is the problem the emission, or that you have also the dislocation have to move? Yes. And there was the discussion: is it difficult to generate the dislocation, or is it difficult to move the dislocation? That's so. But this is a small, tiny thing, and they've finally come to the conclusion it is the problem to move the dislocation away from the tip. Okay. There exist other groups or possibilities that you have, for example, in a heavy deformed material, that you have, if you have sufficient number of of sources, then you can again load up, and the dislocation source will activate, and you will generate the plasticity. And the first group, this is this type of simulation we have done in the 90s. One of my first or third doctoral student, and at approximately the same time, the group of Needleman van Gießen performed exactly the same simulation, but with one difference: they don't assume generation of dislocation. They only placed a large number of sources in front of the crack, and these sources generate dislocation, and then the crack can grow by, in their model, by a decohesion similar as in the Griffiths concept. The only thing which is necessary is that the dislocation sources must be activated before you reach the Griffiths toughness. Otherwise, it will fracture. That's the trick behind this thing. So to describe the fracture process of these, let me say now, semi-brittle materials or plasticity in these small dimensions, we know when we come to these small dimensions, typical Mises plasticity becomes senseless. One of the things what continuum mechanic groups have done is to use crystal plasticity, where they take into account really the single slip processes, but even this crystal plasticity concept cannot be used on this scale. They can only used on scales which are large compared to the spacing of dislocations. And they cannot describe, for example, the size effects. It will come in a few seconds. They cannot describe, because it is a continuum mechanic concept in the standard version. If you take then into account the gradient, then you can also come to a size effect. They can introduce a size effect. The next, which really can tackle this size effect, are this discrete nature of mechanic of discrete nature of plasticity. But this discrete nature of plasticity can describe the growth of the evolution of plasticity, but it is difficult to describe then even the separation process at the crack tip. These can only describe the fracture process. Then you have take further assumption. Another possibility is then to go even further, to go to molecular dynamic. But molecular dynamic has the disadvantage that it's really limited to very small volume. Yes, you can. Even today you can use 1 million of atoms, but 1 million of atoms is not so large. Yes. If you look to a cube of 1 million atoms, there's are only 100 atoms times 100 atoms times 100 atoms. That's not more, and that's not much. Okay, and if you go, and even this molecular dynamic are rather limited because the potentials which you use, because you simply assume that you have points with a certain potential, with certain laws of which depend on the distance of the atoms, yes, of cohesive forces, and the real description you have to go to density function theory, the quantum mechanic. But in this case, the maximum atoms are about 1,000, yes, maybe 2,000 if you have really enormous computer power. But in this case, the only thing what we have already done, we have sometimes used this, is to calculate the stress which are necessary to move the dislocation at 0 Kelvin, or to look to the structure of the dislocation or something. You can do, but it is not possible to really describe plasticity in a unique way on this scale. That's an important point. And that's also the problem why we cannot describe the fracture in a simple way, in a unique simple way. One has to take this always into account. We have to simplify our view. Okay? So, when we now, for this consideration of the stresses, the dislocation, from the dislocation mechanic point of view, is the simplest one, because it is really analytical. You can analytically describe the stresses in distance of nanometers. Yes, when you realize plasticity, for example, in mode 1, mode 2 loading, this point means that you have edge dislocation. These are screw dislocations to realize a mode 3 deformation. So why you can do this is if you, this is now crack, if you introduce or if you omit two dislocation, what we have done here before, in this case, like in this case, yes, can really calculate the stresses which are caused by these two dislocations. And these are the tension stresses induced by the two dislocations. Here is one dislocation, and here is one symmetric. And the interesting thing which this figure should show is that this dislocation induces near the crack tip a stress field which is exactly the same stress field as you would load the crack. In this case, it is a compressive stress. So it means that you would compress the stress. Or in other words, if you generate here these two dislocations, and you apply a external stress, you get the stress field, and the two dislocation reduces the stress field. That's the effect of the plasticity, exactly what happens. But really, near the crack, the stresses can be in the order of near the theoretical strength. And they are not, if we go to nanometer dimension, then the stresses can really, here these are for 20 dislocation. I think, I do not know why this image shifted. Okay. So when we have a dislocation, when we generate dislocation here, and this dislocation are usually, especially if they are generated at the crack tip, the distance of the dislocations are in the order of few 10 to 100 nanometers, yes, typically. And if they are generated at the crack tip, they form a zone which is nearly free of dislocation, few 10 nanometers. And it is interesting that you can really describe by linear elastic tool, not with linear elastic description, the stress at the crack tip, and the stress at the crack tip is simply given by the applied stress and stresses induced from the dislocations. These are exact linear elastic solution. This is an exact linear elastic solution from the loading. It is exact linear solution from the dislocation. And since in linear elasticity there exists a superposition principle, and you simply can superimpose all the things. And it is, in principle, we could describe the plasticity in front of a crack on discrete dislocation mechanic. The only problem is that we would have to take into account all the dislocations which are generated. Yes, this can be millions. And the description of the plasticity is very similar to the description, for example, of the arrangement of our universe. Yes, if we know all the masses distributed in our universe, at the speed of all the masses, it is very easy to calculate what happened with this universe. Yes, because we know the gravity law, we know the law, the simple Newton laws, and that's else. We have not to do more. The only problem of the persons in astrophysics is that they do not really know the exact distribution of the masses. Yes, But in principle, it is not difficult. And the same problem have we in our case. And the problem is that so many dislocations are there. And only for, I would say, in 2D, we can treat about 2,000, 5,000 dislocations. Yes, what you have seen here, for example, these are few hundred, but in principle, a few thousand would also be possible in 2D. In 3D, it is, you have to separate this line into small pieces. There exists also exact solution, what is the stress field of these small pieces, yes, of dislocation. And the only thing what you have to do when you calculate is, you simply look to the position of the dislocation, you look what is the stress caused from the external loading, and what is the stress from all the other dislocations, all the other pieces of dislocations. And then you know, okay, the stress, the dislocation can move or cannot move. That's all. So in principle, the calculation is simple, but it is simply a problem of power. So this is now here, you see what happens when we load up. In this case, it was a mode 3 crack, but for a mode 2 crack is exactly the same. The only difference in the equation is here, 1 minus the Poisson ratio is different. If we load up, then we generate the dislocation here in front of the crack. And this is the stress field of the dislocation. Yes. And this is the stress field which causes the stress field, the change of the stress field at the crack tip. This is a so-called shielding stress intensity. And in the near vicinity of the crack, you can describe again the stress field by a local stress intensity factor, which is simply the applied stress intensity minus the stress intensity caused by all the dislocation. That's very easy in principle. So when we look, for example, here there are 9 dislocations generated, and if we look carefully, then we see, okay, here there is 1 dislocation, next, and so on. We see the singularity in the vicinity of the dislocation. We have also a singularity stress field, and so if we would really measure the atomic displacement, we would see this stress field. Yes, except the distance is smaller than the dislocation. It makes no sense. And this is exactly what we would also, from continuum mechanic point of view, we would expect this behavior. Yes. But in reality, we have these variation of stresses. They are enormous high. Yes, can be enormous high, even in the case of plasticity. Yeah. That is what we always should take into account. If you assume a low strength material, you assume that the stress is very low at the crack tip. But that's not true. The mean stress is low. Yes. The local stresses can be in the order of the theoretical strength. And you will never have a deboning of atoms when you are not in the order of the theoretical strength. That's what you should always take into account, yes, when you look about fracture. So this is the typical scheme which we use when we discrete dislocation simulation. In this case, we have always a stress field from the applied loading. If the dislocation is in the vicinity of a free surface, we have also to take into account that the stress field of the dislocations are only simple for infinite size. And, but it is easy, if a free surface is there, you can take into account by image stresses. And this stress, if this stress is larger than the critical one, then the dislocation moves. Here this is for a mode 3 or mode 2 crack. The equations are not very difficult, yes, which you use. And what we have done in the 90s is to understand the threshold by this discrete the threshold of, for fatigue crack propagation by this discrete nature, because at these very low load amplitudes, the numbers of dislocations are quite low, so that classical continuum mechanics cannot be applied. What we have done is simply, okay, we load up, generate dislocation. If we unload, few dislocation will run back, and they form new area, and in the next sample, next loading cycle, it will happen the same. That's really the process in ductile materials. You see, this was the results of discrete dislocation simulation. You see the arrangement of dislocation, and the crack is grown, and they form some serration, some special shapes. Okay, I will show you one thing. This is what happens when we load, for example, a crack. It's really taken into account only that you need a certain friction stress that the dislocation can move. If you unload the crack, dislocation moves back. They form this V-shaped crack. If you load again, dislocation moves again away from the crack end. If we assume that the surface cannot revolt, the crack grows by this process, and it really shows that the crack growth behavior in the discrete dislocation simulation is really very similar to what we really physically observe. This is here now for the crack is now grown. The crack is now grown over a certain distance, about a few microns, and now what happens is also shown. So this is a cycle. This is after 1,000 cycles. Now the scale is varied. This here is in units of Berger's factor, or you can assume in units of lattice spacing. Yes, plotted. This scale is different to this scale, therefore you don't see this V shape of the crack. But what you clearly can see that the crack, we have the emission of dislocation. It runs back, and it really reflects what happened really at such small load. Okay, so and interesting to see the size. These are, well, let me go back. This here. These are 30 microns. This would be, if we have a coarse-grained metallic material, this would be more or less what happens in one grain. So this would be the arrangement, the necessary arrangement of this location. I will not go into detail, this would be another thing. But what you clearly can see, there are distances where these are nearly dislocation-free, and where really always more or less linear elasticity can be applied. Now let us come to the size effect. This is very strongly related also to the discrete nature of plasticity. The first, yes, not really the exact first, but really very popular become this area of size dependence in the 1990s, where Fleck and Evans have performed some key experiments on wires and bending beams with relative small dimensions. Yes, here you see the wires with 100 micron and 12 micron. They here plotted here a normalized yield stress. And what you clearly can see when this was always the same material, when you reduce the diameter, you significantly change the yield stress. It looks like a complete different material. But when you perform the same thing with the tension experiment, the differences are quite small. And the same was in the case of bending. So here they perform bending experiment as a function of the applied strain, and they looked here to the necessary flow stress, normalized flow stress at the surface as a function of the surface strain. And also, we could really see that the flow stress significantly increased, decreasing diameter. And this was one of the pace that in continuum mechanics they introduced the so-called strain gradient theory. But the question was now, can we use this strain gradient? These are samples in the region of from 10 to few hundred microns. Can we use these strain gradient theory also to smaller dimensions? Because we have seen that the mean spacing of these locations are typically 1 micron or below. In this case, the sample size is is large compared to the mean spacing. Okay, the question is now, can we use this strain gradient theory also to smaller dimension? So, this is now a nano indentation experiment, and you see the enormous change of hardness here as a function of the size of the indentation size. In reality, it falls even further. But for this case, you will see this later. We have to use a logarithmic plot in this area. So the standard, most used concept to explain this size effect was also the strain gradient theory. This results in the so-called Nix-Gao model. And I always had some doubt on this, that this really works for these extreme small dimensions. And so we performed really careful experiments. The idea of this Nix-Gao model is really simple. Yes. The idea was, okay, when we increase the plastic deformed volume below the surface is always proportional to the size of the indentation. That's the idea. And in order to realize this shape, we need a certain amount of dislocation, because in order to make all this shape change, we have to move this location here downward. Yes. Or there exists different arrangement, but in all the case, we need a certain number of dislocations, yes, to realize this. And if we want to pack this in a certain volume, we have a much denser arrangement of the dislocation when the indent is small compared to a large. That's easy to calculate when one do this. And if one take this then into account with this strain gradient concept, then which is more or less based on this already in the 1913s introduced concept by Taylor, that is dependent on that the yield stress is proportional to the square root of the dislocation density, and then there exists statistical stored and really geometrically necessary dislocations. These are also the base for the strain gradient theory, because in order to realize a strain gradient, you need geometrically necessary dislocations. And if you do this, then you come to this relation. And if we plot this really careful measured over very high range, then we see that this do not work. And what we also have done is to look to the arrangement of the dislocation below the indenter, and what we have found is that it is this principal assumption that this deformed volume is proportional to the size is not true. In small deformed volume, the dislocations are more widespread than in the case of large indents. And therefore you have a different gradient or different geometrical arrangement of the dislocation. And this goes to this relative complex change of the hardness as a function of the indentation size. And what you really see is that the hardness of your material here, when you go of the single crystal to the largest values, can be or very nearly 1 order of magnitude. It is exactly the same material. It's a perfect single crystal. Yes. And even if we would go to even finer, smaller crystals, we would come to higher values. So plasticity is extremely size sensitive when we go to dimensions of below 100 nanometer. But when we look to the separation processes in brittle or semi-brittle material, then we are in this area. Yes. Exactly at the same time, beginning of 2000, there were another story coming up. This was the so-called micropillars. The most prominent, unfortunately, we have applied for our FIP in 5 years before, but we couldn't get it in our first approach we need. And this was approximately 1 year, the same year where we got our FIP, and therefore Eugene was somewhat faster than we. He measured the strength of a different type of materials as a function of the diameter in a compression experiment. And you see the enormous variation of the yield stress as a function of the diameter. Here you see a summary of the results. Again, here the size. And this also clearly indicates that strain gradient cannot be explained why we have this increase in yield stress. There was really a big discussion about 10 years ago that we have a compression experiment where we assume that we have homogeneous stress distribution in this area, yes, and we get a yield stress variation of again more than 1 order of magnitude. Yes. So what should we do? Okay. One of the things for this large effect is what we thought at this time is that one of the large effects is the dislocation. They can maybe move here free, but the problem in a compression experiment, they cannot run out here at the top. If they run into the surface, it is difficult. So they cannot pass through the whole sample, and that's a problem with compression experiments. But it's a compression experiments, the most simple one if you make small samples, because it is very easy to fabricate such a pillar, yes, with a focused ion beam. Therefore, we started with our tension experiment. It was the first tension experiment. And what we have done is now to simulate this. We have changed the length of our sample, the deformation length of our sample. We have always the same dimension. Okay. And what we can see is that even this volume, the length of these, dramatically affect the yield stress. Nearly factor of 2, yes? That's enormous. Because it is not so surprising, because we have here dimensions, that's are the typical distances where dislocation moves, yes? And therefore it is not so surprising that the yield stress in this dimension changes over such a distance. And here I have tried to summarize what we have done. These are the compression experiment, this pillar experiment. It shows really a pronounced size effect. These are the tension experiment with what we call standard tension sample, where the thickness is 1/5 of the length. That's our standard measure. And this is when the length is smaller. Then we come more clearly to the compression. And one of the things is that this dislocation moves on plane, and only when the dislocation planes over the whole length on free surfaces, then they can really move freely. Otherwise, they are constrained here, top surface or the bottom surface. And this makes or induces significant constraint and induces significant size effects. And this is, if you look then, for example, to semiconductor components, where you have dimensions of metal films in the order of microns, which are within a surface which are attached to silicon, maybe above is an oxidation layer. And we have these dimensions, and you cannot simply use the yield stress of kappa. That's senseless. Or when we look here, if you look to, for example, for a medical device with small dimensions, which are mainly banded, for example, or for flexible electronics, which are also mainly banded, you see that the yield stress of these kappa changes again from 200. This is a really macro, and this was not the onset of yielding, it was really, I would say, the plateau strength during the yielding. It is 5 times higher. And the reason is relatively simple for why bending is, we have not studied over such a large distance in the bending as in the tension experiment. The reason is quite simple. If you generate a dislocation, the dislocation can move in a certain direction. But at the opposite side, the shear stress is in the opposite direction. It cannot move further. Yes? Only the dislocation can move it somewhat above. So the neutral axe in the bending beam is somewhat like a barrier for the dislocation, like a grain boundary or phase boundary. And therefore, in the bending experiment, the yield stress is significantly high. This is a typical experiment, what we have done. We've done the first of this type in the beginning of 90. But then, here you can see, one could do this in a 2D experiment. Oh, it's not working. Why? It's not good. Why? Let's try again. Oh yes, now you can see. This is now really 3D calculation. 3D, MD, or discrete dislocation simulation. In 2D, I thought that you can really realize relative large plastic deformation, but they do not reflect the real plastic physics. They reflect some of the effect of discreteness of plasticity, but not all. And for this, you have to take into account really the 3D nature. These lines, what we have seen, these dislocation lines, they are curved. And when you make this 3D calculation, you have to take all small parts of this and to look what is the effect of these small parts on all the other dislocations. Yes? And you have to do this for every movement step. And that makes the limitation for this discrete dislocation. What you really can see is that all the dislocations are stored here in the center and piled up to this neutral axe. Okay, so when we talk now about the yield stress or the fatigue strength of metals, we have also seen this for fatigue experiments, as a function of the sample size. Here we have taken a logarithmic scale, and if we are in the area where the microstructural size is very small compared to the diameter of our sample, then we are in a size-independent region, yes, for plasticity, for the yield stress, and also for the fatigue properties of the material. But when we come into a region where the dimensions of our sample becomes in approximately the order, if we 5 to, yes, we have seen 7 to 8 times the grain size, for example, then it is interesting that the strength go down. That's a simple effect that the surface of the plasticity is not as constrained as in the interior. It is quite easy because, yes, in the surface, deformation can do what they want to do, but here at the boundary between to the next grain, plasticity cannot do what they want to do. They have to adapt with the neighboring grain, the plasticity. And therefore, we have this decrease in fatigue strength and also the decrease in yield stress. And when we come then into region where the size of the sample is smaller than the crystal, then we get again a significant increase. This increase depends on many different things. It depends on the constraint. But one of the reasons, even at very long crystals, single crystals, there exists a very simple reason why the yield stress increase. You need a source for the dislocation generation. In this coarse-grained material, the size of the source is simply limited by the grain size. And here, the size of the source is simply limited by the size of the sample. That's not really difficult yet. But the real behavior is difficult. Okay. So let us start with some points before we stop here. The ductile fracture. We come then to the semi-brittle of micro-sized dimensions. So ductile fracture is, in our material science point of view, is the generation of pores, the growth of pores, and finally the coalescence of the blunted crack with the pore. Yes, that's ductile fracture. And when we talk about ductile fracture, we have always the discussion, what is the stress state in front of the crack? And then we always ask, what is the stress state at the crack tip? And what is the stress state in larger distance of the plastic zones? This is also important when we go to the semi-brittle process, yes? Because semi-brittle fracture may occur in the whole nonlinear region, whereas ductile fracture mainly occur at the crack tip. Okay, when we look to the effect of the stress state, we have only the simulation, and we have only the simple solution for plant stress and plant strain. The real intermediate is more complex, but this is the situation. In the elastic case, in principle, in the elastic case, the stresses in the loading direction and in the growing direction are exactly the same. They are not affected by the stress state. The only difference is that in the plant strain case, in the direction perpendicular to or along the crack front, sigma ZZ, the stress is 2 times the Poisson ratio times the stress in the loading direction. And there is one difference also between plant stress and plant strain. It is if we recalculate the energy release rate, there is this small difference. As in the plant stress case, in the plant strain case, the energy release rate is somewhat smaller than the energy release rate in the plant stress case. This is simply due to the relaxation. The relaxation in the thickness direction delivers more energy for crack propagation, because in the thickness direction, in the plant strain case, the volume elements cannot go back to the unstrained case, and therefore there is this small difference. But that's the only difference in the case of elastic loading, of the effect of stress state. But the effect of stress state in the plastic zone is enormous, especially if we go very near to the crack tip. And this is especially important in thin films and also in microsamples. In really macrosamples, it is very difficult to realize a stress state. Plant stress state can realize a plant stress state here at far distances from the cracks, but it is nearly impossible to realize it very near the crack. But in microsamples and in thin films, you really can also realize relative near to the crack tip a plant stress state. In the elastoplastic case, very near the crack tip, which means that we are looking here very near to the crack tip,